So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions.
Hi everyone!
Hello!
Welcome to the remote second edition of TypeScript Congress. Ahead of you is the Type Track, a collection of great talks that we have collected for you.
We are very happy to be here and we hope you enjoyed this conference. Hi, I am Liz Parody. Yes, Parody is my real last name. And I'm a software engineer focused on JavaScript and head developer advocate at Stateful. I organize different community events and I'm a speaker in different conferences. I love sharing knowledge, promoting JavaScript and Node.js ecosystem, and participating in key events such as this one and conferences to improve my knowledge and network.
Hi, I am Daphne Liu. I am a front-end engineer at Grow Therapy based in Seattle. I previously worked at Lyft, Yelp, and Shopify. I perform improv, write comedy sketches, and speak at other tech conferences as well. I don't know how many Daphnes you met in your life, but on Twitter, I'm the better Daphne.
Yeah, she's the better Daphne. Go and follow her. Thank you for the program committee and for the great program. All the amazing talks that you're going to see today, the speakers, is because of them. To Josh, John, Kelly, and Lance, a big round of applause to all of them.
We, of course, have to thank our wonderful sponsors as well. We got Rollbar, GraphBase, and Focus Reactive. We want to see Twitter full of talks about today's event. Show us where you're watching from and what your computer setup is like. And you can do that by tweeting your picture with the hashtag TypeScriptCongress. We'll be on the lookout for your picture because we have a raffle afterwards for multi-passes to Git Nation conferences. 2 winners will be picked randomly, and you can also search Twitter for the TypeScript Congress hashtag to see our setup too. And here is ours. That's mine with the board game table.
And that's mine. I also have something. It's not a board game, but it's like a yoga blog. So yeah, the things we do to improve the setup. The prize for 2 winners of Git Nation Multipass. The Multipass give you a remote access to the batch of JS conferences like React Advanced, React Summit US, Test.js Summit, React Day Berlin, and many more. You don't want to miss this. Find out more in portal.gitnation.org.
We highly encourage you to talk to the speakers after their presentations. To do so, please visit the Track with Speakers room. Just click on the cells with their speaker's name, and you'll enter spatial.chat, where you can talk to the speakers from the interface and type track directly. Be sure to also join the Discord server. To join, there is a link on the watch page or in your org emails. Let's just test it out right now. Make some noise in the TSC interface track Q&A and TSC type track Q&A channels. Post your favorite emojis or GIFs, or just say hi to everyone there.
Your feedback is very important to us because it helps us keep making the event better and better. We have a form available to you at typescriptcongress.com/feedback. Take your time and leave your feedback and thoughts there. We have a form that will be available through the whole event. You can fill it now or later or in the middle. We're always open for feedback. Also today at 6 p.m. Central European Time is the premiere of TypeScript documentary prepared by Offersen team. Please visit the YouTube channel. During the video, you will see, among other things, the speakers who are speaking here for you today. You can also watch Matt, the other MC.
Some of our sponsors have prepared very exciting perks. Everything is available for you all watching the conference, and you can check out the perks on typescriptcongress.com/perks to see what our sponsors have prepared for you. Now, moving on to the section that we've all been waiting for, the talks. Let our very first talk begin. Our very first speaker is Jen, who will be giving the talk Lessons Learned While Learning Live. Jen is a multifaceted individual with a passion for technology and a heart for people. Currently, she works as a developer advocate for Avon, where she helps developers harness the power of data infrastructure. Outside of work, Jen hosts Teach Jen Tech about exploring technology, and she also hosts a thought-provoking podcast called Shit You Don't Want to Talk About, where she fearlessly dives into challenging topics such as mental health, equity, and diversity. The stage is yours, Jen. A huge round of applause for our very first speaker in the Type Track.
Hello, hello, beautiful humans. Welcome to Lessons Learned While Learning Live. Picture this. You're about to go on stage and tell people about an idea that you just learned, or you're going on stage because you're about to learn from someone you've never met. What feelings are going on there? I'm curious. Because I know learning something new, scary. Not my favorite. Definitely. Well, I mean, it is my favorite, but like it didn't used to be my favorite. Never thought it would be that cool. But learning something new is very scary. Talking in front of people, whether it be to a screen or to a crowd of 10,000 people behind the screen or in person, This is terrifying. And also, not knowing. Not knowing is not fun because there's this whole shame and well, okay, we'll go through that another time. But it makes me go, ugh, ugh, I don't want to do it. I don't want to do it. It doesn't sound great. Then why would anybody do it? Why is it that scary? Like, how do we combat this, the not fun part? So to understand the scariness, it's the fear of the unknown. It's a big part of it. It's like, we don't know what's going to happen. We can't predict it. Therefore, our body doesn't know how to react. Fear of judgment. Dude, do I have lipstick stuck on my tooth? Could you tell me? If I do, I can't see myself right now, so y'all are going to have to deal with it, and you can judge me for it. It's okay. It's the human experience. Patience and practice. Patience and practice. This is really funny because this is my third time recording this talk, and I'm excited to talk about the Q&A with you, but I can tell you that my patience with inanimate objects is very small. But hey, I'm getting practice. And then there's those physical responses. Literally, your body doesn't know what to anticipate. It's that fight or flight or freeze or what are we doing? And then you have the pressure to perform. Are you going to do as good as last time? Are we going to, be able to outperform the other person? Are we going to hit those numbers? Are we going to close those sales? The pressure to perform. And all of those for myself go to the fear of failure. Dude, what if nobody sees it? What if nobody comments? Oh gosh, what if I don't get it? These are all things that get stuck in my head almost every time before I start to strain. And no, thank you. It's not fun. It doesn't sound fun. It doesn't sound fun. So let's talk about what we are going to talk about today. Because there is some pretty cool things we're talking about today, like the double-edged sword of public learning. Is it good or bad? Or is it both? Understanding your own learning techniques. Okay, y'all? We're going to say this multiple times throughout this presentation, talk, whatever you want to call it. We're talking about learning techniques, also learning styles. I'm not saying that learning styles is an exact science. That is a debate for off this talk, but it is a great place for people, including myself, to get an idea of some avenues to go look into. And then we are at TypeScript Congress. So what are the lessons I learned from TypeScript and learning TypeScript? I'm excited about that one. And last but not least, continue to learn. Like, what are we going to do to continue learning? It is so important. Oh, and hey, by the way, my name is Jen Janan. Yay, sparkly jacket. It makes me happy, even though this is a really old photo. I just happen to be wearing it again, and it makes me happy. All right. I am a developer advocate at Ivan, who is the trusted open source data platform for everyone. It's actually pretty dope, so hit me up if you are curious about that kind of thing. Also, Teach Gen Tech, where I am the host that is helping break barriers by getting into learning to get into tech. Wow, words and I. We are friends sometimes, but that is where I go to learn things. And I also learned a lot from a podcast, Shit You Don't Want to Talk About. It is pretty dope because I have a lot of conversations about stuff people don't want to talk about or learn about or struggle with in all three areas of my life. It's pretty dope. And if you scan that barcode, it's to a link to Linktree. You can connect with me. It'll have all of the information for the shows, questions, all of that, if you're curious about it. But I know you're more curious about what's the good in learning live because, like, seriously, we're kind of struggling right now. In this next bit, I'm going to be sharing some clips that will help you see different bits of the stream and my experience learning. Like, there's good because you get to share knowledge. And this is a clip from my very, very first episode with Yere, where I didn't know the difference between, I'm giggling because this was the beginning of my journey, baby Jen, of I didn't know the difference between HTML, CSS, or JavaScript. And here's a quick clip. I think that's a big part of the paralysis too, is it's like, if you start learning something and you're like, okay, so this teacher is showing you how to do it, yet they're talking at you because it's, recorded, it's not virtual where you can learn with them. It's very difficult because when you go to Google things, then they're like, oh, you do it this way, this way, this way. And it's not always, at least from a beginner standpoint, I'm just like, I don't know what you just said. I get that it might be a different way, but I don't know why and what it meant compared to like what this specific lesson is talking about.
Yeah, and I think that's one of the biggest challenges when you're self-learning, is understanding the why. And once you understand the why, then you can figure out, okay, this is the same thing but in a different way because of X, Y, Z. But if you don't really get that why just yet, and it's the most difficult part is to learn why we're doing things a certain way, then it's tough. And that's why I do prefer there are like learning groups and things like that where people learn these. I think that's a big part of the paralysis. It's so true. Too, is it's like, so true. If you start learning something, I mean, as much as I learned from Yuri, these just kept coming up and having to learn and overcoming fear of mistakes. Okay, that fear didn't go away. It didn't go away at all. It just makes it slightly less scary. Even 5 episodes in with Anthony, and this still happens.
Well, welcome. Wow. Welcome. Wow. Anthony, you are like our very first episode. I totally butchered saying hello as well. So can I blame you for this?
Must have jinxed you. I guess I'm cursed.
Well,
I can introduce you.
Oh, yes.
Welcome to Teach.
Well, welcome. Wow.
Welcome.
Wow. Anthony, you are like our very first episode. I totally butchered saying hello as well. So can I blame you for this?
Must have jinxed you. I guess I'm cursed.
Well,
I can introduce you.
Oh, yes.
Welcome to Teach.
Well, welcome.
I really am keeping that clip forever. If anybody asks, I'm saving it. And it shows how I'm gonna make mistakes. It's gonna keep happening because me and words don't always get along, and it's gonna happen even in this next part where increased understanding, and Jay is on the show to teach me about Python. And y'all, it's kind of clicking, not clicking, but it's starting to.
So now let's do the same thing where we do in options, change true false to false. Okay, so now do you think it's going to return true or false?
True.
Why?
Because at least one of them are false.
No, because any is looking for at least one to be true.
And since it's not using the word true, therefore it's not true. So
exactly, it's false.
Okay.
Yeah, and I mean we can run this and see. Like if
you're
return false.
Yeah, like what you're saying makes sense. I think it's just like saying true. There will be a false there. That is truthful.
Yeah.
As in, like. Yeah. Yeah. I still struggle with this. I definitely still struggle with all of it. And yet it oddly somehow starts to make sense. It's interesting, but we all have to figure out how we learn ourselves. So a bit about how did I get here? Because you don't just like wake up one day and be like, yo, I'm going to go learn live. I mean, some people might. It may happen. It didn't happen like that for me. The first, 30 years of my life, yes, I am an older millennial, was a lot about, I don't know what I want to do. I was in sales for a bit. That was fun, but way too stressful. I was in tech support for a bit. Also fun. didn't pay the bills that I needed. I also traveled and did other cool things, and it was a lot of fun. And then, I get back from a trip, and on my near 30s, I'm like, yo, I want to do something about human connection. And to do this, I must learn videography. I got an internship at a production studio. Pretty dope, right? Except it cut all of my pay, and then COVID hit, and it was just a shit show that year. So the end of 2020, I had brain surgery and then took a detour to a new company, and it was super dope. I worked with APIs and had a lot of fun. And between all of that, I took 8 months to try to figure out how to start shit you don't want to talk about. I mention that because that is a key time frame. 8 months. 8 months. It took me 8 months. It takes other people longer. It takes practice. It's the starting is the hardest part, in my opinion. But what happened after that? What about 2022? I got laid off. And then I met the Denver API people because I used to live in Denver, and they're like, yo, dude, come be the API Denver meetup co-organizer. I was like, sweet. They definitely did not sound like that. They are very French. All three of them that were the co-organizers at the time are all from France, and my last name is French. I try to say that was why they let me become a co-organizer. They're not convinced, but story for another day. Ori, one of the co-organizers, was like, yo, if you could be describe your dream job. And I was like, seeing other people succeed, advocating for them, making sure that things are accessible for those who can't normally get into understanding it or being able to have the same access. And he's like, and you like tech? I'm like, yeah, it's fun. It's always fun learning. He's like, yo, that's a developer advocate. Oh, I had a dream. It was like, I finally came up with something that I could work towards and a goal. And then I reached out to people. My bubble, my dream was a little busted. It was like, oh, you can't just go get a job in DevRel. It's not just like you wake up one day and you can go get a job. No, it takes a lot of work. That's also another story for another day. But the first 3 people I met were like, yo, dude, you don't have content. You don't know the tech or know how to code. So you're probably not going to get a job here. Like, you got the personality, but you got to have everything else to back it. And I was like, oh. Within a week, Teach Gen Tech was launched because I needed content. I needed to learn. And I started meeting people that were willing to teach me. Yay. Then I met Laura. Laura is such a dope soul. She came on the show and started teaching me Python, and little did we know that there was much more that was going to go into learning than I ever imagined. Some of which being learning styles. As a previous math professor, she was teaching me how a lot of people don't get algebra. And I was like, whoa, really? And learning how we learn is such an important tool in our toolbox. As a heads up, as we said earlier, these are learning styles. Go do your own homework on this. It's a good starting point. How to study. I honestly never knew how to use flashcards. It was pretty cool. I dropped out of high school. I winged it. I never actually learned how to keep up with it. And when are you productive? I didn't know that people were productive at different times of the day, and not everybody can be a night owl or a morning bird. Is that how early bird? Why is it night owl and early bird? Can it be morning owl? Anyway, learning while being neurodivergent. Thank you to Wesley Faulkner, who also taught me this during one of my first conversations with a DevRel, because I had no idea that I could be ADHD and dyslexic and learn to code. It was great. Patience and practice. Patience with myself. Still working on that one. And embrace the frustration. Yeah, no, bro. Like, I still struggle with this. Inanimate objects are not my friend. Majority of the time. I'm learning. We're getting there. one of the biggest things I could say to really get started was learning my own learning techniques. So if you're getting started and you're like, yo, I want to go start something new, how are you going to get there? How are you going to learn it? How are you going to get started? A big way that talking with Laura about made me realize that, especially with me being dyslexic, I found out that audio is really good for me. Not the only way I learn, and some people, that's why there's a lot of controversy around learning styles. I just happen to learn through audio a lot better because text is really hard for me. Visual, for myself, was watching a lot of videos. That is very one to many, so I can consume it and watch it many, many times. Kinesthetic, to me, and it made more sense of like if I were to go actually have someone teach me to do it or code myself. And learning these different pieces of me helped me embrace them and know which ones to use when. Same with sleep and productivity scheduled. Also, some have heard of them called chronotypes. Again, this is a great starting point, not any like saying this is the end all be all. I found out that even if I wanted to be any of these other animals, that I was a lion. Yeah. Waking up super early and being more productive the first half of the day, and then I'm dead for the rest of the day. It's not fun. I wish I could do more. But knowing this, I can embrace it. Knowing how to work with my neurodivergent. Yeah. It's fun. It's stressful. It's hard. I'm not alone. And talking about it, I was like, oh, all right. That's dope. Other people have it too. And how to use and find tools that help me with all of the above, like different alarms or text to speech, or, I do a lot of my streams with my iPad so I can write notes. All of these things are different ways that I have learned that go into my own learning techniques. And this all leads up to why TypeScript? How does TypeScript help? That's kind of a weird thing to help. And think back to when you were learning TypeScript. Do people say that don't you need to know JavaScript to know TypeScript? Well, it would probably have been helpful, but I like to do things the hard way, and that's really fun. So I'm learning both at the same time. Also, TypeScript gave me structure in the show and in the code, which is awesome and weird all at the same time. And one of the biggest pieces that TypeScript gave me was my community. So many people that I was learning from and associating with knew TypeScript. And so by all that, as you already know, TypeScript gave me structure with types. Okay. This one slide was for me, just for me. But there's also a big part of the community of why I started learning TypeScript and why it also made it a lot easier for me to learn was having someone on the show that also can be punny and goofy and break things down easily from a very complex point of view to a beginner point of view. I'm doing a talk at TypeScript Congress, and I'm going to use this quote, at least maybe like the last sentence. TypeScript provides a set of types. Yes. You do it. I'll clip it. You do it.
I thought we were doing it in unison.
I'm not that.
Like a
I
cult
don't know.
situation.
Okay. Well, TypeScript provides
a set of
type system
tools for
interfaces to help us model the wackiness.
That was great.
Josh says it was great. I think it was a little painful. Either way, it was a little fun. And Josh Goldberg is the author of Learning TypeScript. And this book and Josh and my open source guild community, open source raid guild? Yeah, community. OSRG. It's in the link tree if you want to come join the community there. All of these different people from so many aspects of my life knew TypeScript. So it made it a lot easier to start learning because that's who I was around. So what other things did TypeScript give me structure? it also gave me structure in checking errors, which, I mean, it does. It's pretty cool. That's what it does. And learning errors. Understanding APIs. Earlier, I mentioned that I worked at an API company. I also worked at the Denver API meetup, or was one of the co-organizers, and it never quite clicked. And learning TypeScript and putting structure to all these different technologies really helped. It also made me learn that learning Python and TypeScript at the same time, not my jam. So I stuck with JavaScript and TypeScript. Now, to continue learning, we always have room to grow. Your mindset matters so much. And please always remember that. I am so amazed at some of the guests that I've had on the show that have done such cool shit in their lifetimes and accomplished so much. And they come on the show and they're like, yo, I learned something today from the show. I'm like, wait, what? You learned something? That happens? That's cool. And always being open means we'll grow together. So, top lessons I learned over a year of streaming and 100 episodes later is, I don't know if this is good or bad to say at TypeScript Congress, but it's not as scary as they say. I mean, it's still a little scary. You know, learning and live streaming have some things in common. They're fun. And they're nerve-wracking. They're super frustrating. And it's always, we're going to wing it. You're going to wing it. Some part of it's going to be a wing it. And then we have learning how I learned. Like, that is something that I wish I could give everyone. That would be so helpful. And last but not least, doing things outside your comfort zone is kind of like a muscle. The more you do it, the easier it gets. Or the more you do it, you don't have enough time to like become a crab again and shell. I don't know. But it does seem to be getting a little bit easier. So what are 4 things you can do to start live streaming today or tomorrow, or if you ever want to look into it? Gear. You may hear an audio difference between all of the clips that I gave you. Gear is a big piece of it. Just starting with a wired headphones with a mic, like I'm thinking the Apple headphones that used to come on with all the phones. Those are great. Just make sure they're wired. Bluetooth gives it issues. You can hear it in some of those. It's really annoying. Figure out what you want to talk about. Do you want to ask questions? Do you want to deep dive on research, like finding out why elephants can communicate? Elephants might be a big reason I really like Postgres, but also elephants are just really cool, and databases are cool too. Where do you want to stream? There's so many different options. So choose one. Figure out which one you want to choose. Which ones are pros and cons? And share your excitement. Your excitement will get others excited and engaged, and it will just make learning together so much easier. And thank you for joining Lessons Learned While Learning Live. Together, we will break the barriers of getting into tech. And click that like QR code if you would like to connect or see any more of these resources. The deck will be sent out, and I look forward to your questions. Goodbye, everyone.
Thank you so much, Jen. I don't know about you, but I learned so much from her talk. If you have any questions for Jen, find her on spatial.chat on Discord. Before we go to the second speaker, make some noise for our platinum sponsor, Rollbar. Rollbar is the leading continuous code improvement platform that proactively discovers, predicts, and resolves errors with real-time AI-assisted workflows. With Rollbar, developers continuously improve their code and constantly innovate rather than spending time monitoring, investigating, and debugging. I know you'll have questions for the speakers, so address your questions to them on spatial.chat after their talks. You can join spatial.chat directly from the timeline below the player. Click on the object with the speaker's name and see who's having Q&A right now, and you can join from there. Up next is our second speaker, Daniel, and he will be talking on taming language models through TypeScript. Daniel is a language designer and PM on TypeScript. Daniel, take it away.
Hi everyone, my name is Daniel Rosenwasser, and I'm the program manager on the TypeScript team at Microsoft. Today, I want to talk to you about TypeChat, another thing I've been working on recently with others on my team. So, in the last few months, you've probably seen a lot about artificial intelligence and large language models. These language models are very powerful, and you've probably gotten the chance to even use them in the form of something like ChatGPT or a similar sort of chat program where you can ask the model questions, it can give you answers, you can iterate through ideas, and it's just a great way to sort of creatively iterate through concepts and whatnot. That works really well for people, but these language models are very powerful, and you may have had the idea of trying to bring the smarts of one of these language models into your app, maybe to add a natural language interface in some way. So, for an example, let's say we have some sort of app that's supposed to help us plan out, plans for a day, plans for the weekend, maybe specific to a location. It doesn't seem impractical given the fact that these models have been trained on so much data in the world. So they might know a lot about Seattle or some other city that you're trying to scout out ideas for. In this app, maybe we just want to be able to ask a question, right? That's our user intent, and then get a set of results with a couple of venues and each of their descriptions as well. So that seems all good, but how would you go about trying to get one of these language models to produce data that you can use in this app? The thing that you may have realized in trying to do something like this is you end up trying to often pamper the AI to give it in a specific format. And even once it's in that format, it comes up with natural language which is not always going to be easy to parse. So, for example, here's a prompt and response that took a couple of tries to get even reasonable, right? One of the things that you might notice is I end up trying to just give it a little bit of guidance on how I expect the answer to be, right? This isn't so bad, right? But mostly because it's come up with a regular answer in a specific format. And so it's actually given me a format of list items. Each of them is numbered, and then between the venue and the description, I have a colon. Now, is the AI always going to come back with that schema or format? Not necessarily. A lot of these language models are non-deterministic, so you really can't count on this format. But even if you could count on that format, you can't always trust that the data is going to be uniformly parsable, right? So for example, in this case, I have a list and I have everything in this format. What about trying to split the colon, right? You might try to say, let me just try to shave each of the numbers off and then split by the colon. But what if one of the items in your list has a colon inside of the title or something like that, right? You're basically trying to do natural language parsing at this point, right? And now you have a bug, and now you have to figure out how to be resilient against that. And so this ends up being a little bit impractical for most people, right? It is very hard to parse natural language. But many of you probably also realize that you can get the language models to respond in the form of JSON. And that's great, right? Now you actually have something that your app can easily just do a JSON.parse or whatever and get the data that you need and work off of that. But that only really works for sort of simple examples, right? Here I was able to say, here's an example of the JSON that I want to get back, right? I have a venue and a description, a venue and a description, and the AI is pretty good at figuring that out. But it doesn't really tell us about maybe optional properties, maybe the case where you have 3 different kinds of objects that you expect to be in a specific position, things like that. And so just giving examples would be impractical because you'd get into these sort of combinatorial explosions of like all the types of things that you would want to actually provide. So examples aren't enough. What you need is something a little bit more. And it turns out there is a format that does work out pretty well for the most part in our experience. And it's something that you're all familiar with here at this TypeScript conference, which is types, right? TypeScript types are actually a great format for describing the exact format that we want out of a language model and all the sorts of shapes that we're expecting. And so types are actually really good at guiding the language model into the thing that we want, right? And you can actually take the types in an application, like the actual text of the types in your program, take a user intent, and craft a prompt that you can send into an AI service, into a language model. And that will provide you with JSON, right? You'd say, give me a response in the form of JSON. Here's the type that which you should conform to when you provide that response. And so now you're able to guide the language model. But like I said, the language model isn't always going to come back with a response that is actually exactly as we expect, right? So maybe it comes back with JSON, but it's not of the format precisely, right? So we can always say, hey, you didn't give me correct JSON, try again. But you need something else that pushes an AI so that you can say try again as well. And that's the validation. And so actually, once you have the types, you can use the types to validate the response from the language model as well. And so what we actually just decided to do is we said, hey, if we have the types and we have the JSON, it's very trivial to construct a small program where you can get TypeScript itself to check each of the properties and each of the values that have come back, because it's very simple at that point, because JSON is really just roughly a subset of JavaScript, and JavaScript is a subset of TypeScript. And so you can actually create a program, have TypeScript type check it, and if it has an error, you feed that error back into the language model and have the language model try to repair whatever its response was from the last time. That works out pretty dang well. And so you can use this to actually construct even more complex responses, right? So you can actually say, hey, maybe I am a kiosk that takes orders for coffee or something like that, right? And so the orders are effectively in the shape of a cart. A cart has many items. Those items can be one of several different kinds of items. And we give that schema, we give a user intent like, I want 2 lattes, 1 tall and 1 grande. And the language model good language models can typically respond with well-formed JSON that conforms to the type. And it depends on the quality of your model, right? You can have it repair a couple of times, but generally speaking, many of the ones that are available to people today that are broadly available do come back with a good response here. And so I think that this is a good time to give a quick demo of TypeChat, which is this library that we put together to encapsulate all these ideas and make it easy to get running with them. So I'm going to open up the TypeChat repository, right? It's all open source. You can get it today. We announced it about a month ago or so. And so we want to first look at the README for the examples, right? So this is the README at the top level. But to get a sense of TypeChat itself, we want to take a look at the examples. In the examples folder, we have a README with a table that describes each of the examples that we have, and they basically go from easiest to understand to maybe the most difficult. So the sentiment example that we have is kind of like the hello world of TypeChat. It's a classifier which takes a user intent, right? It takes a sentence from the user in a prompt, sends that to a language model, and tries to categorize that sentiment as whether or not the sentence was positive, negative, or neutral. So let's go into that. We have a sentiment schema. And this schema file is what's actually going to be used when we send it over to the language model, right? We're actually going to take the full text of this schema file. But notice that it's just a very simple response, right? It's just an object with a property on it that gets a string that is either the string negative, neutral, or positive. Also, just something to keep in mind is I mentioned we're going to literally send the entire text of the file over to the language model. So that also means that things like comments are also going to be useful for kind of coaxing the language model to give you a response that fits a shape better than just the raw types themselves. So you can also communicate more than just the types. So we're already in the sentiment example. Everything is already built here. So what I'm going to just do is run the example. So this thing creates a prompt, and I'm going to just write hello world. So the language model that we're using right now, which is GPT-3.5 Turbo, is categorizing this sentence as neutral. Every single time I do this, as many times as I put an exclamation mark, it's always neutral for some reason. But if I write something like type chat is pretty cool, that's positive. So let's take a look at what the code looks like to actually construct this. So first off, we have this function called create language model. Create language model actually takes the environment variables that we have in our process, and that's populated by a .env file. So that .env file, I'm not going to show you the full contents, but you can configure things like the model that you want and some other data. Create language model currently is just there to sort of bootstrap you so you can get an easy model that's accessible that loads up either OpenAI models or Azure OpenAI models. Really, a model is a very general concept, and so you can bring any model that you want. You can bring something that's trained locally. You can bring something that is a completely different service. TypeChat is agnostic to all of that. Really, all that we care about is, can you take a string and make a connection through a language model and eventually return either a success or a failure on a string, right? So we just care about, can you give us a string from a string? Anyways, so we create the language model, we infer it from our environment variables, and then we actually load up the schema file, right? This is the actual schema file that we have adjacent to main.ts. Now, there's some subtlety there, and I'll talk about that in a second. But notice that this file right here corresponds exactly to this file right here. And then we create what's called a JSON translator. And this thing is going to take the model, take the schema, and the name of the type that we want our response to conform to. And this is sort of like the entry point in our types file, right? We might have many types in this file. We may have a whole net or graph of types, and we want to make sure that we know the exact one that we're starting off with. And so we're feeding in the name of the type, we're feeding in the actual type that we've loaded up in the program here, and then we have a translator object. And we also have this process requests function, which is really just there to make it easy to create a command line prompt, because Node for some reason makes it somewhat difficult. You give it the prompt that you want to have at every single, the text that you want to print at every single prompt, and then a callback every single time you get a user intent or a sentence, right? So this is every line that gets entered at the prompt. So we run each of the requests through the translator eventually calls the language model responds, and then the translator takes that, uses the types, constructs the program, and internally uses TypeScript to check the program to make sure that it has succeeded, and if it has not, it possibly does some retries and maybe backs off a little bit as well. And so if we're not successful, we just error and just exit. But if we are, what we end up with is well-typed data. So we get our a success of sentiment response, our data is a sentiment response, and then we have that well-typed sentiment. And because TypeScript is type checking this thing, we know that this thing is strongly and static or strictly typed, right? And so that is very easy to get going, right? Altogether, about 22 lines of code. And there is a little bit of subtlety there because in our build, we actually have to do a little bit of extra stuff, right? So if you're using something like TS Node, this isn't a problem, but because we are actually looking for the TS input file, we're actually using the schema file types, we actually just copy them all over into the output directory. And it's a little bit rudimentary, but it works pretty well, right? And so if you don't want to do this, you can always use something like TS Node, and there are probably easy ways of getting this working with something like Deno or Bun or whatever, right? So the sentiment example is pretty easy to get going. We also have another example of a coffee shop. So in our coffee shop, we have a slightly more sophisticated schema. I'll close the other files right here. And so this is similar to what I had in the presentation just a little bit ago. Just bear with me for a second. We have a cart. The cart has items. The items are each of these line items, and then, et cetera, et cetera, et cetera. So we can order Apple brand muffins, blueberry muffins, bagels, whatever. And so I can actually exit this prompt, go up, go into the coffee shop example, and then I could just run this thing. And I could say 1 small latte and a bagel, please. And so if we look at the output here, we actually get well-formed JSON. And for each of the items, we have 1 latte drink, it's a short, and a bagel, right? And the quantity is 1, and the quantity is 1. And, depending on your model, you'll actually end up finding that this often works consistently well, or it can have occasional issues. So, let's just try this one. Give me 1 tall latte and a banana. And so notice that it didn't actually fail here. It actually ended up saying, I didn't understand the following, and it listed that thing out. And that's because of how we formed our schema, right? The interesting thing is that when you create these schemas, it's actually good to give them a degree of uncertainty in a lot of cases, right? In cases where a language model can't quite understand what the user intent was, it's good to have an out. And so the out here, the degree of freedom, whatever you want to call it, that we've added is we have this thing called unknown text. And so whenever the language model doesn't understand the concept, it tends to put things in this unknown text bucket, right? And so what will happen is, as we make our orders, right, this thing works basically the same way. But what we say is, whenever we encounter an unknown type, then we say, I couldn't understand the following, and then we just run through the whole thing and explain, and we elaborate, right? So I can say, I want 1 tall latte and a banana and a gorilla holding the banana. And it's able to translate each of those into an unknown, which is a banana, and a gorilla holding the banana, right? So that works pretty well. Generally speaking, if you feel like a user is going to get something wrong, it's actually pretty good to add these degrees of freedom. So saying something like, I permit unknown text, or maybe a Boolean that said the order was not clear, or something like that, can help with your application, and you can be a little bit more robust, maybe flag specific things down. And one of the key things about something like type chat is, because you get it all in JSON, you can always preview exactly what a user was going to get when they made one of these requests. So that's like maybe the easiest part of type chat to kind of grok. One of the things that we also realized was that people are often trying to do some form of planning or scripting or programs in with AI, right? Maybe you have an application and you have many different tasks, and they can all be run subsequently in sort of this order. And you can use like the basics of type chat, like the type chat approach that I just showed you, to create commands, right? So you can create like objects with a command name and maybe some arguments or properties that follow that could be used as arguments in some way. And it turns out many programs like VS Code and others use a form of performing actions that's similar to this, right? There's a command name and then like some properties that follow. And you can also sequence them too. But one of the problems with this is that, well, you only get a linear sequence with this, right? And you don't have a way of referring back to an earlier argument in some cases. And so what you want to be able to do is also validate one that you're getting the right flow of data, right? That each of these steps actually has the right type of data that it produces that can be used in the next step. But also you want to be able to refer to each of the individual steps prior, because maybe you need to have some intermediate results before you run an action or something like that. And so one question that you might ask is, hey, what if you just generated code and you just took a very similar approach to type chat that you had before, right? All you need is types. And so maybe you say, here's my API, generate a program like this. That works well sometimes, but there are a couple of issues, right? First is we do want type chat to be cross-language over time, right? We do want to be able to bring this to other languages like maybe Python or C# or others. But when you say, I'm going to create explicit code, you need to be able to also say, I want to sandbox this as well. Or maybe I want to be able to have something that like interprets the real code in some way, but then you end up creating a very rich interpreter that really has to interpret a lot of JavaScript as well, or whatever language that you create. And then you end up with a lot of other issues like, okay, well, I have APIs that are async versus sync, so now the AI needs to generate code that knows about that as well. And it actually also turns out that when you have the real language, it tries to draw outside the lines a lot. So if you have JavaScript, it's going to try to take full advantage of the JavaScript that's available to it. That's not always ideal. So what we actually kind of found was you can throw the A off enough by just creating a pseudo language in a sense, right? And you say, actually, just respond in JSON, and the JSON should look like this, and it can piece that together really well enough. And say, hey, there are these meta properties, and each of these properties can refer back, or they specify that I have a function or whatever. And so this is basically a fake language or representation of a language that's just kind of serialized to JSON, and it works well enough. But where do you get the validation from? How do you know that the inputs from write file are actually of the correct type? That trim text creates a string, and that string can be used as the input to the write file call. Well, we can then take the fake representation, the fake program, take that JSON, turn it into a real program, and then use TypeScript to create a program that actually does need to be type checked. And so when we do that type checking, then we can validate whether or not each of the inputs and outputs corresponds accordingly, right? And so now you do have a well-typed program between each step, and you know that the indices correspond correctly. And so that's another part of type chat, is that we have this concept of type chat programs as well. So I can really quickly show that as well, because I'm very short on time at this point. But I'm going to go into the math example. That's not where it is. And then I'm going to run the program as well. And my terminal doesn't work so well with this. But let's look at the math schema. The math schema is really just a set of methods for add, subtract, multiply, divide, negate, and then some identity stuff, and then I don't know how to handle this, right? That degree of freedom that I mentioned before. And in this program, we're actually not using a JSON translator. We're using a program translator. And the key idea here is that it always expects a specific type called API. So I have to export a type called API here. And so what I can do is I can actually just write mathematical expressions, and I can say something like add 1 and 41, right? And so what that does is it actually creates that JSON program before. This is what we construct to actually validate the program. We actually create this thing. And then we have an interpreter that actually runs it. So when you implement this thing, you effectively create an interpreter in the form of like create or handle call, right? And so you have this evaluate JSON program function, and you provided a callback, and then it just takes a function name and the arguments that get provided to it. And there's a lot of metaprogramming stuff that you can do to make sure that this is all well typed. So at the end, jumping back to our math example, I can do sort of sophisticated things. Like I can say, add 1 and 41 and then double it after. And I have like a typo there. And in some cases it will inline this, but in other cases, maybe because of how I've said it, it will create a step. And the step can then be referenced in one of the other steps. So it says add and then it says multiply. And it turns out that the language models that have been trained on both code and prose do pretty well here. So that was our demo. Unfortunately, I'm short on time, but what we really do encourage people to do is check us out on GitHub. We have discussions, we have issues. We're really looking to hear from you. And you can follow us elsewhere on Twitter or Blue Sky or other places as well. So thanks very much for your time. And that's a wrap. Take care.
Thank you, Daniel. It's always so impressive to me to see how people work with TypeScript to resolve some of the issues that they face. Don't forget to address your questions to Daniel on spatial.chat and Discord.
One more reminder, we have the second track with talks in parallel, and after each talk, speakers from Interface track. Check it out. And our next speaker is Mateus. Mateus is a JavaScript developer focused on React ecosystem. He's also a big OSS enthusiast. He believes that Node modules is not a black box, and he dabs into it frequently. That has led him to maintain a few popular repositories like Xstate, Emotion, Changset, Redux Saga, and recently he also started contributing to TypeScript itself. Mateus, the stage is yours.
My name is Mateusz Brzezinski. I work at Stately, where we work on state machines and all the things related to that. I also maintain a couple of popular open source projects like Emotion, Redux Saga, ChangeSets, Xstate, obviously. And I also contribute to TypeScript from time to time. And I'd like to tell you today more about inferring multiple things at once with reverse map types. So let's start with a short recap on what map types really are. So they are sort of like a type level function, and they accept a union of keys. They output an object type, and they are very useful for object type transformation. They are commonly used for transforming object property values, but since TypeScript 4.1, it's also possible to transform object property keys. So in a sense, we just have our X, our N input, and we transform it into our Y with whatever transformation that TypeScript syntax just allows us to. So let's take a look at a short example. We define our input as an object type with two properties, foo and bar, and they both have different types. So we define also our type level function. This one is just identity, and we can see how the syntax looks like for it. We put in square brackets our k, that is like our I in a for loop. So we can use that to look up that property in our type parameter t. and use that value somehow. In here, we just grab the same thing and return it back. Now we can try to call it at type level. And the point is that we should actually get the same thing just back. So we can inspect that, and yes, this is the very same type. Let's perhaps take a look at something slightly more useful in practice. We can define another type level function. This one is promisify, and we do the very similar thing. We iterate over key of t with our k, and just wrap the current k of t with a function that returns a promise of that type. So we reuse our earlier object type and treat that as some kind of RPC object here. Now we can try to use it at runtime. We can chain off a bar method of it, and then we can see that we actually can use it. So it's a promise. And in the callback, we receive our value. And upon inspection, we can see that this bar property is indeed a function that returns a promise of number, and val is being successfully resolved to a number type. So what are reverse map types and how they relate to what we just discussed? So with reverse map types, the situation is just slightly different because we still deal with a transformation from X to Y, but this time it's a little bit reversed because what we know is the transformation itself and the end result, our output, Y. And what we are trying to figure out is what we got as an input to satisfy this transformation into Y. So we try to figure out what's our input, what's our X here. And what is this actually useful for? It's useful for inference. Kenzie Dots asked on Twitter how one can do this sort of thing, and this actually inspired this talk. So let's take a look at this example. So the question here is how he can try to define an object and provide some contextual type to it for like parameter types, add those different keys to resolve to those keys themselves. So in the method A, how we can resolve parameter name to A, and how we can do the same for B, and how we can resolve name there to B. So this can't really be done with satisfies because satisfies doesn't participate in inference, and we can't really like create a candidate for it here. But we can do that with functions. So let's take a look how we can do that here. So let's first define a type level function, satisfy name, to resemble what we had on the previous slide. And this very operation, we iterate over key of t with k and just produce a function that gets k as its name parameter, and it can freely return just anything because the return type is typed as void. Now to actually utilize it, we need to introduce a function. We call it satisfy object name, and we reuse that type level function that we just declared previously. And the tricky part is that now in here, that object literal that we passed the satisfy object name function is kind of our output, and we need like the TypeScript inference engine has to reverse what the input for this could be. So we can see that it can actually do that. Like we can solve Kant's puzzle, and we can like resolve to those keys here for those parameter types. And we can look it up on the satisfy object name function that it indeed successfully inferred some input object that if we'd provided between angle brackets used as an explicit type parameter, we could go from this object to this output that we have seen as an argument passed to the satisfy object name function. Let's continue with a more advanced example of the provide value function. And again, we declare a type level function here. And this time we put k of t at the val property of this whole template of this mapped type. And we also introduce a new property, which is CB, that stands for callback. And we use that same k of t here as in a function. So we should be able to resolve to whatever has been used as the val property. We should be able to use that as the parameter type for this function. And now we can see that it's indeed able to figure out that it should use that specific type of value property for both A and B, the top level keys of this input object. And we can see that in here it was indeed able to zip this whole object into a simpler form to answer again the question of what the input could be to satisfy this whole mapping operation and for this output to be produced here. I've highlighted here those spots here that were used to create this input object. And if we take a look at our template in the mapped type, we'd see that those spots relate exactly to our template, and that TypeScript was able to reverse engineer in a way that input type. Let's continue with another example. This time we declare some, let's say, database entity user that has three properties: name, last, and age. Again, we define our template for our map type, and in here we specify some requirements for this whole transformation at the needs property. Notice that this can be just anything here. We don't really care what that will be. We'll use it in a specific way, but at this point, it's unbound and it could actually resolve to just anything. But whatever we will put at this needs property will be used in the compute property. And this time we pick from the user object key of this k of t, which resolves to our needs property at this very specific position, and we intersect that with key of user. This is a neat trick to filter those properties, because whatever we put in the needs property those should be properties of the user object. So by intersecting those requirements at the needs position with the actual keys of the user, we just create a common set of those two things. So it's like a filtering at the map at the type level. And in here we extend our user entity with the family name extra property. We specify its requirements. We see that we specify that we need the last property, and we try to compute its value, the value of this family name thing. And in here we use the property last of this user object, and this is sound and valid because we specified that as our requirement as the needs position. And we have a different extra property that is full name. This time we specify two requirements. Those are name and last. And we use both in our compute function provided to this thing. We can see that TypeScript was able to resolve to completely different things at different positions here, within the family name property and within the full name property. And at both positions, the user parameter in the compute callback is different, but it still refers to our user input, and it still refers only to our requirements. This is pretty neat. we have yet another example of how we can use that with tuples. So in here, we have bind all function that just grabs a list of different event types. And for each of those events, it tries to provide a specific listener type. So within the first element of this tuple that has type blur, we'd really like for our listener to have the focus event there, because we don't want to deal with the other one that would be a mouse event computed from the click type. We don't really want here to deal with both of those things. We'd like for each listener to be as specific as it can be here. So this is like our goal, and there's a small utility that could be used, for example, with React useEffect, because we could bind a couple of events at once and just return some unbind function that useEffect could later on clean up when the effect gets actually disposed. So let's try to climb up here. We have our bind all definition. This time we have T that extends HTML element. Notice that it's a different type parameter than our reverse map type. And we have types that extends read-only possible event type of key of that T. So we can actually even like bind some constraints to our reverse map types, and we can do some clever things with those. The first argument, the first parameter passed to this function is that T, and then we have just a list of specific like bindings that are computed based on that reverse map type contained in the type parameter. We spread those bindings here to hint TypeScript that we actually want this thing to be inferred as a tuple. Otherwise, it could try to infer it as an array. That's a small thing that we need to be aware of here. This is another example of a small utility, bindAll. It accepts some element type as the first argument, a list of bindings. This is a small utility that could be, for example, used in context of React useEffect, because this is a single call that accepts a list of some pairs, and that whole thing returns a single unbinding function, or it could return such. That could be in turn just passed back to React, and it could invoke that when it's cleaning up the effect, the setup effect. It's pretty neat because it just removes some boilerplate for us at the expense of using this small utility. So let's take a look how it's defined. We have here its declaration. We bind T type parameter that resolves to some HTML element, and now we can use its keys to compute, to like constrain our reverse map type to only possible event types of that specific HTML element. So we won't be able to use event types that are not related to this one. And then we just use those two bound type parameters here. We pass T to the first argument that is our target, and we spread a list of bindings from those types for the listener's parameter position. That little spread just helps TypeScript to actually infer a tuple here, because otherwise it could infer an array. So it's a little hint for TypeScript to do what we want it to. What is a binding here? So we can see here that we have our T that has a read-only. We have bindings here, and that accepts our T type parameter that has a constraint of read-only array of strings. So to iterate over an array or a tuple, we use the very same syntax as we are using for mapping over object properties. So we do exactly that. Here we use k of t as the type property here, and use that k of t within the listener parameter here. And we use that type to somehow retrieve possible event types with the help of an extra type. That's a little bit like outside of this presentation. So let's assume that it just exists. We also have this possible event type that grabs a list of keys of our target and tries to infer possible event types. But remember that from here we'll be returning just some strings like click, blur, input, etc. But the get event helper that I didn't show was supposed to map those strings to actual event types. And we can see that this example is able to resolve at each specific position specific event type. So for the blur event, for the blur type, this is a focus event. Whereas for the click type, this is a mouse event. This is very nice because we were able to just narrow it down as much as possible, so each listener can deal with its own specific event type instead of having to deal with every other type that could appear here within this whole tuple. And what's nice about it is also that autocompletes work pretty nice here. So we can. What's cool about it is that autocompletes work here, and so we can even provide a good developer experience for those things here. And thanks to the possible event type helper there, that was computing the allowed event types. All of them appear here. This is pretty nice because the original signature of Bindall was using like a ton of overloads, I think like up to 10 perhaps. But with those reverse map types applied here, we can just downsize all of it to just a single signature, which is a big readability improvement. For the full implementation of this helper, you can look into this repository, into this bind event listener package. So let's talk now about what I love. So state machines. Let's take a look how we can utilize reverse map types in this context. This is a create machine function that accepts some initial state, a list of those states, like the first state, second state, and the third one. And each of those also have a defined transitions for them. They can accept events to change the current state into another state within this whole configuration object here. And that create machine function can be defined like this one. What's neat here is that we have a mapping of all of those things, of all of those properties. We define our on record that will point to different states, but we also can refer to this whole reverse map type like outside of it. So we can strongly type the initial property that is being used outside of it, and we can verify that it works here. Autocompletes work great, and we successfully were able to constrain this property to only those states that exist in this very configuration. And in the similar manner, transitions here are also bound to only those states that appear in this configuration, and we can select them from the list and all of that jazz. Let's talk about recursion, because it would be really cool to do those things recursively. And it turns out that we can actually do that also using an expanded version of the create machine function. So in here, this is very similar to the previous one. It just defines a hierarchical state machine. That means that within states, we can have more states, and such like a compound state can point to its children with its own initial property. We define a signature for create machine here. As the config, we use a helper state type, and that is very similar to the previous one with a very small just change. In here, we are using state recursively. So as long as k of t appears naked here, we can just pass it recursively to some other types like state here, and it will infer all of those things recursively through layers. So that delivers a very nice DX, because at every level of the state machine, we can bind accepted types to only that level, because at this level, we can only transition to first or second state, but we shouldn't be able, at least not with this syntax, we shouldn't be able to transition to its children. So we shouldn't be able to transition to my child or my other child. So we can see that this specific transition is bound correctly, and those are the only two valid values here, and the autocompletes work nicely. In a similar manner, in the nested transition, only those states, those sibling states, can be used there as transition values. So we can't really transition from here to the top level states first and second, and the autocompletes are also correctly constrained to those valid ones here. There are some fixable limitations to this whole technique, like they can only infer a single thing per object property or tuple element, and there are some work in progress PRs that could address that. Intra-expression inference also don't work within them, or other type parameters that appear within that reverse map type can't be. Sorry, let's pause. There are some fixable limitations to this whole technique, like, for example, they can only infer a single thing per object property or tuple element. So if we'd have more relationships between different spots within our slot, we couldn't really express them, at least not right now. There are some pull requests that are open. Some of them are work in progress things. They might be able to just address those limitations. In a similar manner, in intra-expression inference, just doesn't work with them right now, and there's also work in progress PR for that. And inference sources for other type parameters can't really be used when they appear in those reverse map types, because they are lazily evaluated, and there's also a pull request for that. Thank you. This is my Twitter handle. I'm _Rake on Twitter and _ on GitHub. Give me a follow or convince your company to sponsor my work, because all of those PRs mentioned on the previous slide are actually mine.
Thank you for that amazing talk. Do not forget to address all your questions to Mateo on a special chat and Discord. Do you remember tweeting on how you're watching the stream with your great photos? Because we show us yours, so we want to see yours. Just a reminder that after all the talks, we picked 2 winners randomly who will get multi-passes with access to the batch of JSConf and Git Nation team. Tweet with the hashtag TXCongress. Before we go to the second speaker, make some noise to our gold sponsor, Focus Reactive. Focus Reactive is a Next.js, headless CMS, and e-commerce expert agency. They partnered with Vercel, Shopify, Storyblock, and Sanity.io to deliver quality software with a focus on scalability, performance, and great user experience. And the launch of TypeScript documentation is coming soon, starting at 6 p.m. Central European Time. Time to have a break to get back to you with more energy.
So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions.
And welcome back. Our next speaker is David. David is a full-time open source TypeScript developer and author of ArcType, a one-on-one validator for TypeScript. ArcType is the first validator to include a static parser that can infer TypeScript syntax, as well as full type system that can compare arbitrary pairs of types for assignability and automatically discriminate unions. Make a virtual applause for David.
Hey everyone, my name's David. I'm very lucky to be here today and have the chance to talk to you about one of my absolute favorite topics in the TypeScript ecosystem, of which there are many. But as many of you may know, one of them is perhaps the nearest and dearest to my heart, which is runtime validation. So this is something that's been discussed very frequently by the community in the past and solved many times by some fantastic engineers. So there are some great solutions to this out there. But when I was looking at this problem, I couldn't help but feel there was this gap between the expressiveness and power of TypeScript and its type system and its syntax versus what was available at runtime through some combination of builder methods or various transpilation steps or things like that. So essentially, this was a couple of years ago, I sort of just asked myself this very dangerous question of what is the closest we could get to expressing a TypeScript type like this in a way that we can use at runtime. So remarkably, the answer is pretty simple, and I don't think there's actually as much ambiguity as there is when you're answering most design problems like this. So luckily, TypeScript leveraged a lot of the same structures for its object literals, tuple literals, etc., as are built into JavaScript. So we can do the same thing. We can say name is a string, sure. Okay, so we have to embed this. We got a device, we got a nested object here, platform. So this will be a little tricky because they're already in a string. So probably have to do some kind of nested quotes or something like that. so that we know we're still in a string literal since Android and iOS aren't keywords. And then there's a couple ways you could go about this one, but let's just go with this. So this is the closest I think you could basically get to a one-to-one here. If you compare these two things, you look at this, we don't have an as const here, but essentially these two have a very strong parallel, right? So the question is this structure something that we could theoretically use for runtime validation in a way that captures the essence of what makes TypeScript syntax so powerful and extends that for some of the core needs of a runtime validator? All right, so fast forward, give or take a few months. Basically, what I'm facing here is we need some way to take that original structure that looks just like TypeScript type, but infer back out the original TypeScript type without all that, runtime embedded syntax that's designed to fit within JavaScript. So essentially, after some iteration, I came up with this initial solution. You can see that I called it parse type, which eventually, as you can probably guess, evolved into archetype. It's just a simple process of a couple of years and some iteration. You can see this is the beginning of my iterate on types, type iterate, and it has kind of been a theme since then. But there's a few sort of like intermediate stages, and you'll sort of be able to see a little bit about how some of this evolved. So this was kind of like my initial stab at things. It's got some fairly complex types in it. It's this top-down parser approach, doing a lot of pattern matching and some pretty, I'll say familiar. I mean, this is a little crazy stuff still, but like in terms of what had been done within TypeScript in the past for parsing, it is kind of this like, hey, does this match this template expression? If it does, then infer this part of the syntax. Otherwise, do this other thing, right? So somewhat straightforward, but I would find that it had some kind of inherent limitation. So got some nice error messages. Impressively, one of the first things I added was this kind of like cyclic inference capability. So it's able to do that. So that's cool. I added function parsing for some reason, which is useless for runtime validation. So I think I just thought it was cool or something. So I'm not sure why that was there. But then this precedence issue kind of continued to be a thorn in my side because, I had very little control with this top-down method in terms of, ensuring, for example, that the array operator had higher precedence than the union operator. And that was really the most straightforward manifestation of this issue. As I went on, I would discover others, like trying to represent string literals like this, yes or no. Well, you need to make sure that it's not interpreted as the string literal containing that union operator. So this top-down approach, I'm going to continue to try to work around it for a while, but eventually I'm just going to figure out, it's just not going to work. This case was the specific one that made me realize, okay, there's no way that I'm actually going to be able to use this approach at all if I want a fundamentally scalable solution, both in terms of performance and in terms of capabilities of parsing more complex syntax. Okay, so where do we go from here? How do we solve this problem, this ridiculous type with a union operator and two string literals, and how are we going to do this? Pattern matching is kind of at its limit here in terms of what we're going to get. So where do we go? All right, so back to present day. We're back in our editor. It was that problem that really led me to the first sort of fundamental breakthrough that made archetype possible. It's the idea of a shift-reduce parser. So it's pretty different from the top-down approach that we had before. See if I can find this. And basically what you have is instead of having this top-down approach where we are matching against various expressions across the whole string, this is, there's a lot going on here, but the core of what you really need to understand is that we actually are keeping track of a state that has various branches and has groups and various other data that we need in order to parse a string. And it's just a simple algorithm where we're looping, checking if we have something to operate on. So for example, maybe it's string or number or the literal 5, or we don't, and we need to get something to operate on. So we keep looping like this. If we don't have anything to operate on, we get something to operate on. And if we do, we figure out what's operating on it. So it's actually really straightforward, and it lends itself really well to this problem. TypeScript handles this incredibly efficiently, as we'll get into a little bit in the future. Basically, using this method both allowed me to represent much more complex syntax than I would have otherwise been able to do, but also allowed TypeScript to do it much more efficiently, which was really surprising to me because the logic is not trivial. This is, in my opinion, kind of one of the more beautiful parts of the type level implementation here. So you can kind of look and see this parallel between the runtime implementation of the parser and the static implementation of the parser. And certainly, in this case, I definitely went a little bit out of my way to kind of create that parallel, but it's really kind of demonstrates, in my view, that with some of the right patterns in mind, types can be written that really are quite close to imperative runtime code in terms of their expressiveness, in terms of their capabilities. Of course, eventually you're going to hit the limits of TypeScript's type system a lot faster than you're going to hit the limits of your language in general. But for something like this, it works remarkably well. You can kind of, again, see some of the patterns here where we're checking the remaining part of the string. We're kind of just getting the next token, and then based on that, kind of making some decisions about what to do with the state and how to continue. So again, this is really a remarkably effective way to parse strings in TypeScript. Everyone should totally use this if you're parsing something more than trivial. This is absolutely the way to go. Maintaining the current state, getting the next characters, and it gives you as much flexibility as you need to handle these very complex, potentially, cases where you're maybe having to disambiguate between various operators or things like that, things you'd never be able to do with the top-down approach. So it really can scale as far as you need it to, which was amazing for me to find. I thought that I'd kind of like hit the end of the road in terms of a lot of the utility of the project when I ran into that last problem, thinking that this kind of implementation would just be out of reach in terms of performance for the compiler and everything. But to the contrary, it's actually much more efficient. And this was the breakthrough that I had where I was like, wow, okay, this, really has a lot of potential. Like, if I can parse arbitrary syntax and it's really performant to do that, and then I can infer that one-to-one as types, who really knows where this thing could go? Like this could feel amazing to author our types for runtime, get, live validation and everything. So I was really, really excited. So if you're a grizzled veteran of the TypeScript ecosystem and see a type that looks like this one, my guess would be probably have some alarm bells go off in your head, because despite my enthusiasm, your experience might be that when libraries have types like this, it's very frequent that they will, for example, crash your TypeScript server. That's maybe the most frequent reaction I get when someone sees archetype for the first time by a factor of 3 or 4. But rest assured, the problem itself kind of necessitated we come up with some better solutions for type level testing, including performance testing. So we built a framework called Attest that can benchmark at a type level the number of instantiations contributed by any expression. So you can see that we have this very granular metric for every type of expression in archetype. We can ensure that it's inferred performantly and accurately, even for very complex types like this one. We know that it's going to do exactly what you expect, and it's going to do it very quickly, so you don't notice any delay whatsoever. And in terms of functional assertions, for example, we could check out our divisibility tests over here. A little bit more space. You can see that the types of assertions we're making here at a type level. We have all sorts of syntactic errors, semantic errors. At this point, the capabilities of the type level parser are really, really advanced and essentially on par with the kind of like native IDE editing experience. So for example, let's say I want to define some type, say it's a number. Of course, you get autocomplete for everything in your scope, including all the keywords, and then maybe it's divisible by 2. Okay, it's not going to affect the inference. It's a runtime constraint. But if I were to write, you see we're missing an operand there. 0, you get a specific error for that. Let's say I try to divide by unknown. Essentially we can narrow down exactly what the problem is whenever anything goes wrong like this. So the idea of strings not being type safe, that's also out the window. Again, this is really on par with the native IDE experience just from within TypeScript's type system. So that's a really, really exciting point to be at with all of this. And I've just been so excited to share with you all for so long. But even with all of this implemented, there was one thing that was nagging at me as I was getting ready to release this quite a while ago. And it was just something about the way the types compose together and reduce together that didn't feel quite right. I couldn't put my finger on it because I hadn't really worked much with type systems in the past. But what I eventually figured out, what I was missing and what I wanted, was the ability to compare arbitrary types together, the ability to reduce intersections and unions as completely as possible, to go beyond shallow validation capabilities and truly have a runtime type system. And you can see some of that after very significant iteration has finally come to fruition here, where in addition to the kind of standard constraints that TypeScript covers, it treats runtime constraints like divisors, ranges, regex, etc., with the same rigor that you treat comparisons between numbers and strings and objects and things like that. It's all integrated together into a single type-safe system that you can use, for example, to do more than just define your validators. You can compare them to one another. So you could say, does this numeric type extend some other numeric type that maybe is an integer that's divisible only by 1? And it will, because it's more specific than that. So it's essentially a full type system as well at this point, on top of all the validation capabilities. And really, this was an amazing problem to work on. It gave me a much deeper understanding of the kind of work that the TypeScript team does. And really, there's just a lot of beauty in having a chance to work with these kinds of types in general to find the simplest possible representation that allows types to be composed together, compared against one another, and reduced fully was really such an amazing problem to work on. And it led to a lot of really significant new capabilities within validation as well. By having this type information, for example, we can do things like discriminate unions automatically. So, for example, in archetype, you can just define a union like this directly. And essentially, we will, within our type system, identify the optimal discriminant or set of discriminants in case it requires multiple checks to figure out which branch you're on, and will implicitly optimize the actual runtime validation process around leveraging those checks so that most unions are, without you even having to think about it, going to be checked in constant time, whereas other existing validators without that type system information are either just going to be checking it linearly, or they're going to require you to opt in and manually specify it through syntax like this. Zod, I think, actually specifically recently was having some issues maintaining their discriminated union types. And even defining it explicitly, it's really expensive at a type level. You can see there's a massive disparity of about 20 times fewer instantiations for the union here. And of course, it's just a much more straightforward type to define and read as well. You mouse over it, you see exactly what the union is, versus we go here. And I don't use Zod constantly, but it's a lot harder to tell what's going on exactly without being able to, see many of the parameters. And maybe you have to pull it out with Zod.infer. But there are some pretty significant disparities, and largely those come out of the two major areas we discussed: the ability to use the runtime type system to optimize the validation process, so we don't need to rely on user-provided information like this, as well as the optimizations in TypeScript's type system to ensure that this can be parsed much more efficiently. So in terms of runtime performance in general, Archetype's been very heavily optimized, and for the sort of base case, checking simple props on an object is going to be basically identical to some of the top runtime validators performance-wise that are out there, like Tipia and Typebox. But where it really shines is these cases where it can leverage its deep type system knowledge, for example, to implicitly discriminate a large union. It could very easily, result in, speeds of 20 or 30 times faster than even those most performant validators in cases where, again, it can, through multiple steps, identify which checks it needs to make sequentially in order to determine which branch of a union it's on, and often will be able to check that union in constant time without you having to even think about it. Whereas, again, the alternatives are sort of generally to not have that option at all, or to have to build in that logic manually and maintain it as your type changes. And as a point of reference, those base cases that we're talking about for existing performant validators are already about 400 times faster than Zod for these kinds of scenarios. So certainly, if you need to optimize around performance, there's going to be some really big gains to be had in that area as well. So I know we're sort of running out of time here. I just wanted to demo a couple of my favorite features from the upcoming release, which hopefully, I guess, is the current release now that you're seeing this video. It's been hard, getting to this point. There were so many things that I wanted to cover. And the scope definitely grew quite a bit beyond what I had anticipated in terms of the improvements for beta. But hopefully, if you're seeing this and I was able to wrap everything up the way that I intended, you can try all these things out now. But regardless, I wanted to show off some of these generic inference capabilities, which I feel are very cool. So there's a new feature in beta that you can define these generic types. You can define a signature like this and then reference a type parameter and then instantiate it later on. And you just get this one-to-one inference. Again, it's just like TypeScript, and then will work for runtime validation as well. You can define them within a scope, which is essentially a way to bind keywords, your own custom keywords, to whatever types that you want. So this one is probably the most kind of like mind-blowing type within TypeScript's type system that's in here. So you can see we've got this like alternate generic that takes A and B, and it calls itself, and then swaps A and B. So it's just a classic like TypeScript recursive generic, but this can actually be inferred within archetype. And you can see that, in fact, you get these alternating inputs. If we instantiate it later, we pass in off or on. Instead of 0 or 1, you get the expected result, and those two are sort of toggling back and forth. So the fact that all this ends up actually being possible within TypeScript was really incredible for me to discover. Again, props to the TypeScript team for creating such an amazing parser, an amazing tool that would support, probably unintentionally, this kind of level of depth just within, its own type system. I think is incredible. So the last feature that I just wanted to show off quickly, which actually does exist in alpha, but because it's a really major part of what archetype does, in addition to scopes, which I barely had a chance to go over, but unfortunately, it's just 20 minutes is a very short amount of time and there's so much here. But of course, I'm so excited to follow up with you all. Morphs are how archetype handles transformations. What's really unique about them is they're actually built into the type system. So instead of just at a high level, shallowly kind of marking everything as an effect where it can't be combined with types anymore, they're handled granularly so that only at the particular property where this transformation occurs is it considered a morph and can't be combined with another morph. But in general, it just avoids the function coloring problem where more broadly the type can still be used as a type, intersect with other types, union with other types, etc., etc. And you get this really nice visual representation of exactly what kinds of transformations are going to occur. So I think that's a really nice feature as well, and I hope you guys enjoy it. So just to wrap up at this point, I guess we're kind of like bringing it back to the start here. We've got this structure, and maybe we'll even just try importing directly and see what we get, and hopefully we'll get a good result. So let's see if I can just do it from the package name itself here. And if we just wrap this, and it's nice that it applies the highlighting as well from the extension. But there you go. It's exactly what we anticipated, exactly like the original type. And really, I have to say that the developer experience for this is pretty mind-boggling compared to stuff that's out there. I feel like just getting this immediate autocomplete. Again, even within expressions, you'll get these full completions that work. You get immediately these very responsive errors if there's any problems with the expression that's being parsed. It really is an amazing experience that absolutely is on par and often even feels better than natively editing these kinds of types in your IDE. So I'm so excited to share this with you all. It really has been a journey to get here, as maybe you've inferred from the talk. But I really look forward to following up. Hopefully you guys have some questions for me. And we can talk more about that during the Q&A and in the future. So thanks so much for taking the time to listen to my talk. Again, I really do appreciate it. I appreciate all the love and support I've had from the community. It's allowed me to get to this point because it has been a lot, but it's also been one of the most amazing things I've ever been lucky enough to do. So thanks so much, and I hope to be answering your questions soon.
Thank you. That was a great talk. Do not forget to address all your questions to David on the Spatial Chat and Discord. He will be very happy to answer all of them. Do not forget to address your questions to the speaker on the Spatial Chat after their talks. You can join the Spatial Chat directly from the timeline below the player. Click on the object with the speaker's name who is having a Q&A now and join the platform.
A quick reminder about tomorrow's activities. Join the discussions on spatial.chat around topics such as TypeScript Future Spotlight, contributing to TypeScript, ecosystem tooling, and TypeScript shenanigans with our wonderful speakers. Attendees with full access to the conference activities will receive an email with the details on how to join the rooms. Up next is our speaker, Tishan, and his talk is on how to make our CLI safer with types. Tishan is a developer in the JavaScript infrastructure team at Bloomberg, where he works on JavaScript and TypeScript tooling for internal developers. You may have recognized his name because he's sort of Stack Overflow famous. On Stack Overflow, he is currently the number 3 answerer for the TypeScript tag. Tishan, now on to you.
Hello everyone, welcome to my talk, Speeding Up TypeScript Builds. My name is Tizian Cenicoa Dragomir. I'm a software engineer in Bloomberg in the TypeScript JavaScript infrastructure team, and I'm also a TypeScript compiler contributor. And today I want to talk about build performance, especially build performance in monorepos. And we're going to talk about an upcoming feature of TypeScript that we've been developing in collaboration with Bloomberg, Google, and Microsoft. You can check out this feature on our public GitHub repo on our fork of TypeScript, but we're going to talk about it today as well. So what is the motivation for this feature? Well, if you spend any amount of time on Twitter, you will definitely find people that complain about build time performance in TypeScript. And these complaints are not unwarranted. Unfortunately, type checking can be slow, especially if you have a lot of code in a lot of projects in a monorepo. So the question is, what can we do about it? Well, we could optimize the compiler, and the TypeScript team have definitely been doing that. If you check the release notes for the last several versions, you will see that every version brings new optimizations to the compiler, and that is all great work. We could also rewrite the compiler, and there's efforts out there that are trying to do this. We're excited to see where those go as well. But we tried a different approach. We thought about running things in parallel, because a lot of hardware today is multi-core. People have a lot of cores on their desktops and their laptops. And it would be great if we could take advantage of those to actually make things faster for people when they build their projects. So let's run the compiler in parallel. Let's see what performance gains we could get. What we did inside Bloomberg, we took one of our own monorepos. It was a 23 project monorepo. It has over 100,000 lines of TypeScript code and a very deep dependency graph. So you can think something like this, lots of projects with lots of dependencies. And we tried to see what gains we could get from running the type checker in parallel for this monorepo. We took an initial baseline using TypeScript's built-in composite project support, and we got build times from about 60 seconds to 30, depending on hardware. Now, TypeScript -B, which is the composite project support in TypeScript, is actually single-threaded. It will not try to build anything in parallel, so all of these projects are type-checked individually in order of their dependencies. So let's see what we could do if we try to run the compiler in parallel. What we did was we ran a separate instance of the compiler for each project. Now we didn't do this in a naive way. There were some optimizations that we did do. For example, we batched all of the projects into several workers, and each one of these workers had a shared file cache and a shared source file syntax tree cache, which are already optimizations that TypeScript does for its composite project support anyway, so we were just trying to emulate that. Now, the problem we immediately ran into is that projects are not independent, so we can't just run everything in parallel. We need to actually wait for dependencies to finish building. So, for example, for the diagram I showed before of dependencies, we would get an execution that looks something like this, and we can already see that we have a great limit on parallelism, and there's only 2 projects that run in parallel at the same time. So only 2 projects get type checked in parallel. And even in our sample monorepo with 23 projects, we would only get about 4 to build in parallel. Now, what does this actually mean? So, for example, on a laptop with 12 cores, which is what we see here in this picture, we only use some of that computing power. We can see that even while the build runs, there's a lot of CPU power that is still being left unutilized. A lot of CPU cores that are just sitting there idle. So that's definitely not a great start for running things in parallel. Let's see sometimes what kind of improvements could we get if we did this. And the answer is that we definitely will get improvements, but they're just not that great. I mean, there's about a 10-20% improvement that we get from running things in parallel using this approach, which again is better than what we had, but it's not something that is going to be dramatic. So how can we increase the parallelism available? How can we run more things in parallel? Well, for that, we first of all need to understand exactly what it is TypeScript actually does. And what it does is 3 things. It does type checking, it does declaration emit, and it does JavaScript emit. Now, these things are not perfectly independent. Namely, declaration emit depends on the result of type checking. But for each one of our projects, TypeScript will do all of these 3 things. So inside the build for each of projects, all of these 3 things have to happen. Now, there is one key insight here. Namely, that what is needed to unblock a project from starting its type checking phase is that it needs to have available all of the declarations for its dependencies. So declaration emit is what is actually needed for the dependencies. We don't really care if the dependency has finished type checking if we can get its declarations. So the actual dependency tree would look more like this, right? Each type checking phase depends on the declaration emit of its dependencies, not necessarily the type checking. That's an interesting insight, but as long as we still have this dependency between type checking and declaration emit, the fact that this is the case, the fact that we depend on the declaration emit doesn't really help us because we need to do the type checking anyway. So, could we remove this dependency? Well, for that, we should first of all look at why JavaScript emit is so independent from type checking. How is that? And we actually even have tools that do JavaScript emit without the need for a type checker. They do it completely independently of TypeScript. How is this enabled? Well, a few years back, TypeScript added a new mode to TypeScript called isolated modules. So what exactly does isolated modules do? Well, it ensures that each file can be transpiled from TypeScript to JavaScript individually. It basically removes any dependency on type checking from JavaScript emit. So this means that JavaScript emit becomes a purely syntactic process. Tools still need to understand TypeScript syntax. So every time we get new syntax in TypeScript, all tools that do JavaScript emit need to understand this new syntax. But the advantage is that they don't actually need to understand all the semantic rules of TypeScript. They just need to understand the syntax enough to be able to remove it. So basically, when we do JavaScript emit, we start out with a TypeScript file, and what happens inside a JavaScript emitter is that all the type annotations are removed. Right, and this is a very simple process. It's not hard to build such a transformation. At least it's not hard compared to actually building a full type checker. So could we use a similar approach to cut this dependency between the declaration emit and type checking? And for that, we have to look a little bit at what exactly declaration emit entails. So for the most part, it's also a subtractive process where we just cut things from the TypeScript file, except we're not cutting the types anymore. We're cutting the implementation. We're cutting for example, the initializer here. We're cutting the function body. We're cutting the constructor body. So all of these just go away in declaration files. However, there is one exception. Namely, in this case, the return type of this function. Because if the developer did not specify the return type, then the declaration emit needs to reach into the type checker and find out what the return type of this function will be. And this is why type checking is required for declaration emit. If everybody were to write all types in their TypeScript file, then we wouldn't actually need the type checker for declaration emit. So this is one way where we could cut the dependency if we specify all types, and this would allow us to unblock dependencies sooner. So there are already lint rules out there that could enforce this, but it would definitely be used to have something built into the actual compiler that would be a guarantee for other tools as to what annotations are necessary. So we decided to add a new flag to TypeScript that we called isolated declarations. So isolated declaration is the new feature that we are implementing, and let's have a look at what this feature would mean. So our first idea was that we should add type annotations to all values that make it into declaration files. Now, this mostly means exported values, although there are some indirect ways that values can make it into declaration files as well, even if they're not explicitly exported. Now, we did make some exceptions. In some cases, values can be trivially inferred, and maybe we can allow those without having explicit type annotations. But what is for certain is that the type checker itself cannot be involved in declaration emit, because we want declaration emit to be purely a syntactic transformation where we're just cutting out implementation, and we don't have to reach into the type checker to ask about type information from the source code. So the next logical question is, okay, do I have to type annotate everything? I mean, I want to point out that you don't have to do anything unless you opt into it. If you're happy with your TypeScript builds, if you're happy with the way TypeScript was and with your build times, you can keep your project as is. Nobody's forcing you to adopt this. If your dependencies adopt this, you won't really care because you're only consuming their declaration file, so it won't really be something that everybody has to opt into. So our initial thinking, however, was that yes, we will need to specify type annotations on everything. Turns out this makes converting large projects a pain, and it's not the best developer experience, especially since looking at some of these expressions, you could figure out very easily that yes, indeed, the type of something is a number. So we went through 3 phases, basically. The first one was where we thought that no, we wouldn't do any inference in this mode. The second one was where we thought that maybe some trivial inference is okay. And the last one, which ultimately we rejected, was where we do a lot more inference, but we also ran into some problems we're going to see in a few slides. So let's see what our code would look like with each one of these versions. So no inference. What this would mean is that you would have to specify types on absolutely everything. For example, you're assigning 20 to the variable margin. It's pretty obvious that the type should be number here, but we don't allow any annotations, so you would have to specify it. You would have to specify it for this constant, basically duplicating the literal in both places, both in the type position and in the initializer. It gets even worse for things like object literals, where you have to duplicate the property names and the values, and it really becomes very painful to do so. For constants that are initialized with a function, well, you would have to copy the parameter list again to the type annotation and also specify the return type. And again, for fields, even if you're initializing it with very basic values that should be obvious what type they are, we would still need to specify the type explicitly. So again, this would have been quite painful and would have made it very difficult for anybody to actually adopt this feature. So we decided to make our declaration emit a bit smarter. So if we would see a number literal, well, the type there is pretty obviously number, so you don't need to specify that. Same for literal types. For object types, it's a bit more complicated, but it's not impossible to deduce the type from the initializer. So we decided that we can support this as well. For functions for constants that are initialized with a function, well, you don't need to specify the whole function signature as a type annotation, we can just extract most of the information we need from the parameter list. You will, however, need to specify the return type because we don't want to have to go into the function body itself and look for any returns and try to synthesize a return type based on that. And for and for class fields, again, you can just omit them if the initializer is clear enough for us to infer a type from. What about if we want more? Right? We were very excited by our initial success with this trivial form of inference, and we decided, well, maybe we can do more. Maybe we can infer more things. And the problem is that TypeScript's declaration emitter is very smart, and we want to keep our emitters dumb and hopefully fast. So we don't want the declaration emitter, for example, to have to look up information in other files. So let's take an example. Let's say we have a variable and we're initializing it with a value of another variable. Could we trivially infer a type for orientation? What type could we write to declaration files without having to involve the type checker? So we could try using type of horizontal. This seems like a very good fit, right? Type of will give us the type of the variable, and orientation should have the same type as what we're assigning, right? Well, that sometimes works. For example, if horizontal is defined as a variable of type string, then yes, the type of horizontal will be the same as the type of orientation because they will both be strings, and everything would work out great. However, if horizontal is a constant, then what we actually get for horizontal is the literal type horizontal. So what happens when you assign that variable to a mutable variable is that TypeScript will actually widen the type. So orientation will have type string. So in this case, the type of the variable horizontal is going to be different than the type of the variable orientation, because we will have basically string on one side and horizontal on the other side. So it doesn't work for all cases. So the answer is, can we do more inference? The answer to that is yes, but we will probably not always be right. So declarations would have to be optimistically emitted. This basically causes some problems, though, because what we're saying here is that, okay, a declaration emitter could produce declarations all without the type checker, but they could be wrong. And then TypeScript itself could come back and error out looking at all of the information in the type system and say, okay, well, in this particular case, if you're using isolated declarations and you're using a standalone declaration emitter, it could not possibly have known what the correct type is there. So this is possible, but it kind of creates a very complicated mental model, makes it very difficult to understand. Also, the errors would become much harder to understand because we would need to tell people why exactly they're erroring on a certain construct. And what we ended up was errors that sounded something like, this type that is inferred in isolated declarations is different from this other type that would be inferred by TypeScript normally. And it kind of sounds like the compiler is having an argument with itself. Isolated declaration says one thing, regular TSC says another thing, and the developer is involved basically nowhere in this process. So all of this might result in actually degrading the developer experience instead of improving it, which was the reason why we wanted more inference in the first place. So definitely adding more inferences that might not always be right is not the best way to go. So we still wanted to make sure that people would have an easier time adopting this feature. How could we ensure that? Well, we decided to add a quick fix. The information is already present in there. We just need to insert the type inside our code. Visual Studio Code already has all the information. The language service that is running in there already knows what the types of all the variables are, even if they're not spelled out. So what we could do if there's an isolated declaration emit error, we could just use a quick fix to actually insert the type without having to write it ourselves, which I think is something that will definitely help a lot of developers adopt this feature. And I want to send a special thanks to Hannah Ju from Google, which worked extensively on this feature, and most of it is her doing. So how would isolated declarations improve TypeScript? Well, we hope to improve it in several ways with this feature. First of all, we hope to improve speed. Bypassing the type checker to synthesize new types will probably improve declaration emit speed all on itself. We hope to unlock a lot more parallelism if we can emit declarations up front. Projects don't need to wait for the type checking phase of all of their dependencies to finish. They already have the declarations. They can just do their own type checking with that. We also hope to improve compatibility with other tools. Like I said, there are already tools out there that generate JavaScript from TypeScript. We're hoping to create a similar ecosystem of tools that could emit declaration files without the use of the type checker, but that would be 100% compatible with current TypeScript declarations. And we also hope that we will improve transparency. Developers sometimes forget to write types for their exported values, and sometimes the type checker synthesizes some things that are not particular developer friendly. There are either very large types or types without any semantic meaning, resulting in a bad developer experience for the clients of those libraries. So if people are forced to actually write these types in code, they'll probably think more about them, and the declarations will probably have a better quality just because of this. But coming back to our experiment of running the build for a monorepo in parallel, we saw that without isolated declarations, there was a limited amount of parallelism. With isolated declarations, we hope to increase the amount of available parallelism. We saw that in the other version, this was pretty limited. At most, 2 projects could type check in parallel in this example. So what we want to do is we want to front load all of the declaration emit so we can unblock all projects as quickly as possible. So we want to go from this diagram to basically this diagram. And hopefully the difference between these two is that time we will not need to wait for TypeScript anymore, because type checking will be done much faster if we can do all of this in parallel. And this was the hope, right? And without actual numbers, theoretically this might work, but we didn't actually know what kind of performance gains we were looking at in real life projects. So what we did is we actually converted our sample monorepo to use isolated declarations. And we tried to see what kind of performance gain we would get from trying the build in parallel with this new approach, with front loading all of the declaration emit. So drum roll, let's look at the times. As you can see, even just by looking at the numbers, there's a great improvement there. We get even single digit build times. Looking at a chart maybe makes it more clear. The improvement in performance is quite dramatic. We're talking about 3 times improvement in performance. So when we saw these numbers, we were really happy that our theory sort of panned out, and our expectations were actually met and even exceeded by some measures. So what does the future hold? Well, hopefully we're going to get this feature in TypeScript soon. We don't know exactly when, but hopefully it will happen within the next half a year. The other question I usually get when I tell people about this feature is, can this help in a single project setup? We're not sure about this yet. We have done some experimentation, but there are some limitations that still need to be solved in the TypeScript compiler first. We will see if we can help with that as well. Can this get even faster? We used the TypeScript compiler backbone to actually implement our own declaration emitter. There is space there for other tools to be a lot faster, just as there's an ecosystem of JavaScript emitters. Hopefully there will be an ecosystem of TypeScript declaration emitters, and hopefully that will make things even faster. I'd like to say a warm thank you to everyone who was involved, from Google, Hannah Ju and Jan Kuhle, from Microsoft, Daniel Rosenwasser, Jake Bailey and Ryan Kavanaugh, and from Bloomberg, Rob Palmer, Thomas Chetwin and Ashley Claymore. Also a special shout out to the Flow team, who implemented a very similar feature a while back, and which was definitely a source of inspiration for us. Thank you very much for listening, and I'm ready for any questions in the chat. Thank you.
Thank you so much. If you have a chance, also check out his talk at TypeScript Berlin and the workshop that he has on YouTube. Address your questions to Tishen on Spatial.chat and Discord. Discord server is kind of where the party is at, so be sure to find the link on the timeline and the org email. Do not miss any announcements, as well as to spend the time to hang out with the speakers and other attendees. Now we have our next speaker, Maria. Maria is going to talk about how TypeScript is integrated in your editor. She is a software engineer at Microsoft on the TypeScript team, and she mainly focuses on its language support in Visual Studio, but she also works on a JavaScript project system and the integration of other language servers into the IDE. When she's not debugging mysterious code she didn't write, she also likes to give her 2 cents to open source. Please welcome Maria.
Hello everyone, and thank you for joining me today. I'm Maria Solano, and I'm a software engineer at Microsoft. Quickly introducing myself, I focus on TypeScript editor tooling, but sometimes I also dive into LSP extensibility, Visual Studio's JavaScript project system, or I just stare at the TypeScript checker for a couple of hours, trying to absorb its wisdom, as I'm sure all of you have done. Today we'll explore how TypeScript is integrated into your editor, and who does what, and when. For these, we'll use TypeScript's inline variable refactor as an example, which is my favorite, mainly because I implemented it. Say that you have this print greeting function, and your cursor is in the first line of its body. In an editor like VS Code, you'll see a light bulb. Where is that light bulb coming from? Spoiler alert, if you click on it, a list appears. Who constructs a list, and how are items inserted into that list? Not only VS Code has this functionality, Visual Studio, NeoVim, Emacs, Sed, and other obscure editors also have a TypeScript lightbulb experience that doesn't differ much from the one in VS Code. How is that done? As a side note, during this talk I'll be using code action and refactoring as synonyms, despite that they're not exactly the same. Although the difference is a technicality, I'll explain it anyway just so that you can win your next code editor trivia game. A code action is tied to a diagnostic, and hence represents something that you can do to potentially fix those errors. Refactorings, on the other hand, aren't corrections. They're just smart recommendations for writing cleaner or nicer code, but it doesn't mean that there's something wrong with what you wrote. Going back to print greeting, the first thing that happens is that the editor will recognize a trigger event. This can be a passive action, such as your cursor being placed in a position where a refactoring could be applied. The trigger could also be explicit, such as one that you configure with a key binding. Note that results could differ based on the trigger kind. Having a constant light bulb popping up everywhere in your screen could be annoying, and so TypeScript might decide to show you certain refactorings only if you really want to see them. In this example, TypeScript will show a light bulb besides the identifier of a variable that could be inlined, but you'll need to explicitly request the refactor in references of such variables. Now say that we are NoVim gurus and use the mouse to click on the light bulb. The editor doesn't actually know which refactorings to display here. It needs someone who can understand the code. To communicate with that someone, the editor will record the position as well as the content type. Note that the content type isn't exactly a one-to-one mapping with the type coming from the file extension. A TypeScript snippet inside a script block of an HTML file is also assigned to the TypeScript content type. This is how you can still get code action, completions, and the correct syntax highlighting in embedded code. An extension announces that it can handle the code action request. There are different mechanisms to do so. In VS Code, you would register a code action provider for the TypeScript content type. In Visual Studio, you could use Roslyn APIs or the Language Service Protocol. Most of the time, this basically involves registering a callback and telling the editor when to invoke it. Note that this isn't limited to language servers. Extensions like ESLint can also hook up into the code action list to enhance the fixes provided by the language server. This also means that there can be multiple code action providers coming from different extensions. The editor will then combine all of the results into a single list. But okay, I'll back off now because I already mentioned the TypeScript server before properly introducing it. As the name suggests, TS Server is the JavaScript and TypeScript language server, an executable which encapsulates the language compiler together with other features that are represented with a JSON protocol. This protocol defines a set of commands which represent each message you can send to TS Server, together with the request and response format. This is how different editors can provide the same TypeScript experience. They're all just following the same protocol. For example, when sending a completion request with a completion request payload, you'll get a completions response back. When I first joined this team, I remember being confused with the difference between TS Server and the TypeScript compiler. TSC can indeed show you TypeScript errors, but these are only the ones that prevented successful TypeScript compilation. Other features revolve around the editing experience. Think of how it doesn't make sense to figure out refactors if you're just transpiling to JavaScript code. Returning to the event handling, remember that the editor just had the position and file information, and so first it needs to translate that into something that TS Server understands. Here I show a simplified snippet of what the TypeScript VS Code extension does, but Visual Studio has a basically identical C# implementation of the same logic. About that first line of the arguments, that's because VS Code uses 0 based lines and columns, but TypeScript requires 1 based positions for these. You can imagine the off-by-1 errors we've had because of that. You might also wonder, where is that client variable coming from? In this context, we use client and editor interchangeably. Since TypeScript is the server, the client is whatever is sending messages on the other side. TS Server is listening on the other side, and the state and delegation of this communication is mostly encapsulated in session.ts. In this file, there's a handler for each command defined in the protocol, delegating to each language service and performing some processing of the arguments and responses before putting them back on the wire. Here we also keep track of the TypeScript project, which is defined by your tsconfig.json file or by performing some discovery heuristics in the case that you have a set of TypeScript files in a random folder. It's up to this layer to pick up the results from one project or combine them across multiple ones. Moving on to the session handler of interest, we arrive to the getApplicableRefactors function. Here we extract each argument, get the project, and then delegate to the assigned service for that request. Notice the getPreferences call. Since refactorings can change your code, we try to ensure that the applied modifications have the indentation, quote type, and other style needs that you have configured. Each refactoring has its own handler, and the one for inline variable does something like this. Given the arguments from the requests, it will ask the type checker for the respective TypeScript node. And by the way, if you want to learn more about TypeScript's inner workings, you might have fun looking at that 50,000 line long beast. It then performs a bunch of checks to make sure that such a node corresponds to a variable initialized to a value. It also tries to ensure that your code doesn't break when applying the refactor, and so we check that you're not exporting the variable, among other obscure verifications that my more knowledgeable peers told me to consider. After that, we piggyback on find all references to find all the references we would need to modify. Next, we ensure that all references locations could correctly handle the value replacement. And if any of these checks fail, we just return undefined to indicate that the refactor cannot be applied here. The response is then sent back to the editor, which performs an analogous translation to add those refactorings to the lightbulb list. And fantastic! The editor now unfolded the code action list and showed the user how they could improve their code. They picked the best action ever of inline variable, and we send another request to TS server. At this point, you might be wondering, why do we need to talk to TS server again? This is because code actions are an example of a TS server command that happens in 2 stages. In get applicable refactors, we just notified the editors which refactors could be applied, but we didn't tell it how. This is because we don't want to compute all the necessary file modifications for refactorings if you won't even click on them. Only when the refactoring is actually selected, the editor will ask TS server to apply the chosen item. Refactorings might seem special here, but there are other operations with 2 steps that you've used a lot already. Completions are another example. You might have a completion item with an exported object from another file. If selected, not only the completed line will be modified, TypeScript will also update your imports to make sure that the new reference is valid. You know the drill. The editor registers a selection, which later the TypeScript client will map back to the refactor it received in the previous request. From that, it constructs the command's arguments following the TypeScript protocol. And when it receives the result, it will return the workspace edits, which include file modifications, additions, and removals that the refactor implies. Let's go back to the handler for this refactor. When asked to apply the action, it will again ask the compiler for the node that's being inline, the references to it, as well as the expression we'll replace the variable with. It then updates all the references to use the value instead of the variable identifier. And finally, it gets rid of the now unused variable. And ta-da! After the editor reads and translates the response, the refactor is finally applied. Now that you're TS server experts, impress editor and TypeScript maintainers the next time you encounter a bug and create a GitHub issue. Say that when applying the code action, the modified line is off by 1. Without further context, I would dare to say that this is a language server bug, since at the end of the day, the editor is blindly applying the change that the server told it to do. Also, if it's a server bug, you would be able to reproduce the issue in another editor, so you can also try that. As another scenario, say that when clicking on the light bulb, the displayed list has duplicate items. This is a bit harder to say, but from my experience, I would guess that this is an editor bug, since it is the one responsible for querying the code action providers, combining the results, and displaying them in the UI. As a funny story, one of the first bugs that I fixed at Microsoft was duplicate completion entries in Visual Studio. It was both a fascinating but slightly traumatizing experience. If you really want to look like a professional, you can even take a look at the TS server logs, or by setting TypeScript trace level to verbose in VS Code to see what exactly the server is receiving and returning. That will help pinpoint where things go downhill. Now that we went over how the TypeScript protocol works, you might ask if it was always designed like this. The answer is a bit vague, because TS Server kind of always existed, despite not being formally specified. In the early days, TS Server ran in process in Visual Studio. And yes, I mean the IDE and not VS Code, because VS Code didn't even exist back then. Later on, TS Server was moved to its own node process as an effort to improve the performance of the IDE. Fortunately, that transition was smooth, because with the existing JSON protocol, going to an inter-process communication had basically no impact. From the snippets we just looked at, you might feel like translating the arguments and response might be annoying or even redundant. However, this allows the same server to communicate with anyone that follows the TypeScript protocol. The language the client is implemented in doesn't matter, neither does the UI used to interact with the user. TS Server can just care about TypeScript stuff, and the editor about everything else. Thanks to this design, we can have a TypeScript client in VS Code, a Lua implementation for NeoVim, and a Python handler for Sublime. In fact, TS Server was even an inspiration for LSP, the protocol that defines a standard over how editor tools and language servers communicate. With it, a single server can be reused in multiple development tools, and editors can support languages with minimal effort. LSP uses language-neutral types, like file URIs and document positions. This is because it is much easier to standardize a text document URI or a cursor position than it is to defining a common round between abstract syntax trees and compiler symbols across multiple programming languages. So why don't we just use LSP? Why stick to this custom TypeScript protocol instead of the more flexible and general language service protocol? After all, by doing that transition, there would be no need to translate between TypeScript and editor types. However, such a change would require a major rewrite of not only the server, but also all of the clients that have been following this communication handshake for years. Moreover, such a change might not mean a huge win anyway, since in order to provide rich editor interactions, we often need to override LSP methods. Remember that LSP remains language neutral, and hence TypeScript-specific features require custom extensions to the protocol. An example of this is the new Move to File TypeScript refactor. With it, you can move a block of code to an existing file, which requires asking the user for the destination file name. LSP doesn't have a standard for code actions that require user input, while TS Server can evolve to do so. That being said, LSP is still a powerful extensibility solution, and even complex and popular languages like Rust use LSP for their language service interface. And that's all that I had for you today. I hope that you enjoyed and learned more about how you're getting all of those typed goodies. And the next time that you click on a light bulb, you'll remember this talk. Thank you for listening.
Thank you so much. And the whole talk just reminds me that it's time to make my updates to my OMO editor. Make sure to address your questions to Maria on spatial.chat and Discord.
So our next speaker is Stefan. Stefan is a software architect based in Austria and the owner of Oda.dev. He is the author of TypeScript in 50 Lessons, published by Smashing Magazine, and the TypeScript Cookbook, published by O'Reilly. He organizes ScriptConf, that1, and Rostlin, and co-hosts the German Language Working Draft podcast. Please make a huge virtual applause for Stefan. Stefan, the stage is yours.
Hi, welcome to my talk, Lies We Tell Ourselves Using TypeScript. It has been a fantastic TypeScript Congress so far. You have seen lots of fantastic speakers, people that I wanted to meet for such a long time, people that I've engaged with on social media and who are the best of the best in TypeScript. And now I need to tell you that I'm sorry. I'm sorry because you had fantastic talks from fantastic speakers, and now I'm going to crush your dreams and destroy your hopes because this is not going to be a fun talk. You know, I've done my fair share of TypeScript development. I've written 2 books about it. One, which is, TypeScript, the good parts. This is how the type system works for JavaScript developers. And the other one, TypeScript Kubeflow, where we have 100 actual problems that we are going to solve together. And throughout my journey, I always start with this example where TypeScript is absolutely perfect for. I have this JavaScript code, don't worry about what it does, but it's just JavaScript. The browser executes it. It just doesn't work. There's no error that's being thrown. Nothing tells you what's going wrong. It runs, it doesn't throw any errors, but it does not produce the right results. And for examples like that, TypeScript is fantastic. Because TypeScript, just when I activate it, finds about, 10 errors in 15 lines of code. That's what we're here for. That's TypeScript's purpose. But this is not what I'm talking about today. Today, I talk about the total opposite. I'm going to show you an example that TypeScript is totally happy with. We are just fetching some data from some API and concatenating it with something else. And TypeScript says, well, the types check out. This is good code. It compiles. You can ship it. And it will most likely crash at runtime. At runtime, those things that TypeScript is supposed to prevent. Let's go through the code step by step. The first function fetches data. We call it list entries, and you have two function overloads that define an API for you and your users. If you get a kind of species, then you're getting a promise of species in return. If you're getting a kind of people, then you're getting a promise of people in return. We are accessing the Star Wars API, which is great if you want to do any REST tests. And we have a very tailor-made API so that you actually know what you should get back. Then you have the third function overload, which is the actual function implementation for you. Next, we are fetching data. And since it has some meta information, we are unwrapping it. We are just interested in the results. One thing that is very interesting about this line of code is that we are doing some error handling. So there's one part where we say, well, that result.json call on line 3 might go wrong. So let's better catch that syntax error. What if we don't get any JSON back? Fantastic. 5 lines of code for that function, 3 lines of type information. The next is one-liner. I just formatted a little bit for this slide. Then we are concatenating a promise of an array of people or species to another list of array of people or species. So we are concatenating those two with the push method of an array. And finally, we are calling it. So we are creating a new people array and we are appending species to the people array. All right, this is our program. It's about, 10 real lines of code, a couple of type information. And I want to ask you, if you look at the entire program, do you know what's going wrong? Or do you know what's supposed to go wrong? So, well, I think everything. And where does it go wrong? Everywhere. And when does it go wrong? Yeah, one by one, because we're single-threaded. But don't worry, we are going through it step by step. We are now going to look at all our problems. Problem number 1, in chapter 1, a tale of fetch. Let's look at the core of our very first function. If you look at that, it's marvelous. We're just fetching some data from the Star Wars API, and then we are calling result.json. So we have a JSON object and we are unwrapping it. But there's one little tiny lie hidden in line number 3. This type annotation, let data of type meta people, just works because the result.json call returns a promise of any. And you know any. Any is the happy-go-lucky type in TypeScript. Any says, I'm not doing any type checking at all. You, as a developer, you know best. And since we are assigning any to meta of people, things break. Because TypeScript then thinks that you know best, and you know that the result, or that the JSON result of result should be meta people. But this is just done by yourself. No type checker helps you with that problem. And what we're seeing here is TypeScript at its boundaries, where the meta world of your types, that work well together, that you designed how they should be, meets the real world when you have user input, when you have network I/O, when you have stuff from APIs. This is where something from the outside enters your type world, and you need to make sure that those things line up. And TypeScript has a very nice way of showcasing those boundaries, or showing when those boundary problems arise. I like to call that unsafe operations. And we have keywords for that. We have, for example, a type assertion. So instead of doing a type annotation, we can say, well, result.json should be meta people. And this is an explicit type assertion from us, where we are bending the type system. The same thing with function isDice, where we say, okay, if I'm getting a number in and it is from 1 to 6, then I know it's of type dice, and I can bend the type system. I can say, type system, I know better than you do. Same with assertion signatures. And all those keywords, as in these, for us signal that we are bending the type system to our will. So if I ask you, what of those two things actually shows better that the type system is being bent a little bit? It's number 2, because you can do a full text search for the keyword as, and you find all the positions, all the places in your code where you're bending the type system to your will. Number 1 is just a type assertion. You're never going to figure out that you're having any on the right-hand side, and it suddenly becomes matter of people on the left-hand side. So what we want is actually number 2. But the problem is that type annotations with any just work, and nothing keeps us from doing that. TypeScript is totally happy with it. What would be better in that case if result.json wouldn't produce a promise of any, but rather a promise of unknown, because unknown is the cautious sibling of TypeScript. Of any. Unknown is the cautious sibling of any. Unknown tells you, please check everything before proceeding. And we can tell TypeScript to use unknown instead of any, with a little thing called declaration merging. So no interface in TypeScript is ever closed. You can always add new methods to it. This is, first of all, for keeping track of ECMAScript versions, fantastic. Second of all, also for you to patch stuff according to your browser's needs or to your environment's needs. This is how jQuery handles plugins, for example, and how TypeScript works with, the object constructor and whatever. And you can tell TypeScript, the body interface, which is the one interface that our result gets its methods from, has another JSON method of promise unknown. And since it's the last one, since you edit at the last position, this overrides the other one. So you have another function overload that now returns a promise of unknown instead of a promise of any. And if you add those 3 lines of code, then suddenly you're getting an error. You're getting an error, and TypeScript tells you, wait a second, the type unknown is not assignable to the type meta people. Unknown is the cautious type of any. Same set of values, but very cautious. And this is where you need to do extra checks. Either do a type assertion, or maybe use something like sort and make sure that the data you get is actually the data that you're looking for. Cool. Problem 1 found, problem 1 solved. Let's look at problem 2. The theme is dark and full of errors. This one is so interesting. This line of code where we are catching for a syntax error. The developer was very clever because they thought that result.json might throw a syntax error. And they are right. If you don't get any JSON back, it's a syntax error. And then you can catch the error and maybe return an empty array or whatever, use something to mitigate that error. I'm just throwing another error. Who cares? But, we want to make sure that we are catching that syntax error. The problem is that in JavaScript, anything can throw everywhere. So errors can happen all the time. And this is why the developer added any to a union. And again, in JavaScript, everything can throw. You can throw the number 2. You can throw undefined. You can throw tantrums like my 2-year-old. Basically, JavaScript and my 2-year-old are the same thing. In JavaScript, everything throws, and I don't know where it's coming from. My son throws tantrums, and I don't know where they're coming from. But anyway, if you look at that line, the little any in the union with a syntax error should tell us that this is what's actually happening. You either have a syntax error or you have any error. Because, Just have somewhere syntax error, somewhere type error, or whatever, and your program crashes. So it's true. The statement here is absolutely true. The problem is that if you put any to a union with something else, you are getting any again. The happy-go-lucky type that, deactivates type checking for you. So we are basically catching for any, which means that if you access e.message at this point, that might go wrong. So it just prints undefined now, but what if you do something with the message, like to uppercase, or you send it somewhere that expects a defined value? And you can again solve this with a little compiler flag called unknown in catch clauses, and you do instance of checks later on. So you activate the flag, use unknown in catch variables, then your error is unknown by default. So you don't need to catch for a syntax error or for any or whatever. It's unknown by default. And then you can do checks, instance of checks on syntax error to get to the actual properties of a syntax error. And this is how you mitigate these problems. So problem number 2, error handling, solution, do instance of checks. Problem number 3, the metrics overloaded. Now it gets juicy. Wait a second. Let's look at those function overloads again. We have 3 function overloads. 2 are for the interface, for your users, like kind of species returns promise of species, kind of people returns promise of people. And then you have the broader implementation signature, one that you can actually work with. You get either kind of people, kind species or people, and then you return a people array or a species array. One of those, or array of people or species. Good. The problem here is that if you look at that line of code, the only thing that I return are people. I'm not returning species, but the types tell me that I get species. The code tells me that I just return people. So I can request species in my code, and the type system tells me, well, everything is species, but in reality, I'm just working with people. And if those 2 types are different, well, then you have a big problem, because then you're accessing properties that don't exist. All right. So let's look at those function overloads in detail. We can split it up. So if you have function overloads, 2 are always for the usage, and the third one is for the implementation. And there are 2 type checks happening. First of all those usage checks check if they are being covered by the implementation. So you can't write anything in the usage section that is not being covered in the implementation section. This is what's happening here. So if I add species and people to kind, then I also need to make sure that the implementation signature takes care about both as well. You either use a union or use a very broad type like string. And the same with the return type, same thing. This is the first type check. The second type check is between the implementation and the function body. So then you look at the implementation signature, and everything you write in the function body will be checked against the implementation signature. So those 2 worlds will be checked, but nothing checks if your implementation actually covers all the usage entries. Nothing checks that. And this is the big problem with function overloads. So first of all, great, you're getting a tailor-made API. The problem is that, there's a disconnect between the function body, the implementation signature, and the usage signature, because it's not checked everything. There are just 2 different type checks happening. A solution for that is doing conditional types. Conditional types, you can basically define as the similar API. I'm now having here return type where I say, well, if I'm getting species, then return species. If I'm getting people, return people. Otherwise, never. This will never work. Don't use anything else other than species or people. And then I can use generics, use my conditional type, and suddenly I'm getting an error because conditional types are very complex. The function body can't be validated against the return type of a conditional type or the conditional return type. So I'm getting an error where I say people or species array is not assignable to return of t. Now I need to do extra checks. Now I need to do type assertions. Now I need to do unsafe operations. Now I highlight the potential problem in my code. I'm getting an error, and this is what we are here for. Now to my favorite, chapter 4, the unexpected virtue of ignorance. Let's look at this single line of code and the type signature around it. So I'm getting 2 parameters. One is an array of people or species. The other one is a promise of an array of people or species. Then I concatenate the 2 of them. Fantastic. That's all that's happening. I just take 2 arrays, concatenate them. Beautiful. Then I'm creating a people array. And then I'm calling await append entries of list and list entries of species. So I'm concatenating a people array with a species array. What's the type of list after append entries? It's still people. The type of list is still people, even though I'm adding species to the array. So this is, I have no words for that. I'm so sorry. I have no words for that, just animations. But this is beautiful. This is such a beautiful error, and it annoys me so much that it happens. But what's happening here is the following, that all the contracts are fulfilled. So if I'm having a list which is an array of species or people, then I can add a people array to it. And if I have another list of array of people, then I can add a species array to it. The problem is that the original list is being mutated, and in TypeScript, nothing exists to highlight those mutations from, for example, arrays or whatever. So the type doesn't change afterwards, and this is a problem. But there's another solution for that. If you are encountering things like this, always add generics. Generics are beautiful because generics have a very fantastic feature, which is that they lock your type into something concrete. So what I'm doing here now is that instead of taking the broad type of people or species, I'm taking a generic type parameter t, which extends an array of people or species. Then I have a list of t and I have a promise of t. I do the same thing. It's just the same code. But now when I create a list of people and I put that list into append entries, TypeScript locks t to array of people. So it locks it to the subset. It's not taking the broader set anymore. It locks it to the subset. And the moment it locks it to the subset of array of people or species, the moment it locks it to that subset, it figures out that what I'm getting here is not of the same type as list. So it tells me, wait a second, the argument of type promise species promise of species is not assignable to the parameter type of promise of people, because list defines the concrete type. You know, this is an error. This is what we're here for. Now we can act. Okay, everything mitigated. Every potential problem now has a solution. Please enter the final chapter. Lies, damn lies, and TypeScript. So far, we found 4 problems and we found 4 mitigations. We used declaration merging to patch the assumptions made by the standard library. We use instance objects and unknown to narrow down error types. Great. We use conditional types instead of function overloads to highlight unsafe operations. And 4th, beautiful, we use generics to narrow down to specifics. 4 problems, 4 solutions. And all of the solutions just have more lies. I'm so sorry. I just told you more lies. First of all, interface declaration merging is fantastic. You can extend the global namespace and add more properties to it if your software needs it, if your libraries need it. If you have Google Analytics in the window interface, well, then you can just add it to the window interface. That's what you do. It's great unless you are defining a new interface that you accidentally merge with the global, like form data here. This has happened to so many people already. I'm constantly getting messages from people on Twitter or Mastodon or wherever, where they say, you know, I had exactly the same problem because I was defining my form data with the interface form data, and guess what? It's a global, and nothing tells me that it's a global. And suddenly you're getting more methods like .get, .set. Where is this coming from? Well, it's coming from a global form data interface that I accidentally merged with. So declaration merging is great unless you accidentally merge with globals. Now something that, you know, makes my toenails go up. It's hilarious. I have 2 classes, class A and class B. Both have a number property. One is called A, the other one is called B. And then I have a do something function where I'm getting a union of A or B. So it's either A or it's B. And I'm doing instance objects. So I'm doing P instance of A, then it should be A. So I'm logging out A. And in the else branch, it's B. So TypeScript tells me that it's B, and I'm logging out P.B. Good. So this is how it's supposed to work. Beautiful. So now I can create new instances of A, new instances of B. I'm having instance objects. Everything is as it should be. And then you realize that TypeScript has a structural type system and that you can enter an object that just looks like an instance of A and that it will type check. So do something with this object A42 type checks. But if this object goes into the do something function, it will not be an instance of A. It will not be an instance because it's not being created with the new keyword. It's just something that looks similar to an instance of A, and TypeScript is happy with that. So this instance of A checks falls through. You're in the else branch. TypeScript thinks you're B, but in reality, you are an object like A. So yeah, instance objects are great until you realize TypeScript is structurally typed. Yeah. Third problem, conditional types are great unless... I'm so sorry. Seriously, I'm so sorry if you look at that. I have no clue what it does. From the creators of regular expressions comes the sequel nobody asked for. No, I'm so sorry. This here is, I guess it's about currying function overloads. I don't know. I've written this type, so it's done by myself, and I couldn't tell you what it does because just a week ago I totally forgot what I did. I've written a book about it, so this is part of my book to explain what's going on. But so if you use conditional types, know about their complexity. They are great because you can do a lot of things with it. They are very powerful. It's amazing what you can do with it, but they require extra documentation and extra care. And you're not here to work for the latest and greatest and for the most code voodoo that you can do. There's no magic in coding. You need to work with people. You need to work with yourself, or you need to work with your colleagues. And if this goes into your code base, double check what's going on there, document everything, write test cases for that. You can write type test cases. You can do that. Make sure that everything in here is documented and available, and it stands the test of time. So yeah, conditional types are great unless you figure out they are actually quite complex. And last but not least, generics are great until you explicitly make the set right as they should be. You are always able to explicitly annotate the generic type parameter, and then everything goes boom again. So yeah, 4 problems, 4 solutions, 4 more problems. Let's go for the epilogue. All right, folks, I told you, I'm sorry. This was not the fun talk. This was just problems and more problems and lies above lies above lies above lies. And I'm very sorry for that. And you might think, I've written 2 books on TypeScript. I'm doing consulting on TypeScript. I'm working with lots of teams on TypeScript. And I'm creating a TypeScript runtime, like Deno, but internally. What do I think of TypeScript? What do I think of TypeScript after finding all those big problems? And I have to say, I fucking love TypeScript. Seriously. It's still the second best language I had the pleasure to work with. It's so much fun, and it makes me so productive. And you can't argue with that. TypeScript makes you productive. This talk is not called lies that TypeScript tells us. This talk is called the lies we tell ourselves using TypeScript. And there are lots of lies that we tell ourselves. We tell ourselves the lie that TypeScript is 100% type safe. We are telling ourselves the lie that we can forget about our code because TypeScript has our back. And maybe we are telling ourselves the biggest lie, that we think that we are here to write code. And I don't think so. I don't think that we are here to write code. I think we as software engineers are here to make decisions, and we're here to validate the trade-offs of every decision that we are doing. TypeScript is just a tool in the box. The code that you write and everything that you get, for example, from Copilot or Stack Overflow or wherever, if you put it in your code base, you make the decision that this code is good enough to be put in your code base. And this is what the main task should be about. Tools can just help you make decisions, but you still need to know what's happening underneath. And you know who's really good at making those decisions and trade-offs? The TypeScript team. This is one page from the wiki on GitHub, which defines goals and non-goals. And I think the non-goals are very interesting because there's one line that basically tells you the reason for everything that you just saw. A non-goal is to apply a sound or provably correct type system. Instead, they want to strike a balance between correctness and productivity. And all those little errors that you just saw come from exactly that line. They put productivity first. And with that, there might be a couple of patches where, things might not end up as they should be. But still, you make the decision to put that line in your code. So you are the one responsible for that, not TypeScript. You just need to know about the trade-off. And there's a big trade-off in TypeScript that, stuff might not be provably correct in the type system. And you might say, well, why do they even bother if they're not making it provably correct? Because the main goal was always to make developers productive. I gave the same talk in front of 4,000 people at the VIA Developers World Congress, and I asked 2 questions to the audience. Question number 1 was, who is using TypeScript in a room with 4,000 people? Over 90% were raising their hands. And then I asked them, does anybody remember a type system called Flow? And it was 3 people. 3 people in 4,000 remember a type system called Flow, which was Facebook's answer to TypeScript, very similar in syntax, very similar in features, but the Flow folks had the goal of having a provably correct type system and thus killing productivity for everything outside React. We see what has prevailed over time. As much as I like Flow, and I know people from the Flow team, I know what they worked on and how they approached things. It's a beautiful type system. But this little decision to put productivity first is what made TypeScript so popular in the end. And this is the point of my talk. The point of my talk is that if you use TypeScript, please love it as much as I do, because I seriously love TypeScript and it's so great to work with. But be aware of the trade-off that you're making. Be aware that the type system might work differently than you expected, and it's still your duty to learn it. It doesn't take away the responsibility of learning a programming language just because you get such excellent tooling. And this leads me to the one learning that I want to transport to you, which is the one thing that you should take home. Be pragmatic and be aware. Choose what works best for you and your team. And if you don't have a team, well, you have always future you that you need to work with. You'll never code alone. Don't listen to dogmatic advice. It's so easy to make, I guess it's TikTok where you have those shorties, or a tweet or whatever that gives you this one beautiful, fantastic advice that kills everything else. But then, it's just another decision that somebody else made for you. Don't listen to dogmatic advice. Always question everything. Validate it against what you need to do. Be pragmatic, be aware, make decisions well informed. And with that, I want to say thank you very much for listening to me. Thank you very much for meeting me. I hope you had as much fun as I had. Thank you very much.
Thank you for your amazing talk. Do not forget to address your questions to Stefan on his spatial chat and Discord. And do not hesitate to share your feedback via the form typescriptcongress.com/feedback. The form is open within the whole event, and your feedback will be very helpful for us. Do you know that there will be more remote workshops after the main conference days are over? One of them will be live coding workshop to set up rollbar error monitoring. And one more, build and deploy instance GraphQL API to the edge. And the last one, practice TypeScript techniques building React Server Components app. Please check Git Nation portal to get more information about all of those remote workshops. Don't miss them.
Before we go on the break, I want to give a huge shout out to our gold sponsor today, GraphBase. GraphBase guarantees rapid data access worldwide. GraphBase provides a real-time API with data positioned close to users, ensuring swift performance and minimal latency. Whether your users are in New York or Tokyo, they get consistent, fast data access. Time to have a little break so that you can get back to us all charged up.
So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions.
Welcome back again. Now, the next speaker is Ryan. Ryan has been working on the TypeScript team at Microsoft since before its first public release in 2012. He's worn many hats in all this time, including tester, developer, customer data, and now serves as the development manager for the compiler team. Ryan, the stage is yours.
Hello, welcome to Let's Make an Inference Algorithm. I'm Ryan Kavanaugh. I'm the dev lead for the TypeScript compiler team at Microsoft. My goals today are to show you a high-level overview of how TypeScript's generic inference process works. People often ask me how this works, and I can't give you a complete explanation in 20 minutes, but we can go over a lot of the high-level concepts and explain what the general goals are. This is going to be an example-driven talk because our language is driven by motivating examples that really show why things work the way they do. And we're going to discuss possible other options of how things might work and discuss some of the trade-offs that you take as you make different decisions along the way. So let's start with an example. I have f here. It has one type parameter, t. It has a regular parameter, x, of type t, and it returns a t. Whenever TypeScript sees a generic function call, it acts as if you had written a type argument here. You can write type arguments yourself, but you don't have to. And if you don't, we will try to figure out what you wanted to go here. In this case, we're going to pass in the value 42 for x. And the question that we need to answer is, like, fill in the blank. What goes there? If we had forced the user to write a type argument in that position, what would they have written? We can start making some guesses about what we might want to do. One thing you might say is it's any. If you don't tell us, we're just going to assume any and then let the chips fall where they may, right? That wouldn't be very good. I think people wouldn't like that. We could say unknown. In this example, unknown is a safe bet, right? 42 is a valid unknown. Whatever f returns is sure to be an unknown. So unknown is a correct inference, and you could make that, and you could make a theoretical argument for unknown. We could say, well, 42 is a primitive. The primitives are number and string and Boolean. So maybe you meant the whole family of primitives when you invoked f here, and maybe that's what you want to happen. Or we might say, no, number. 42 is a number. That's probably what you want for t. We could also talk about the literal type 42. I will be pretending that literal types don't exist for the purpose of this talk because it complicates things a lot. So number is as low as it goes right now. So we think that number is the right answer here. It seems like if you called f of t and gave it a number, the sort of most specific value that we can pick is the right one. So what is the algorithm that we would write down if we had to specify how that works? Well, we would say we're going to look for t and find a place where it occurs in the argument list, in the parameter list in this case. We're going to say, oh, 42 was passed to x, so we've found this guy, we found this one, we lined up, we say, yep, that's the t. We'll say 42 is a number, therefore t is of type number, therefore it's as if you had written f of number, therefore x is a number. Cool. Talk's over. Everyone go home. No. So let's write down the algorithm here. It's like, look at the argument type where we see the type parameter being used at top level, and just sort of use that. But what if there isn't a type parameter used at the top level of our function signature? It could appear somewhere else. So I have a type here, box of t, pretty straightforward. It just has a single property called value of type t. We'll use this a lot. It's a great type to use. I have unbox of t. This is another good function. It's a great use of generics because it takes a box of t and returns the t from inside of it. So it does the great thing that you should do with generics, which is relating your input types to your output types or an input type to another input type. I normally won't be writing function bodies here just to save screen space, but you can imagine the implementation of unbox. It just returns b.value. And we call unbox and we pass in value colon 42. So we need to figure out what goes into this type argument that we are inferring. So one thing you might do is you might just do a lining up process where you say, okay, well, we saw value colon t at the b argument, and we saw value colon number down here. That's the type of this expression. And we just sort of line up the t in the number. I won't talk about exactly how you go about doing that, but you can imagine how it works. Therefore, t is of type number. Therefore, n is a number. Really good. So we might write that down as at each of the parameter positions, we'll look for t's and we'll line it up with the argument types, and we'll set t according to those matches that we found. I need to shorten this text as we change it over the course of the talk. So I'll talk about step one as collecting candidates by doing that matching process, and we'll set t to a candidate from the set that we found. But a candidate is unsatisfying. That seems underspecified. So if there's only one candidate, that's straightforward. But what if there's multiple candidates? Box, unchanged in this example, but now we have box has value of t. It takes a box, which is a box of t, and it takes an x, which is a t, and it tells you whether or not the value in the box matches the x that you gave it. And you call it, and you say value colon 42, and the string hello is your x value. So let's collect some candidates. We pick up number from value colon 42. We pick up string from x. So now we have two candidates, and we need to decide what to do. We might say, well, there's nothing really in common between number and string, so we'll just go to unknown. We'll act as if you had written box has value of unknown, which means that value :42 is a valid unknown and hello is a valid unknown. The call will succeed. That's good. We could say it's string or number. It's a little bit more specific type. Again, we would process this call and say, okay, it's as if you had written box has value of string or number. Value :42 is a valid box of string or number, and hello is a valid string or number. The call should succeed. Or we could say T should be number, and you would eventually get an error on hello, because if we had said box has value of number, we wouldn't be allowing you to pass that string to the number position. So what should we do? We've got 3 valid answers that it seems like we could choose from, but 2 of them don't err and 1 of them does. Erring seems bad, but what should we do? I will offer you a principle that I think is useful when you're thinking about generics, which is that they should usually mimic what would happen if you had inlined the call to that function. So by inlining, I mean replace the call with a recitation of the function body. So if we have this call that we had before, if we inlined it, it would look like this. It would say value :42 gets replaced here. That's replacing box up here. Dot value corresponds here. And then hello goes here. This is not how TypeScript works internally. We're always reasoning about things in terms of the function's signature. What I'm showing you here is just a way to think about how generics should work. So TypeScript would say, if this was what was happening, that you can't compare strings and numbers. That seems like not a plausible piece of code to write. It's always going to return false. You probably meant to write something like this value, which is a number, triple equals hello.length, or some other way to make these things line up in a way that they would plausibly overlap. So it seems like this call should error. But you might go back and say, no, Ryan, like T is string or number is a really good inference. You should just do that. Because if you had inlined this, but treated these values as if they were of type string or number, then it would have been allowed. So maybe this is just a circular argument and Ryan's making very bad points. To that, I would say that doesn't seem like the right behavior, because developer intent exists. At least for now, humans are writing this code. Humans have intent. And the way that you structure your code informs us of that intent. Let's think about some counterexamples of how you might have written box as value. Had you wanted the type of the box and the type of the X to not have any relationship with each other, that's what multiple type arguments are for. You could have said this has 2 type parameters, T and U, and there's no relation between these, and they can be inferred freely without regard to each other. Or really, if you really wanted things to just kind of be whatever, like you can just say box of unknown and X : unknown. There's no need to use generics at all if you're not trying to relate what's in this position to what's in this position. So our algorithm becomes collect candidates, pick the first one, and then process the call, possibly erroring because we think that you wrote those type arguments with a purpose. So it looks like this. We say it's as if you had written box has value of number, so we can't convert the string to the number here. Again, this is the inference process. We're always trying to figure out what you would have written had we made you write this. And if you feel like writing box has value of unknown here, you're always free to write these type arguments explicitly. It's all about what the inference behavior should be. It's not always about the correct answer. It's about the best answer. The best correct answer, I guess. So our algorithm here is we're collecting the candidates, picking the first one, and processing the call. But like first is pretty weird. Why did I say first and not last? Why not the middle one? Why not the second to last? Like first is pretty arbitrary here, right? So let's look at another example of multiple candidates. This time I have find of T. You give it a needle of type T and a T array, which is your haystack. And then, like I said, no function bodies. You can just imagine what find does, right? It maybe calls haystack.includes needle. So you call find and you pass hello and 1, 2, 3 hello. So it's a string in this position and a string or number array. So we go through collect candidates. We got a string from the needle and a string or number from the haystack. We pick the first one, which is that T is of type string. And then that would imply that we error on the string or number array appearing in the second position. If we think about our inlining, even though we can't see the body of find, any plausible implementation that we can think of really would not have errored on this call. So it seems like we need to do something better here. We need to pick the best candidate from our list, not just the first one. But what does best mean? That's just kicking the can down the road, right? So how do we determine best? The concept that we use is thought of as the best common supertype, which is the largest type from the candidates that is the one that contains all the others. So if we have string, number, and the union type string or number or Boolean, this last type, the third one here, contains all the others, right? String appears here and number appears here. This is a supertype of the other two. So we would pick this one and say, if these were our candidates, this should be the one that we choose. If you have fish or mammal or animal, we want to pick animal. That's going to be the one that contains the others. If you have string and number as your candidates, there is no best common supertype. We'll still have to do something kind of arbitrary here, but we're not going to form up a union automatically here for the reasons that we talked about earlier. So in this example, we collect our candidate string from hello. We collect string or number from the array. And the best common supertype between those is string or number. It is the candidate that contains all the other candidates, and that's the one we choose. And the call succeeds, so that's really good. Had you only had numbers in that array, now this call looks suspicious. It seems like something has gone wrong. So candidate 1 is a string, candidate 2 is a number. We kind of fall back to picking the first one maybe. So we'll say t is string, and then that means that we'll get an error on our number array because we expected a string array in that case. So that seems good. So we're collecting our candidates, we're picking the best common supertype, and we're processing the call. I think the collect candidates step is a little bit underspecified, and let's look at how that can go wrong. I've got box again, and I've written a new function called unbox if box. It's a great name. You either give it a box of t, and it'll give you back the t from inside the box, or you give it anything else, and it'll return that same anything else. So if, maybe you give it a string, it just gives you back that same string. We call unbox if box, and we pass in a box of number here, and we go to our candidate collection phase. So we work left to right in this union, and from t, we pick up the candidate box of number, because that's what was showing up here. Then we pick up number from t here, where it appears as box as t. There's no best common supertype, so we pick the first one arbitrarily. We say it's a box of number. That doesn't seem right. For one, it's like that's not useful at all. And even if you had said, well, the algorithm should be, no, we should union these. Let's go make unions from multiple candidates, right? That's the best thing to do. It still doesn't make any sense to say X is of type number or box of number, because the contract of this function just implicitly does not really mean that it's going to do that, right? Number is the only correct answer here. So if you just stare at the candidates, you can't really figure out what to do. You need other information about how you got those candidates. And you have to make an observation, which is that the candidates that you collect from a deeper nested occurrence of T are always going to be better than the ones that appear at high level. And the worst case of a type inference you can make is just this standalone T. And box of T is better than that. It means that you matched something more specific because it means that these things lined up. And you should always prefer this T over that T if they both exist. So we're talking about the priority as we go now. So we collect a lower priority inference from the standalone T here. We pick up number from where it appears inside box. That's a higher priority inference. And then we say, okay, we're going to take all of the candidates that tie for highest and pick the best common supertype out of those. There's only one matching high priority inference here, so we pick number, and that's good. So that's how we solve that problem. As we collect the candidates, we note the priority, and then we pick the highest priority best supertype from that list. You can look at this and say, hey, Ryan, why are we picking supertype? Why not subtype? What's going on here? It's a great question. I have a new version of find. It is still one type argument type of find of T. It takes a T array and a function that accepts a T and returns a Boolean. If we put on our imagination hats and try to think about what this does, probably it returns like, let's say some random value of type t from the array where the function returns true, or maybe where the function returned false. So I have this function isNeat. It takes strings or numbers. It tells you if they're neat or not. And then we call find, and we pass it this number array. And we're looking for something that's neat from that list. Let's do some inference. We pick up a candidate from the array, which is number. We pick up another candidate from isNeat, which is string or number. These both appear like one level deep in nesting, so they're of equal priority. So we're going to pick the best common supertype from among them. That's string or number. So that's the value that we get out. We see t is of type string or number, so x is of type string or number. Seems okay, but then you look at it for a little bit and you're like, wait a minute, what is string doing in x? We didn't give any strings to find. isNeat can't produce strings. It can only accept strings. Find at runtime has no way to even inspect find and figure out what its argument type is. So it doesn't seem plausible that someone given an array of numbers is suddenly able to produce a string like out of thin air. It doesn't make sense. If you just look at this for a while and you stare at these candidates, like earlier, you can't just look at these candidates and figure out what to do unless you have some other information. The other information that you need to take into account here is whether the t is appearing in a covariant or contravariant position, or we might talk about this in terms of input or output positions. These t's from the array are going in to find, and these values we're passing to arg from within find are coming out of find. So really, we need to think about the input and output positions of the type parameters as we're collecting them. So our new algorithm is something that I can only really demonstrate with a more complicated function. So I've made find take two arrays, and I've made isNeat also accept booleans. I apologize, that's a little bit longer, but we're going to call find. We're going to pass a string or number array into this first array, a number array into the second array, and then our predicate function in func here takes strings or numbers or booleans. Let's make a little table. I'll make the code. I'm going to condense the code sample so you can see it all on screen at once. Let's do some inference. We're going to collect some candidates. I'm going to start at arg, actually. So we're going to line up arg:t to this string or number or Boolean value, and that's going to give us our input candidate. We're going to collect from R1, it's our first t array, that's a string or number, and R2 gets us a number array. So we've got these list of candidates here. The thing that we seem to want to pick is string or number. So what we're going to do to get that result is we're going to treat the input positions as an upper bound on the result. And then we're going to do our regular best supertype algorithm among the other output candidates that we have. So our best output is string or number. That is below, in type theory terms, below this string or number or Boolean upper bound. And we'll proceed with the call as if you'd called find or string or number. So that means that Boolean isn't showing up in X, which is definitely the right behavior. If I tweak this example a little bit and I say isNeat only accepts numbers, and then I pass in a number array and a string array, we want to issue an error here. And ideally, the error that we would issue would kind of act as if you had called isNeat of A and isNeat of B. That's where the error in this program is, right? We know from find's signature that it is capable of passing a t from array 2 into func at the arg position. So we need to error as if you had called isNeat of A, because that's what's going on here. So let's try our algorithm out. We pick up our best output candidate from string or number in that array, but then we find an upper bound from isNeat because we see n:number in an input position. And so we stick with number as we're inferring here. And then from this other array, we're getting a lower output. So then we get an error. We say, okay, it's as if you had called find of number because we bounded based on this input position. Therefore, you can't convert this string or that string to numbers. And you get a really good error here. So that's great. So our updated algorithm becomes collect the candidates, noting the variance, and then pick the best candidate bounding in both directions. Lastly, I want to talk about what we call context sensitivity. It's a bit of a mouthful. I have a new function for you here, which is exec of t and u. It has a producer argument that produces a t. It has a consumer that takes a t and produces a u. And then it returns the u that your consumer produced. So if we imagine the function body that this generic signature implies, it says that exec will invoke producer, get back a value of type t, pass that t to consumer in this argument position, will return a u, and then exec will return that u. So it's kind of a one-line function, but that's its generic signature. We're going to invoke it with our producer being a function that produces hello, and our consumer function will accept hello and return hello.length. So we think n will be 1, 2, 3, 4, 5. Let's do some inference. We proceed left to right in the absence of any other algorithm, and we say, let's collect from consumer in the first position, or equivalently look for the first t in this list. The t that we see here is for arg, and arg down here has no type annotation, and there's nothing that tells us what arg's type should be. There could be a contextual type here, but there's not, because we're in the middle of inferring what t should be. So we pick up a candidate for t, which is like its implicit any. Maybe we throw that away. Maybe we don't think about it. It doesn't really matter for the purpose of this example, because we go on to collect for u. And we say arg.length is what we're inferring for u. If arg is of type any, then any.length is of type any. So therefore, the candidate that we get for u is any. We pick up a candidate for the producer's return type t, which is string. And therefore, we say u is any. Whether or not we, how you deal with the implicit any and the string candidates for t is immaterial here, because it means that n is of type any. And that's really unsatisfying, because you look at this code and you look at this code and you say, I don't see why TypeScript couldn't figure out what to do with this. So what you have to figure out is arg can get a type based on its context. So this expression, it can change types based on where it appears in your program. For this function, not so much. It doesn't have any arguments. It just returns a string. So what we can do is process these arguments out of order by looking at whether or not they're sensitive to the context that they're in. So our new algorithm is going to be that we collect the candidates from the non-context sensitive expressions. We're going to look at all the type parameters for which we've collected at least one candidate, and we're going to pick the best one from there. And we're just going to write that down and then keep going. We'll repeat the process for our context-sensitive expressions, and then process the call. What does that look like? Let's do some inference. We do our inference by first doing our pass that's looking at the non-context-sensitive arguments. Here we have t:\string coming up from hello. So we're done with all of our context-insensitive expressions now. So we write down t is string. We go to process arg, and we say, arg is of type string. I wrote down string here. I'm going to write down number later, but I wrote down string for t. So now when I'm looking for the contextual type for arg, I know that it's string based on t and the string that we wrote down earlier. That lets me process arg.length, therefore u is of type number, and everything just kind of works. You can think about what to do with t in this particular position. It doesn't tend to matter, since it just kind of doesn't. If you work out why, you'll see why. But that's how it works. So that's our context-sensitive expression inference algorithm. So in summary, I hope I didn't scare you too much. I think this is all pretty straightforward. We had some pretty basic code examples, and by looking at those code examples and how they were written, we were able to figure out what the intent of the user was, and we could use that to do the right inference. Just being correct isn't really enough. You have to also get the best inference. I showed a lot of examples where there were 2 to 4 correct answers to choose from, but only one best answer. Inference is really like a multiple choice test, where you're not just tasked with finding a good answer, you're tasked with finding the best answer. And if you think about your language design in terms of your motivating examples, I think that brings a tremendous amount of clarity, because if you just go and try to write down an algorithm without looking at how the examples that you care about act, you might not get the best behavior. So always be looking at the examples and using those to drive how you make decisions about your inference and everything else about your language. Have a great day.
Thank you, Ryan. That was such an amazing talk. Do not forget to address all your questions to Ryan on the Spatial Chat and Discord. And do not forget to address your questions to the speakers on the Spatial Chat after all their talks. You can join the Spatial Chat directly from the timeline below the player. Click on the object with the speaker's name, who is having a Q&A now, and join them in the platform. Our next speaker is Alexandra. She's a software engineer based in Poland. She's working a full-stack developer with many different languages such as Elixir, Golang, Python, and TypeScript. She was previously a tech lead for the Hasura console, and now she's a lead maintainer of Blitz.js. Alexandra, the stage is yours. And dear audience, make some virtual noise for Alexandra. Yay!
Hey everyone, thanks everyone who's joining. Today we're going to talk about TypeScript performance. So a few words about me before we begin. I work on open source at the Guild, primarily in the GraphQL ecosystem, and I also co-organize a TypeScript meetup in Poland. You can find me on Twitter as Alexandra Says or Biros on GitHub, and also feel free to check out my personal website, alexandra.codes. So this talk will have three main parts: an introduction to the topic of performance, ways to debug performance, and what to do to improve it. It will be like an overview of the existing tools and how you can use them to help you deal with different performance issues in TypeScript. So I will start with the introduction. At this conference, we all probably know already what TypeScript is and why we are using it, so I will go straight to the point. So what do I mean by performance today? Usually when we talk about performance in computing, we talk about the runtime performance, like how fast are things to our users. But today we're going to focus on the developer's experience and on our tooling. And I wanted to talk about it because whenever we are building a feature or fixing a bug in production, we would like to be like this Formula One driver. Our tooling should get us up to speed, and it shouldn't slow us down, because the better our process, the more value we can deliver to the end users. And I think that this is an important topic because like slow compilation time and lagging editor can be quite annoying. And what's also important, it can be quite time consuming. So we'd like to avoid that. So because TypeScript team is doing like a lot, like really a lot performance improvements. Before I even go further with my presentation, I want the first takeaway from this talk to be keep your TypeScript up to date. I'm going to show you a quick example. So a few months ago, or maybe even like half a year ago, I wanted to like debug performance issues or like see if there are any in Hasura console. That was like a familiar code base for me because I used to work there. So I was like, okay, let's check it out. It's a fairly big application, and I ran TypeScript compiler, and it was 35 seconds, almost 35 seconds. And I think we can all agree that this is a lot. And then like before doing any debugging and like looking into the types, I upgraded TypeScript. Back then it was, the latest version was 4.9.5. And you can see that it's like 3 times faster. That's a really huge difference. And you can compare the check time. It went down from 31.5 seconds to less than 9. That was huge. So firstly, thank you TypeScript team for all the performance improvements. And secondly, remember to keep your TypeScript up to date. You can use tools like Dependabot or others like Renovate to make it even easier. But the thing is that it's not always enough. Like we can think logically that, you know, if we have bigger code base, if we have more code, then TypeScript will work slower, like linearly, considering like the amount of code we have. but that's not always the case, and I want to show you one example. So what I have here is a simple page that renders, this is the whole code. It's React, it renders 4 buttons. I have like medium button, small button, some big button that is being created from the, this is not the file I wanted to show you. Oh, here's my big button. This is created using styled function from styled components. And I also have big button anchor. And I'm also using the styled function. And this is like the only difference that this is an anchor. So this code renders 4 buttons. And you can see here that the compilation time was almost 14 seconds. And I think we can all agree that that's not ideal. Like we have only 4 buttons. Like imagine if we had like 8 or something. So this is more or less what we are going to talk about today, like those kind of issues and how to spot them and maybe what to do to avoid them. Okay, but first, before going further, I wanted to go over like how compiler works, what are the steps in the TypeScript compiler, because I think that this knowledge will help us better understand how it affects the performance, and maybe also like how it will allow us to pinpoint what step is responsible for our performance issues, and in the long term, it will make us better TypeScript programmers. So the first thing, the most important part is program. It's like an object that has all the compilation context. The 2 things that are needed are obviously some TypeScript files and a tsconfig that describes how the compiler should behave. Then we have a scanner step, which scans the source code like character by character and converts it into a list of tokens. If there's something like if there's an invalid token, it will throw an error. So here's an example for this simple like 1 line of code. We have the const keyword. It also recognizes white spaces. We have identifiers, colon token, and so on. And then the next step is parser. It takes all these tokens, all this list, and constructs an abstract syntax tree. So you can also say that it brings context to the scanner. So for example, you can see the AST here. So when it goes over the tokens and it says that there is a const keyword and later on there is like a colon token or an equal token, it will know that it will be a variable declaration, so it can construct this variable declaration node. You can use tools like TypeScript AST Viewer, or there's also AST Explorer to like visualize your code as the abstract syntax tree. Okay, so the next step is binder, and this is a very important step. It gathers information about the whole context. So it's quite expensive. It's a single run through the entire AST, and it picks up some information that will be used in the later steps. So here's an example. Like one thing it does, it stores a metadata for each node of the tree. It also keeps track of the scopes. So like when we are inside of a function, what variables can I use? Like what's the function scope? Another thing is that it sets up parent nodes on each node, so that later when the checker has to like see what's the type of a particular node, it can easily like go up the tree. I will explain that in a second. Okay, so now we have the checker step, and that includes most of the diagnostics. It has 2 main responsibilities. One is it checks if types are assignable to each other, and the other one is it does type inference. So if there are any gaps, like if there's no like explicit typing, and if we have like one node and we don't yet know what's the type, it it's checker's responsibility to like figure it out and to like fill those gaps. So this is why those parent like information about parents is important, because like let's say the checker is on one node and there's no type information. So maybe it needs to go up the tree, because maybe somewhere higher there was like an explicit type declaration, or maybe somewhere higher it already figured out the type. So this is why it needs to be done fast. And then once it figures out that, for example, maybe there was explicit type declaration for the function and we are somewhere inside of the function, it can pick up the type and then go again down the tree to fill the gap. Okay, and then we have transformers. So to put it shortly, this step takes the AST, and if we want to have the JavaScript code, it strips all the information about the types. And if we want to have declaration files, it strips all the things related to JavaScript and leaves only the types. And finally, we are getting the files that we requested. That is, if you requested any, because you can also run TSC with no emit flag to only do the type checking bit. So this is more or less what happens. In reality, it's not that straightforward. Then there can be like a lot of back and forth between the steps, but I just wanted to give you an overview of the important bits. So you can also try it out in TypeScript Playground. There's a scanner plugin. There's also AST plugin, transformers. So you can like visualize some of those steps. Okay, so we saw what's going on, and like obviously with a larger code base and more complex code, that can be slow. All that like traversing through the AST and like all the tokenizing of the code, that can take a lot of time. And what's the easiest way to be faster? And you can think about this question in terms of like not only TypeScript compiler, but like in general, if you have a long to-do list and you want to be done for the day and like enjoy your evening, like what can you do to be done faster? Well, the answer could be do less stuff. And well, the thing is with TypeScript compiler that we can't eliminate some of those steps, but we can make it do less work. And we're going to see how later. So the first part is debugging, because without knowing what exactly we should improve, we can't really improve anything. So the question is that my build takes forever, my IDE is lagging, and now what can I do? So the first thing that I usually do is run diagnostics or extended diagnostics. And this will give us like some basic information about what's going on in the code base. So this is an output from the diagnostics flag. You can see how it maps to different compiler steps. We have the sparse time, bind time, check time, emit time. And if you want something that makes it easier, like something that automates it without you having to run it on your code base every now and then, I created this very minimalistic GitHub action. It's called TSC Diagnostics diff action. And basically for every PR, it gives you this diagnostics comparison. You can kind of like configure it to have different outputs. But going back to the output of the diagnostics flag. So the first question you can ask yourself is, do these numbers, the number of files, lines of TypeScript, JavaScript, JSON, and so on, do these numbers roughly correspond to the number of files in your project? Because if not, then maybe TypeScript is picking up too many files. And maybe that means that your TypeScript configuration is not correct. So one thing that you can do is you can run a list files, like this TSC list files with list files flag. and see what exactly are all the files that TypeScript is picking up. While the output from this flag is not very user-friendly and not very easy to read, you can use this WebTreeMap CLI tool to visualize it. It will give you, it will open this HTML in your browser with all your, everything that is important visualized. So you can see what's taking, what files are significantly huge and so on. It will help you spot that maybe you are compiling something that you don't really want to. Okay, another thing is high program or write time. So that also can indicate that the configuration is not correct. And I wanted to show you another flag. There is show config. It's especially useful when you have you use extends in your config, and you extend one config after another. So sometimes it's quite difficult to know what's actually the final configuration, and that show config flag can help you with that, because this will print the actual configuration that TypeScript is using for your project. Okay, and now the most important part, and I think the most interesting part, high check time. So for that, I'm usually using generate trace flag, and I'm going to show you a quick demo. I have one project here. This is I just picked a random project from the GitHub Explorer page. Basically, I just wanted to play with different projects, and I run the generate trace command. So basically, to do this, you run this yarn tsc ---- generate trace, and you also have to provide out directory. So I already did this before, not to spend time on that. I have it here. It generates trace JSON file and types JSON file. And now what can I do with this trace JSON? Because you can also probably see that it's not very user-friendly to read. I'm loading it in the browser. So I have it here. So you can open, if you're using Chrome, you can open about tracing, or you can go to you can open developer tools and go to performance tab and load it there. There is a button, you click it, and then you pick the trace file that you just generated, and you're gonna see something like this. So now when I open this file, I can see that maybe there's something going wrong. So I can, in this example, one thing I noticed is that around here, there seems to be a lot going on. And if I click on this check source file, I can also learn what is the file that is being problematic. And well, that gives me already some information. I know where to look for my issues. And then if I go down with this check expressions, you can see that the metadata here is slightly different. I also have the path, but I have the position and end. With this check source file, I only had the path. So basically, you can pinpoint where is what type checking, where the type checking is slow. So I can go even lower. I see now that I'm in the trpcts file. Now I'm in _upts, and I guess this one is something I can look into. So if I open this file, I will copy it, go back to the project. So if I open this, I pasted the error in case it doesn't work during this presentation, but I can already see that TypeScript tells me that the import type of this node exceeds the maximum length of the maximum length the compiler will serialize. The explicit type annotation is needed. So, okay, I know where the problem is, what's causing my TypeScript build time to be slower. And I know that this is the place that I probably want to refactor. This is quite useful because, like, imagine you're working on a large code base, and or maybe you went on vacation and someone other people were working on the code base. You go back and you notice that the build time is much longer. And how do you proceed? Like, where do you look for? Like, do you go over all the PRs, all the comments that people added to see what was possibly changed that caused the issue? Well, that's one way, but like using this generate trace will get you there much, much faster. And I also wanted to show you another thing. Like here is a second place that looks like it takes quite longer. This particular file is this handle children event types test TS. So here we have other boxes, like we have this check the part node with this kind of metadata. We have check variable declaration, check expression. We also have something like structured type related to. And here we have source ID and target ID. So those are like IDs of the types that are being compared. And now what to do with that? Well, there's no information in the trace itself, so you don't really know what the type is. But if we can copy this ID and go to the code base, and if we go to this types JSON file that we didn't look at before, let me make more space. There's something like go to line in VS Code, and you can go to this particular line. We have this ID, and now we know what is the type that is being compared. We know that the first declaration is in just mock extended package, and we also know like what's the start, what's the end, and sometimes there are also additional information. So we know that this is our source that is being compared to, and the target, I will go to line again, and the target is Prisma client. We also know like what are the type arguments. This is a generic type. We have this first declaration, points us to node modules, and sometimes we also have like a display information. So it, not sure if I can show. Oh, for example, here we have this display. It shows you exactly the code here in this place. And now, if we go to this file that we are now debugging, we can see that there is in fact something like Prisma mock, and this is where this just mock extended is being used. So this is more or less how you work with the trace JSON and the types JSON file that was generated. Okay, now let's go back to the slides. This one. Okay, you can also use a tool called Analyze Trace, and you provide it with the output directory that you like, where the types JSON and trace JSON are were generated, and it will give you information about some hotspots in your code out of the box. Now, there's also something that me and Daniel, who's also speaking at this conference, are thinking about and slowly working on. We wanted to make this experience a bit easier. So we're thinking about something called, like, this is a working name, TSPerf. And this is going to be, for now, a VS Code extension. I made a recording in case something goes wrong with because this is a work in progress. So I'm going to show you. Basically, this extension generates the trace for you, and you run one command to display the trace. So it kind of saves you some back and forth between the browser and your project. And we have also some other ideas, so stay tuned. Okay, now the slides and the improving part. So there are a few ways in how you can have problems, basically. So the first one is it doesn't work the way it's intended to. So that probably means that you have to check your configuration. Maybe your exclude, include, or files are not configured correctly. you can reference this tsconfig page. It will you will learn there about all the configuration options and how to set it to achieve what you want. And now let's say we have that covered. It does work the way it's intended to, but still it's doing too much work. So now we have a few improvements that we can do. The TypeScript team created this performance wiki with a lot of very, very useful tips. I'm going to show you just a few with some examples. So here I have 2 examples. I think I only have time to show you one. This is a change from a Zode runtime validation library. So basically what happened here, you can see that this Zode, I make it slightly bigger. Okay, you can see that the Zode formatted error was quite complex. Like there was a lot going on. We have conditional types, and we can guess that TypeScript probably has a lot of work to do there. So basically what the author of the PR did was to extract the complex part, the one with conditional typings, to a separate type alias and use it for Zode formatted error. And I think in this description, you can see how what was the improvement. So you can see that the check time went from 31 to 20 seconds. I would say that's a lot. And why that happened? It's because TypeScript can now cache this type alias, so it doesn't have to recalculate that every time this Zode formatted error is used. And that caused this improvement. Okay, so this is the first tip, like name complex types, extract them to separate type aliases. Another thing is to make your type simpler. I showed you this demo with side components, right? So the reason why it's taking like that much time is because I'm using like a lot of complex higher level functions from side components, this style, this memo. So this is actually from React, not side components, but this one is from side components. So that's like the TypeScript has to do like a lot of inference to figure out the props. So in that case, there's like no easy fix. Like there's no like one line fix for the typings. Like something I needed to do here was to actually like refactor my code. And I have it here. I created new components without using this site. I provided the props. I typed them explicitly. So I have it. I have it here. I have those types, and here my basic button looks like this. So now if I run the extended diagnostics to see the difference, I think it will be PNP. Good. Yes. Yes, you can see that this is much faster. It's only 2 seconds. Okay, so that was another example. And the takeaway from here is to like not show off. Sometimes simpler means better, and simpler also can mean more performant. And another quite interesting example, it's something I found in one of the projects I was working on, GraphQL Code Generator. You can sometimes help TypeScript, but there is, I added this if you really need to. Like, you can rely on TypeScript inference for most of the time, but I wanted to share this particular example because I found it interesting. So, I start by showing you the trace. Yeah, here we go. So this is the generated trace from this project. You can see that this file, this Babel TS, is taking a lot of time. So I went, I debugged it. It turned out to be around this declare function, and particularly about inferring this this first parameter, the options here. And what I did, I provided this generic parameter explicitly. So I typed this client Babel preset options as what we actually use, and that helped quite a lot. I will show you the trace after the change, so you can see that there's no more hotspot in the code base. And that happened because now you can see that this the second generic parameter, it has default type. There's this Babel.plugin object, but because the first one doesn't, TypeScript had it always needed to run the inference for this. So because of I provided the first one, so I basically did something here. Then TypeScript is able to default to this one for the second parameter. So that was my another example, and the difference was that the check time went from 1.5 seconds to 0.88. And I think the last example I wanted to show you is to be reasonable. So TypeScript has a lot of really, really amazing features, and one of them are, I will slowly close this, template string literals. So you can you can do a lot of that, but sometimes maybe you want to ask yourself how much you want to do, because this is an example from one of the issues reported in TypeScript. So basically, we have this type full date string, and the year, the month, and the day is all being declared with templates. And you can see, if I hover it, that there are more than 74,000 elements in this union, and that's quite a lot. So even though I have a really, really short code here, it's 30 lines of code, 29 if I count correctly, this takes almost 2 minutes to compile. That's a lot, and the check time is it's slightly less than the total time, so it's almost almost 2 minutes. So the takeaway here is also to be reasonable. Don't overdo it, and don't skateboard on Rake. So now let's say that we did some improvements, and we also fixed the config if there were any issues. So it works the way it's intended to. It's doing the minimal required work, but it's still slow. So now what you can do is you can use the incremental flag. You can set it in the compiler options. So that will let TypeScript cache some information about the compilation. So whenever you recompile the project, TypeScript will calculate what's the least possible effort to do so. So it won't compile files that weren't changed, for example. And if it's still bad, you can open a new issues. So some tips to do so. Firstly, make sure that you're using latest TypeScript. Maybe your issue was already solved. You also have to include extended diagnostics output, the trace from the generate trace usage, and a minimal reproduction, or maybe a link to the repository if that's possible. So to summarize, we saw some tools, and we saw how to debug performance issues with the generate trace output. I hope that it will be useful to you, and I really, really hope that you won't have to deal with any performance issues. But if you do, here you have the overview of the steps that you can take to improve the code base. Okay, so that's all from me. all of that you can find on my website. If you go to alexandra.codes and to my speaking page, and if you find the TypeScript Congress entry, you will find the notes from this presentation. Thank you all.
Thank you. That was an amazing talk. Do not forget to address your questions to Alexandra on a Spatial Chat and Discord.
Let's now move on to our first block of lightning talks. Ahead of us are 3 blocks of lightning talks. The first one, you will listen to Jamie, engineer at GraphBase, who will talk to us about unifying APIs at the edge with GraphQL and type safety. And the next speaker is Matt, and he will be talking about running TypeScript in WebAssembly on the cloud. And the last speaker is Arthur, and his talk, Enhanced AST Static Analysis with TypeScript Language Server, is surely going to entertain you. So folks, the stage is yours.
Hey everyone, I'm Jamie. I'm really excited to be here today at TS Congress, and I hope that you're all having a fantastic time so far. There are so many amazing speakers and talks lined up. I'm really excited to check those out and catch up, but obviously after this talk. We only have a few minutes together today really to go through some slides and a demo, so I think we should dive right into the topic, that is unifying data sources with GraphQL. Now, if you're building an API, it doesn't matter if that API is REST or if that's GraphQL, it's pretty hard. Yes, it's easy to install a dependency, create some type definitions with GraphQL, and then create some resolvers and then deploy it. It's easy to do that, but there are so many other things to consider when building something scalable that you want to deploy to production at the edge, hopefully, for your users to use and consume. And this list that you see here is really only a small snapshot into some of the concerns that you have to kind of think about when building something scalable and maintainable in production. But I think the biggest problem today, it's a great benefit to have, but the biggest problem is that we have so many different data sources today that we all have to figure out how to use. All of the APIs and SDKs, well, they all differ as well. There's a different learning curve. There's different types of documentation. Some are more documented than others. Some take no time at all to get started, and some take days to figure out. And because we're using so many of these services now to deliver our end products, well, it can often just be really time consuming to do that. I think the simplest to-do app that we all used to do and build when we first got started with something, I think in today's world with all of these different data sources, I think there is so many different implementations of that now, where maybe you create a to-do app that when you add a to-do, it sends you a notification via Slack or email or SMS. So there's 3 services. And then maybe is when you add something or remove something or check something or uncheck something, maybe that goes on to find spots in your calendar that are free so you can actually find time to do these to-dos. So yeah, there are so many things to consider when building apps with all of these different data sources, and it's great that we've got this flexibility. But yeah, like I say, the downsides is some of these APIs have better documentation, some of them don't. But the biggest thing I think with this is that all of the different services that we use today, they aren't really focused on where the data maybe lives, because they know that they could just rely on someone using some caching or a static site generator or something. So most of these just deploy to a single region. But of course, if we want to use all of these different services, that data really should be at the edge closest to the user, so they can get the best experience when using your application that obviously you create using TypeScript. So, and I think all of these APIs, they're deployed to a single region. Obviously, you can pay to maybe deploy it to other regions, but I think that's just something that we all should have the flexibility to do and configure on our own, because there are so many services that don't give you that flexibility when you really want it. And maybe if you are to get that from a service provider, they may charge you a lot more to do that. So that's the one thing that we are on a mission to solve at GraphBase, and we allow developers to connect any type of database, maybe a warehouse or a commerce application like Shopify. If you have a product in Shopify that you want to extend with more products or reviews, you might want to get those reviews from a different API. Maybe you have some content in HighGraph or Contentful or Sanity that you want to add to these product pages. Well, we give you the ability to kind of add data sources, extend them, and add your own custom code and do other things. So we're on a mission to do that, to create a single GraphQL API that you can bring different data sources in with, and then your different front ends as well. And with all of this, you have full type safety on the back end, full type safety on the front end with that unified GraphQL API. And there's so many cool tools to do that. And the other thing that GraphBase does is obviously it has this unified GraphQL API where all of these data sources live. And then on top of that, you can add things like auth. So you can bring your own auth provider like Clerk or Auth0, and then you can say this user can update but can't delete, or they can read and not write. All of that can kind of be configured within the configuration, but the actual user management happens elsewhere. So you can bring your own users essentially to use the API and the connected databases as well. And then on top of that, we obviously mentioned previously about kind of how important it is to have data readily available at the edge, close to the user. Well, we do that with caching at the edge as well. So that's baked in to all projects that you can take advantage of. Then when you deploy this to production, if you open a branch on GitHub, we'll automatically create you a preview URL that you're very used to, no doubt, with things like Vercel and Netlify. They give you that immutable URL that you can use. We do the same for GraphQL. We'll give you that new API endpoint, so you don't have to think about, figuring out how can I build that myself. That just comes for free out of the box. We also have other products like search and then analytics as well, so you can get full insights into what's going on with your project. And like I mentioned before, this works with anything that you're using today. Wherever you can make a fetch request, you can use GraphBase. But the important thing that I want to highlight is GraphQL and TypeScript. They work very well together because of the type system. GraphQL strong type system can be used with things like the GraphQL code generator to generate all of the TypeScript types for all of your GraphQL types, and maybe it's your GraphQL queries and mutations, and if they have inputs and arguments, some are required, some are optional. The code generator can create something in TypeScript that maps to that. So when you're using GraphBase and you're creating your own custom resolvers, you can use all of that code, all of that generated code to create something that's fully type safe from the back end to the front end, which I think is really powerful. But the topic that I really want to cover today and show in the demo next is actually when we started to build GraphBase, we had a single GraphQL SDL as configuration. So on the left here, you can see there is schema, and then we have this custom directive called auth that you would then configure all of your different auth providers with. So this OpenID Connect provider could be something like Clerk, or it could be Auth0 or something else. You can then add that as an auth provider, and then you can specify a list of rules. We just have one rule here, which is allow private, but then that would add some rules to your backend to only allow authenticated requests. Then below that, we have this GraphQL tag, which is defined in a namespace, the URL to the Shopify store or to the Contentful store. And then we have some headers as well. Here we've just got a custom Shopify header. If you were to use this with Shopify, if you were to use this with Contentful, you could obviously pass through different headers, and then those would go on when you make that kind of request to the different providers. So yeah, this is the SDL that people had to use for so long. And it's fantastic. I still use it today. I also use the new TypeScript configuration, but the SDL was really nice. But the thing that it didn't give developers was it didn't give you any hints into what was going on with all of the different kind of configuration and options. You didn't get any help from TypeScript or the code editor when you were configuring backends with SDL. So that's why when we spoke to the community, we noticed that a lot of people were looking for a way to create something that was type safe. So we built the GraphBase SDK. The team put together a proposal. We spoke to the community and they said, wow, this is great. How can I use this? So we started to build the SDK, which allows you to import things like auth, config, connector, schema, and then you can create models from that. You can then connect things. And as you're typing, you can use TypeScript to its full advantage to make sure that you're passing a string where string should be invoked, an integer, etc. And things like the headers API, we make sure that you can customize and specify the right kind of keys and values there, and no one's going to mess those up. So you get that full type safety, which we love as well, thanks to TypeScript. And I think the other thing when you're building GraphQL queries in resolvers that are custom to you, so you're building these within GraphBase, you can configure all of the different kind of arguments that those have. And if there is any optional fields, you can declare that inside of here, and TypeScript helps you generate that SDL automatically. But yeah, I want to jump into a demo now. Now we'll open our code editor. Imagine this was your front-end application and you wanted to create a backend for your front end. You can use the GraphBase CLI to initialize a new project. And then, of course, we want to use TypeScript as that config option. I'm going to cheat a little bit. I'm going to invoke some steps that I created earlier so we can update and change how this configuration looks. But as we explore this file, we can now see that we can hover over things and we can invoke things, and we get full help thanks to TypeScript with all of these kind of descriptions and options that are available inside of our code editor. So we love this experience now, and we think that our developers do too. They tell us they do, and we're really excited to kind of expand on this builder pattern of building APIs. So let's get started by creating a query here. We have some arguments that are optional. Now we'll go over to the file that we have, hello.ts. Here we have a TypeScript function. We can import SDKs and whatever inside of here, but this is TypeScript. We're able to create a TypeScript resolver that will later deploy to the edge. I think now, with this resolver, we should start the GraphQL server, and then if we head on over to the port 4000, we can launch Pathfinder. And this schema that we see here, this was all generated from that TypeScript config. So we didn't have to worry about writing GraphQL SDL. We were able to just use TypeScript and forget about that. You need to know GraphQL to build a backend. You don't. You can use TypeScript to build these backends. So as we run the next step now, we can create another mutation to RSVP to an event, maybe something like this. Then we can define some things like enums and inputs and a mutation. And we have a file now that accepts some parameters. All of this that we have here is type safe, so you can work with TypeScript and GraphBase to create these backends, and you don't have to wait until you start the server to run into errors. We'll tell you if there is something up before you get there. And as you can see, the schema for GraphQL has been updated automatically using that TypeScript config. That was converted to create this GraphQL API that you can then use for your front end. So let's execute a mutation here with GraphQL. We will RSVP to the event. We can pass along our name and our status here, which is an enum in GraphQL. And we can send different enum values if we want to. And then when we run that operation here, that will return the data to us. So that is basically a custom GraphQL query and mutation using TypeScript that was configured using TypeScript inside of our GraphBase repo. Next, we can do things like connect things like Stripe using the Open API connector. And then here, thanks to TypeScript, we know exactly what we need to pass, things like headers, what the key is, what the value can be, and the same with transforms as well. We can transform the schema to exclude certain fields and queries and mutations. And again, thanks to TypeScript, we get all of this help. Before, when we use an SDL, none of our users could do that just inside the code editor alone. They were always having to go to the documentation to reference what they could and couldn't do. And that took up a lot of time, and people weren't deploying and building applications quicker. But I think now with TypeScript, they are. It's fantastic. So with that Open API connector added and with the server running, we get all of the Stripe API here in GraphQL thanks to the Open API spec. We take that and transform that into GraphQL. And users of GraphBase that want to build these backends don't have to worry about learning GraphQL really from a server point. We'll abstract all of that complexity for you, and things like passing headers here, we can see we forward from the client to the underlying service. In this case, it's Stripe, and we update that. And when you make a request from the front end, we'll just pass that right along to Stripe, which is cool. And there's things like logging, so you can dive in and figure out exactly what's going on if things do go wrong inside of your resolver. Next, let's extend the Stripe API. Here we have a Stripe customer. The Stripe customer is the type in GraphQL for the Stripe customer, but users don't have a Gravatar field. So I think we should add one. Here's some custom code inside of our resolver that is fetching the email from that Stripe customer, and then it's creating that Gravatar URL, and then it's just going to return a string. So now with that running, if we go to Pathfinder and we close the headers tab, we should now be able to invoke that Gravatar field that didn't exist before. That doesn't exist with Stripe, but we've been able to extend the Stripe API with GraphBase using TypeScript. Now we can pass a different value in the arguments here, and we can get a different link to get a different image size. So that has been extending Stripe with GraphBase and with TypeScript, and all we really had to do was configure what that looked like using the SDK and then writing that code. And lastly, we'll look at caching, where you can configure different rules. So here we have the Stripe customer. We don't want to cache anything else but our Stripe customer, because generating that URL for the Gravatar image, well, that might take a little bit longer. We don't want to wait for it. So let's cache that URL response so we can configure at a kind of a type level, a field level, whatever you want. You can configure that with GraphBase. And then when you deploy that to the edge and you make a query, that will be cached. So inside of here, this is when the project's deployed with GraphBase. We can open that project inside of the dashboard, and here we can see we haven't passed that header along, so our API is protected. Now if we pass along the authorization header for Stripe, this is our secret key with Stripe, we now run that operation, and that will be successful, and we get that Gravatar URL. But if we open the history here, we can see that we have a cache miss. Now if we execute that again, we should get a cache hit. And we can see the difference in time here. The response time has gone down significantly thanks to that caching that's happening at the edge. So this has been one field extending one API, but imagine all of the different data sources that you use. Bringing that into a unified GraphQL API can considerably save time and cost for building applications. So hopefully this has been interesting. We think developers can build really cool backends with GraphBase, and they can still go on to use TypeScript to create custom code where they want to inside of those custom resolvers. But then to configure all of this, you don't need to learn GraphQL on a server side. You can just use that TypeScript configuration and the SDK to build the backend for you, which is pretty powerful. And that's why we love TypeScript. So if you're interested to learn more about this, you can go to graphbase.com. And if you've got any questions, please feel free to reach out to me on Twitter. I'm at Notrab. That's just Barton backwards if anyone's wondering. I'm happy to answer anything about GraphBase and in GraphQL over there. So thanks very much for having me today.
Hi, I'm Matt Butcher. I'm one of the founders of Fermyon Technologies, and today we're going to be talking about running TypeScript in WebAssembly on the cloud. So that's a lot of terms to unpack here. Let's start really quickly with WebAssembly. So you may be familiar with WebAssembly as a browser-based technology. The original idea was to build a runtime in a binary format in which you could compile lots of different languages to the same language-neutral runtime format and execute it inside the browser side by side with JavaScript. So, for example, in the case of someone like Figma, they used WebAssembly to take their C++ code, compile it to WebAssembly, and then interact with it from their JavaScript running in the browser. Now, at Fermyon, we took a look at WebAssembly, and what the runtime characteristics of WebAssembly are just right for the cloud. It has very fast startup times, very small binary sizes. The security sandboxing model is great. And of course, it supports cross-platform, cross-architecture, and cross-language. So we took the WebAssembly runtime, plucked it out of the browser, kind of popped a version into the cloud, and began building a cloud runtime. So the second term we want to define is serverless. Fermyon is a serverless environment. Spin builds serverless applications, but serverless itself is a term that sometimes gets used in really unclear ways. So I want to make it really clear what I'm talking about when I talk about serverless. What is the server that we are doing without? Well, to me, it's the software server. If you're used to building microservices or other kinds of back-end technologies, you know that step one is usually setting up some kind of server, something that'll start a socket server, will open a port, will listen for inbound requests, will handle those requests. You end up writing all kinds of boilerplate code like interrupt handling and TLS certificate loading and all of that kind of stuff. So in serverless, to me, a serverless application is one where we can do away with all of that, where the entry point for the application is the event handler. So we'll talk primarily about HTTP, though this could equally apply to consuming something off a pub/sub queue or dealing with a time-based trigger. But in HTTP, the event is an HTTP request that comes in. You get that request, you handle the request, you return an HTTP response, and you shut down. So there's no setting up a server, there's no setting up TLS certificates, none of that. The serverless environment says you just define an event handler that takes the request and returns a response. So we wanted to take WebAssembly, put it on the server side, and build a serverless framework. To do that, we needed a tool. So we built Spin. Spin is an open source programming tool and in some ways a platform that allows you to create serverless applications in a variety of different languages, compile them to WebAssembly, and run them in the serverless style on the cloud. Spin supports as sort of like top tier languages, Rust, Go, Python, and of course, JavaScript and TypeScript, though it also supports a number of second tier languages. And we are working on all kinds of tooling to make it easier and easier for you to build an application that is powerful, has key value storage, database, even AI inferencing, but that still follows that very simple kind of low setup, almost no op style developer environment, and a very easy serverless style of program development. Primarily, we'll be talking about that. So let's switch over to our VS Code editor and let's use Spin to create a new serverless app. And along the way, we'll talk about both how the serverless environment works and some of the cool nuances of the way that TypeScript works in this environment. All right, here we are in VS Code. So the first thing to do would be to install Spin. You can head over to developer.fermyon.com and kind of click your way into the quick start guide and see how to quickly install and get up and running with Spin. I happen to just use curl bash to install it, so I've got it running here locally. We're going to create a new TypeScript serverless app. So just to quickly kind of see what all is supported, we can run Spin templates list and see sort of all the different starter templates. Some do Redis with languages like Go or Rust. Some do HTTP, Swift, Python. We're looking for this one here, HTTP TS, to run TypeScript applications. So let's create a new Spin new HTTP-TS. We're going to create one called Congress, and we're going to go ahead and accept the defaults, which basically just skips the walkthrough where it prompts you for a description and the default route and so on, and just chooses those for us. So we can see it created an application for us. This should look very familiar to you. There's the package.json, the TS config, but there is this new file called spin.toml. We'll just quickly glance at that. This is the file that explains to Spin how this application should be constructed as a WebAssembly serverless application. We can see in here in the component, this is the thing we're going to be writing. This is going to have a default route that'll listen on anything. It'll use npm to run its build, and the binary the wasm binary will be called target/congress.wasm. So we're not going to spend too much time in that file there. Instead, we're going to get straight to the code. So let's take a look at index.ts. So this is what a serverless event handler looks like. So first I'm going to go in here and cd into the Congress directory and run npm install and let that install this first library here in the code. That's the Fermyon Spin SDK, which gives us our HTTP request and response and our handler. And then we can take a look while that's running at our actual request handler. So it's going to take an HTTP request. It's going to return a promise for an HTTP response. And all it's going to do is send this hello from TS SDK. So there we've got kind of our scaffolded out original function. So let's go ahead and build that. Spin build is going to package this up and turn it into a WebAssembly binary for us. And then when that's done, we can do a spin up and have it run a version on localhost for us. So it's listening here on port 3000. We can use curl and quickly issue a request and see that that worked. So let's just change this to something very trivial. TS Congress, save that. And then once more, we'll do this build process. Let's see, Control C, and then spin build. And then once more, we'll do a spin up as soon as that is done. So again, we've used kind of 3 commands in our local loop: spin new to create an app, spin build to build a WebAssembly module out of it, and spin up to create a local testing endpoint. And we can see, there we go. Now say we want to deploy this. We can actually just type spin deploy, and it'll go ahead, package this up again, and deploy it out to some endpoint somewhere. By default, it uses Fermyon Cloud, which is a hosted environment. You can also deploy spin applications to Kubernetes clusters, to Docker Desktop, to a Nomad cluster, and a variety of other places, all the way down to like a Raspberry Pi. But in this case, Fermyon Cloud will set us up a domain name and route us through to our new serverless handler. So there we've got it running on a public URL. Okay, so we've done spin up, spin build, spin new, and all of that, and seen kind of how we can build these kind of applications. But let's take a moment to dive into what makes TypeScript interesting in this environment. And that is that if you think about WebAssembly as a binary compiled format, right? It makes sense how you'd take a C program or a Go program or a Rust program, all of which sort of compile static binaries, and just change out the binary target from whatever the local one is, ELF or whatnot, to WebAssembly. And that is in fact how those languages work. But what do you do with a scripting language? Well, you have a couple of options. The first one is to compile your interpreter to the binary format. So compile the JavaScript interpreter to WebAssembly and then feed in the source files. That is a fine way of doing it in WebAssembly. However, what we decided to take a shot at doing was to come up with a sort of intermediary method of doing that. So if we go and look at the package.json and look at the build command, we'll see the build command is actually fairly complex. First, we're going to webpack it. Then we're going to make a directory called target. And then we're going to run this command called spin.js to wasm, which is going to take our spin file, our spin source, our JavaScript source code, and is going to compile it into WebAssembly. So what's actually happening here, and this is really cool, is it's taking the QuickJS interpreter. We're going to replace that with the SpiderMonkey one from Firefox, but right now it's the QuickJS interpreter and our source code. And it's running the QuickJS interpreter, loading our source code into the interpreter, and then freezing that loaded version and saving that out as a WebAssembly module. So essentially, we shave off all of the time necessary to do the JavaScript interpreter invocation, and we don't necessarily have to ship around all the scripting files because they're kind of preloaded into this. All of this is done by this awesome project from the Bytecode Alliance called Wiser, and we just kind of built the tool chain to make that part of the program. So that's it. That's how you do a TypeScript serverless-based application using WebAssembly and how you deploy it onto local with Spin and out into Fermyon Cloud. If you want to get started, go ahead and head on over to developer.fermyon.com. Take a look at the quick start guide. You can surf from there and look into how we do databases, how we do key value storage, how we do AI inferencing, and the rest. With that, have a great day. Bye.
Hi everyone, I'm Arthur, tech lead at Apps Platform team at a London-based company called Zoa. Today I'd like to talk about enhancing static code analysis using TypeScript language server. But first, let's discuss quickly what abstract syntax tree is and how can we use it for static analysis. Imagine we want to implement some automatic code transformation during compilation to remove all console log calls from the output. In theory, we could just use a regular expression to find all console log in the code. But remember, solve a problem with a regular expression and now we have one more problem. And actually, it will be quite tricky to write such a regular expression to handle all the different cases. Instead, we can make code transformations using abstract syntax tree. Let's take a look at code compilation process. Compilation usually contains 4 stages: lexical analysis, syntax analysis, semantic analysis, and code generation. Today we will focus on semantic analysis with abstract syntax tree, and we'll implement our code transformation using AST, and most of the tools of our ecosystem are using AST for analysis and code changes. Let's take a look at our code again. We are going to use a tool called AST Explorer, And on the right side, you can see how our code is represented by abstract syntax tree. The function call, which is console log in our case, is represented by call expression node in the tree, which contains other nodes like callee or arguments. This call expression is a part of the block statement body. Let's just remove it. Once we remove it, block statement wouldn't contain any other expressions in the body. So in the end, generating a code will get just an empty hello world function in this particular case. Going back to diagram, so what we did, we just transformed our abstract syntax tree, removing call expression node, and then we generated code from the new AST. Of course, we don't want to make these transformations manually, so let's implement a simple Babel plugin to remove all console log calls. In AST Explorer, you can select built-in Babel API to implement a Babel plugin, and you can see the 4 parts on the screen, like source code, AST, plugin implementation, and output code. Original source code contains 3 console log call expressions, which are represented by abstract syntax tree. You can see these 3 expression statements as part of the block statement body. Let's expand each of them, and you can find one of the call expressions with callee and argument nodes. Now moving to the plugin implementation. The implementation is quite straightforward. All we need to do is traverse over call expressions, check if callee is a member expression, and if that's a console log, remove the whole expression. In the end, we'll get an empty function hello world without console logs again because they were automatically removed. We can use AST and static code analysis to implement build time optimizations, minification, formatting, transpiling, like for example from the new language features to the older one to support all the browsers, for example, and many more. But how can TypeScript help with static analysis? Let's imagine now that we need to remove console log calls as before, but keep logs of arguments of number type. So, for example, we want to keep 1 to 3, or some constant if that's a number, but we want to remove hello world strings or now strings. With in-place values like 1 to 3, that's pretty straightforward because you can get this value just from the syntax. But it gets quite complicated with function calls or external variables like some constant here. We have to have some kind of type system in place or implement type inference ourselves, and TypeScript can provide such types. In this example, TypeScript can automatically infer the correct type based on the function signatures. And to make TypeScript not only check types with command line tool, but work with different code editors, TypeScript provides a language server, which is a separate process like a backend, and tools can connect to this server to get the information about types or use code refactoring tools provided by TypeScript. And the beauty of the language server is that it can be used not only for code editing or type checking. Following the language server protocol, we can interact with it programmatically and benefit from TypeScript knowledge about project and types at any level, including we can use it during our semantic analysis. TSMorph is an amazing library which wraps TypeScript compiler API and provides a simple interface to interact with. There is an example how we can configure TSMorph in your program. Now we can use it during abstract tree analysis. Let's see how we can integrate TSMorph into the actual plugin. So there is quite a lot of code here, but let's focus on the most important parts. So we want to have a getTypeAtPos function which accepts file name, code, start and end of the position we are interested in. And then we can create a virtual source file based on the file name and code and read the type for this provided position using TSMorph. The idea is the same as, for example, in IDE. If we need to see the type in our editor, we select an expression we are interested in, and editor shows types for the specific cursor position. In this case, instead of cursor, we just have programmable interface, but the idea is mostly the same. And now let's integrate TSMorph with our Babel plugin. We need to initialize the defined previously TypeScript class for TSProcessor. Then we can define a helper called getTSType with the file name, source code, and path to the node in abstract syntax tree as arguments. Each path in abstract syntax tree contains nodes with information where the node is positioned from start to end. This way we can check the type for the specific node. And in the end, we just need to return the type representation provided by tsmof. Having these simple helpers defined, let's see how our original Babel plugin can be enhanced with TypeScript support. To remind, this was the original plugin implementation. Let's integrate it with TypeScript language server. First of all, again, let's initialize our TS processor instance and define getTSType helper. Next, we can get code and file name from the Babel plugin state. And at this state, we already did all the checks, like we checked that this is console log expression. So we just need to go over console log arguments and check that each argument, we need to get the type for each argument and check that if that argument type is number or not. If that's not a number, we can just remove this argument completely. And if it is a number, we can just leave it. So in the end, we just need to check that there are any arguments left or not. If there are any, then we can keep this expression because it means that there are number arguments for this console log call. If not, we can remove the whole expression by path.remove. So yeah, this example is quite unrealistic. I don't think there is a real use case for console log and types of console log parameters, but there is a bit more practical example I've been working on with compile time CSS and JS library. I've been working on a library called Tidy, and the idea is that it can provide a simple functional interface with CSS function which accepts properties like inline styles. But the idea is that instead of generating the styles in the runtime, we can compile them during the build time and extract them into the separate style sheet. In this case, that's pretty straightforward because the blue value and the yellow value are static, so we can get them from just from the syntax tree. But what if our code is a bit more complicated and, for example, our styles depend on the runtime? In this case, color and font weight depend on the variant property and weight property, which are not known during the build time. But with TypeScript, we can get the actual type of each of the properties. Like, for example, for color, we can see that it can be either violet or purple. And for font weight, we can see that that's a union of lighter, normal, and bold values, which makes it possible for us to go over these values and pre-generate classes for each of the value. Thanks to the atomic representation of styles, we can compose these atoms in the end just as class name composition. And all we need in the runtime is just to identify the right hash for the class name for this specific value. But there is no styles generation, and again, we can benefit from styles compilation during the build time and extracting it into the separate style sheet. If that sounds interesting to you, please check the tidy.dev website and tidy repository. It's still in a quite experimental state, but any feedback or ideas will be very much appreciated. And in the end, just some notes. Use tsmof for programmable interface to interact with TypeScript compiler, and you can get TypeScript type hints in Babel or any other AST traverse just from the position in the code, which is quite useful. And TypeScript integration might slow down static analysis because that's quite a lot of overhead, and it might be a good idea to apply some performance optimizations, for example, isolated into the separate worker. There are dozens of different language server protocols. It's not just about TypeScript, so you can build lots of different integrations as well. And in the end, last but not least, types are not 100% trusted, and they can't be because there are types like any, or there are comments like TS ignore. So the more attention you pay to the type safety of your code base, the more you can benefit from it, especially during the compilation and build time. There are some useful links, please check them out. And thank you very much for your attention.
Thank you so much. Those were some amazing talks. You can similarly address your questions to Jamie, Matt, and Arthur on spatial.chat and Discord. Let's move on to our second block of lightning talks. Please welcome Liz Parody. Yes, our MC right here is also a speaker, and she'll talk to you about unlocking TypeScript's potential, exploring the power of ecosystem tooling. And we also have David to talk about replacing shell scripts with cross-platform TypeScript, and Tibert, who will talk about advanced linting rules with ESLint. Folks, the stage is now yours.
Hello everyone, I'm thrilled to be here today to talk about a topic that has been transforming the way we write and maintain JavaScript applications, TypeScript and its incredible ecosystem of tools. I am Liz Parody. I'm working on a very cool open source tool called RunMe that you can use with any TypeScript project, and I will show you very briefly later. TypeScript true powers lies not just in type system, but in the vast ecosystem of tools that surround it. Today, we're going to dive into the world of TypeScript ecosystem tooling and uncover the transformative capabilities that can supercharge your development workflow. Whether you're just a seasoned TypeScript developer or starting to use it, you will leave here with a renewed sense of excitement and knowledge about the tools at your disposal. So, first, we're going to discuss the essential tools for project setup. Oh, I know. I'm sorry. I made a mistake. Oops. Can we start again? Okay. Yeah, because I forgot to show this slide. Yeah. Hello everyone, I'm thrilled to be here today to talk about a topic that has been transforming the way we write and maintain JavaScript applications, TypeScript and its incredible ecosystem of tools. I'm Liz Parody, and I'm working on a very cool open source tool called RunMe that you can use with any TypeScript project. I will show it briefly later. So let's begin. TypeScript true powers lie not just in its type system, but in the vast ecosystem of tools that surrounds it. Today, we're going to dive into the world of TypeScript ecosystem tooling and uncover the transformative capabilities that can supercharge the development workflow. So first one, we're going to focus on the project setup. We will discuss the essential tools for this. Setting up a TypeScript project can be daunting, but do not fear. We will explore the tools and techniques that can make this process smooth and painless. Setting up a TypeScript project efficiently is the first step towards a successful development journey. Here are some essential tools and techniques to streamline your project setup. The first one is Package Manager. Use popular package manager like npm or yarn to manage and install package easily. npm init or yarn init can initialize your project and create a package.json file. The second is project scaffolding. Instead of starting from scratch, consider using project scaffolding tools or templates like Create React App, Vue CLI, or Angular CLI. These tools generate a project structure and configuration file tailored to your needs. The next one is tsconfig.json. The tsconfig.json file is critical for configuring your TypeScript project because it allows you to specify compiler option, target environments, model system, and more. I will configure ts.json, ensure TypeScript works harmoniously with your project. You can generate a basic tsconfig.json using the tsc-init. And TypeScript starter kits. Explore TypeScript starter kits or boilerplates for specific project types, such as Node.js, React, or Express. These kits often come with predefined configurations, saving you a lot of time and ensuring you best practice. And Text Editor, or IDE. The most recommended piece is Visual Studio Code. VS Code is a popular code editor that offers excellent TypeScript support, including 6-time highlighting, auto-completion, and debugging. One super cool tool that doesn't necessarily involve TypeScript, but it can be super useful, is RunMe, which lets you execute commands and scripts inside Markdown, even TypeScript snippets. Let me show you a very quick example here. So with RunMe, you can just click a button and run any TypeScript code in your Markdown file. This is a TypeScript.md file. So if I click this, I'll be able to see the code. And also, it can show me TypeScript errors. Here, I put a string where it should be a number, so it tells me all the TypeScript errors inside my Markdown file. So if I correct this and just change it for a number, it will be correct. You can change any language around here in TypeScript. Okay, the second tool that we're going to cover is code analysis. Code analysis with TypeScript involves leveraging its strong type system to catch errors early and improve code quality. So the first one is type annotations. Type annotations to annotate your variables, function, parameters, and return types with TypeScript types. This practice provides clarity to your code and allows TypeScript to perform type checking. The next one is type inference. Because TypeScript can infer the types based on the context, make sure to use this feature to write cleaner code without explicit type annotation while still benefiting from type checking. The next one is code navigation. TypeScript-aware code editors like Visual Studio Code provide robust code navigation features. You can use features like go to definition and find a reference to quickly explore your code base. And finally, TSLint and ESLint. These linters help enforce coding standards and catch potential issues in your TypeScript code. Configure them to align with your project's specific coding guidelines. The next one is testing and deployment. Testing and deployment are critical phases in software development. TypeScript can simplify this process by, first one, testing frameworks. You can choose the testing frameworks just like Jest, Mocha, or Jasmine that supports TypeScript. TypeScript provides type safety for your tests, reducing the likelihood of runtime error. CI/CD integrations, of course. Integrate your TypeScript project with continuous integrations and continuous development pipeline. Tools like Jenkins, Travis CI, or GitHub Actions can automate testing and deployment. The next one is Docker. Docker containers provide a consistent environment for your application across different stages of development. Containerizing your TypeScript application ensures reliability and scalability. The next one is code quality. Maintaining high code quality is crucial for long-term project success. Now let's see. The first one we're going to see is intelligent code editors. Use editors like VS Code, which we mentioned before, which offers intelligent features such as auto-completion, refactoring suggestions, and real-time error highlighting, making your code experience more efficient. Code formatters like Prettier can automatically format your code according to defined style guidelines, ensuring consistent code formatting across the project. And linters that we talked before about TSLint or ESLint, these tools help enforce code quality rules and best practices. The next one is code-based maintainability, to ensure that your code base remains maintainable as it grows. So, there's 3 recommendations. First one is type checkers. TypeScript built-in type checker helps catch type-related issues before they reach production, reducing the chances of runtime errors. Also, static analyzers, tools like TSLint, SonarQube, or ESLint with TypeScript support can analyze your code for potential issues, security vulnerabilities, and code smells. Refactoring tools. Leverage refactoring tools provide you code editor to efficiently make changes to your code base while maintaining consistency and reducing errors. And TypeScript libraries and frameworks. These TypeScript libraries and frameworks align with your project's requirements. Some examples include React with TypeScript, Angular, and Next.js. And finally, some TypeScript best practices. While TypeScript provides many benefits for developers, it's important to follow best practice to ensure that your TypeScript code is maintainable, scalable, and efficient. Here are some best practices to keep in mind when working with TypeScript. The first one is to enable strict mode. TypeScript strict modes enforces restricted type checking and delivers more helpful errors messages, catching bugs earlier and enhancing code robustness. Avoid the any types. While TypeScript permits any types, steer clear from them whenever possible, because any types reduce code maintainability and introduce hard-to-detect bugs and weaken type checking. Use interfaces over classes for shape definitions. For object or data structure shapes, prefer interfaces over classes because classes define behavior while interfaces specify shape, leading to clearer type definitions and improved code organization. The next one is enforce coding standards like TS-Lean and establish a time with coding standards to ensure consistent and maintainable code. And finally, cautions to use type assertion. Employ type assertions sparkling and only when necessary, because excessive use undermines TypeScript benefits, permitting unchecked types conversion. Rely on TypeScript type interference and structural type checking instead. And finally, the conclusion is that TypeScript's true potential is unlocked when you harness the ecosystem of tools and practices. By mastering project setup, code analysis, testing, development, code quality, maintainability, and leverage libraries and frameworks, you maximize productivity and build more robust and scalable applications. Because remember, TypeScript ecosystem is dynamic and continually evolving. Stay curious and explore new tools and techniques to further improve your development journey. Thank you for joining me in this exploration of TypeScript's powerful ecosystem of tools. See you!
Hi everyone, I'm David Sherritt, a developer at Dino, and today I'm going to talk about why you should replace your shell scripts with cross-platform TypeScript. This is not a talk just for JavaScript developers, but for developers from any language and background. Personally, TypeScript is not my primary language, but I use it in almost all my projects, and this talk will outline how and why you should also consider doing that. So why do we use shell scripts? We often use them because they work out of the box on the system we're on, so that's convenient. They are easy to spawn, they have concise syntax, and they execute similarly to what we write on the command line. So if you have a command you often run in your terminal, you can often just copy and paste it into your shell script. There's some downsides though. The first major downside is it's system dependent. Shell scripts can't be taken and run on every platform. Mostly they won't run out of the box on Windows. Sometimes this is even the case across Unix-based systems, depending on how the shell script is written. Also, basic Unix commands don't work on Windows out of the box, and telling Windows developers to use WSL is not a great solution. That can require them having to set up a new development environment within WSL just to run the script. Shell scripts are great if you're executing a few commands, but it's difficult to increase functionality without drastically increasing complexity. Another point specifically for JavaScript developers is shell scripts present code we need to maintain in yet another language. We also can't pull in and use our favorite JavaScript libraries. Finally, there's no type checking. We don't get code completion to help us develop, and all the other nice tooling that TypeScript provides. Now, why should you use TypeScript instead of shell scripts? First of all, it's familiar. and TypeScript and JavaScript are popular languages with a large community. Many developers have at least touched JavaScript or could at least understand its syntax. Second is type checking and tooling. A very large benefit of TypeScript is that its tooling is great, even if we're just using JavaScript. We get features like code completion, go to definition, and type checking errors in the editor. Now this talk is not just about why you should replace shell scripts with TypeScript, but also why you should use Deno while doing that. First of all, it's far easier to write cross-platform scripts in Deno than shell scripts, because most APIs work cross-platform. Obviously, there's some platform-specific APIs if you need them, but usually we don't have to reach for those. Second is single-file scripts. I'm obviously biased, but I think Deno is the best platform for writing single-file scripts. For example, in Node, using TypeScript requires extra setup. You need to have a package.json file to define dependencies. This also requires anyone running your scripts to have to remember to run npm install first, and also after any changes to the dependencies. That process then creates a node modules folder in the directory tree. So right there you have 2 extra file system entries. So it's not a single file script. Whereas in Deno, TypeScript is supported out of the box, so you can execute TypeScript code directly. It's optional to use a config file to define your dependencies, and it's also optional to have a node modules folder for vendoring npm dependencies. It's important to note that you can still use that model if you want, but it's opt-in. Third, dependencies are auto-installed based on the code, so no separate npm install setup command is necessary. Finally, Deno is sandboxed by default. Node recently got an experimental permission system, but it's opt-in rather than opt-out. Another great thing about Deno for single-file scripting is it's possible to define the dependencies in the script file itself. For example, you can pull in packages from npm or use HTTPS imports to easily host scripts on a web server and reference those directly. One bad part about this is it's verbose to launch sub-processes using the low-level process APIs available in both Node and Deno. But that's not a big deal because we can pull in a dependency that helps make it more like shell scripts. There's a library I wrote called Dax. Dax is a cross-platform shell written in JavaScript that has common cross-platform Unix commands built right in. It also has other useful APIs to help out with scripting. Here's some examples of running commands. The shell syntax it supports is common syntax found in shell scripts. For anything more complex like loops, you probably just want to use JavaScript for that instead. Again, to emphasize, all the code shown here works on Windows. Launching commands is slightly more verbose than shell scripts for simple cases, but in my opinion, the advantages of being able to write these scripts mostly in JavaScript outweighs the slight extra verbosity when launching commands. Also, it could be argued that this is less verbose in complex cases. For example, as shown on the last line of this code, accessing properties on the JSON output of a command is quite easy. Finally, Dax has logging APIs, a path API. For example, here we create a path_ref object from the source for the source directory, get if it's a directory, then call makedir on it to create the directory. Then we get a reference to a text file within that directory, write some text to it, or we could even read from that text file. Or we could write some object as JSON to a file, or read from it deserializing to a JSON value. There's also APIs for doing prompts, making selections, and showing progress. Finally, there's a request API built in that's similar to the fetch API but less error-prone and with some additional helpers on it. Anyway, there's a lot more to this, and I'd recommend checking out the documentation for more details. Thanks for listening to my talk.
Hello, my name is Tibor Blaneši. I work on JavaScript static analysis at Sonar, and in this talk I would like to show you some more advanced techniques for linting with ESLint. Let's have a look at the following function, which I have found in the VS Code codebase. This function returns a range of numbers between two values passed as an argument. If the argument is not provided, it will assume that the range should start from 0. When we use some static analysis tools such as SonarQube, it will quickly show us that there is an issue with this code. For some reason, the value assigned to the variable from is never used later in the code. The logic handling the arguments is actually duplicated. This kind of errors, when value written to the variable is not used is called a dead store. SonarQube provides following explanation of why this is an issue. A dead store happens when local variable is assigned a value that is not read by any subsequent instruction. Calculating or retrieving a value only to then overwrite it or throw away could indicate a serious error in the code. Even if it's not an issue, it is at best a waste of resources. Therefore, all calculated values should be used. In the following couple of minutes, I will try to explain how this kind of errors can be detected with static analysis. First, we will use a representation of code called control flow graph. In this representation, nodes called basic blocks contains only statements which are executed sequentially. Jumps are represented as arrows between the blocks. So here we have a control flow graph for the function I showed earlier. We will only show part of the graph which is relevant for the issue to keep it small. In the next slide, I have the same control flow graph annotated in red with events which are provided by ESLint when we write a custom rule. ESLint API provides two objects, code path which represents the control flow of the whole function and control path segment for each basic block. ESLint then fires events for the start and end of the code path and for the start and the end of each basic block which is code path segment. So in the code, what we will write is the following object which contains an event handlers for the code path events. We don't have the time to go into implementation details, but in the following slides I will quickly describe the basics of the algorithm. The base of the algorithm is liveness analysis, which tells us which variables are live at any given point in the program. Variable is live when value it's holding might be needed in the future. For each basic block, we will compute 4 sets of variables. Gen set with variables that are being read in the basic block, kill set which contains variables that are being written in the basic block, inset with variables which are live at the beginning of the block, and outset with variables which are live at the end of the block. To compute these sets, we will use following 2 rules. Outset of the current block is union of all insets of its successors, and inset of the current block is a difference between outset and kill set unionized with gen set. Now I will go through basic blocks of the function I showed earlier, and we will compute the values of these sets. So we will start at the bottom of the graph to compute the sets of this basic block. So we will assume that from and to are being read later in the function. So gen set is set to from and to, And we will ignore that there is something written, so kill set will be empty. From this we can compute the inset as being from and to. And now we will move to the predecessors of this block. So, because the inset of the successor block is from and to, we can say that the outset is also from and to, following the first rule. In this basic block, we are reading the value of arc, so genset is arc, and we are writing values of from and to, so killset is from and to. From this, we can compute the inset as difference between outset and killset. Because these sets are the same, the difference is going to be empty. The inset is the union of empty with genset, which contains arc. Therefore, inset is going to be arc. Now we move to another block where we are, again, the outset is set as an inset of the successor block, so it's from and to. We are reading the value of arc, so genset is arc, and we are writing the value of from. From this we can compute that inset is arc and to. Now when we move to the predecessor of these two blocks, we can set the outset to be union of the inset of the successor blocks, so it's an arc and 2. We are reading the value of 2, so genset is 2, and we are not writing any variable, so killset is empty. From this we can compute the inset as a difference between out and kill, which is arc and 2, and union with 2, which doesn't change anything. From here we move to the predecessor of this block. So we know that outset is arc and 2. We are reading the value of arc, so genset is arc. We are writing the value of from, so killset contains from, and from this we can compute the inset to be arc and 2. In the next block, the situation is almost identical. The outset is arc and 2. We are writing the value of from, so killset is from. We are not reading any variable, so genset is empty. From this we compute the inset to be arc and 2. And now we move to the first block, where outset is the arc and 2. We are reading the value of 2, so genset is 2. We are not writing any variable, so killset is empty. Therefore, we can compute the inset as being arc and 2. So now we computed the values of these basic blocks. Every time we compute the inset of the block, we need to recompute the predecessors of the blocks. This is very important, especially if there are loops in the graph, because we will need to continue until the sets are not changing anymore. Once this is finished, we can analyze the computed values and detect the issues. We will raise an issue for every variable which is part of the kill set, which means it is being written to, but it is not part of the outset of the block, which means that the value is never needed in the subsequent blocks. So in this case, in our function, from is written in the beginning, but it is not read by any subsequent block because it is being written to again. That's why we will raise an issue on this write to from. So if you want, you can have a look at the complete implementation of this algorithm in our JavaScript Analyzer, which is an open source project on GitHub. And the algorithm is in the rule 1854. And this analyzer is used in SonarQube, SonarCloud, or SonarLint. I hope you found this talk interesting, and thank you for your attention. Bye.
Thank you so much. I personally enjoy those talks so much. And do not forget to also address your questions to Liz, David, and Tibber on spatial.chat and Discord. And now the third block of lightning talks is not quite over yet. Please welcome the speakers from our last block. We have Michael, who will be talking to you about the potential of higher kindred types for library semantics. Lucas, with TypeScript Survivor Guide, life-saving tips and techniques. I think I personally need that a lot. And lastly, Akash will be talking about unleashing object proxies, building type-safe wrappers for anything. Let's take it away.
Hey there, everyone. I'm excited to talk about the potential of higher kind of types for library semantics today as part of the TypeScript Congress 2023 Lightning Talk. First, a little bit about myself. My name is Michael Poteet. I'm an engineering manager at Volley, where we are creating the future of voice-enabled entertainment. I have a passion for type-level programming. I've created HK2 Toolbelt, which we'll mention a little bit later. You can read about my programming on my blog at code.lol. And I'm excited to talk about the flexibility of higher kind of types in TypeScript today. So, library semantics, what do we mean by this? So, we want the type system to infer as much about our code as possible. Often, libraries don't do it. So, in this code example, we're using Lodash. We are doing a chain on some sort of object. We're calculating the keys, and then we're mapping those keys to convert them all to uppercase. What we know the value to be is A, B, and C in uppercase, but Lodash just infers an array of strings. So this is sometimes very inconvenient and forces us to make like explicit type declarations when we otherwise would not have to. So HK2s basically make better inference possible. We can use HK2s to represent type-level operations, and we can compose types together using functional semantics. We can do this so well that end users never have to write any sort of custom types themselves. So what are higher kind of types? Basically, a kind is a type associated with a type constructor. In TypeScript, you would know this as like type foo of t equals t, right? So the simplest kind is just star. These are your base types. And the next simplest kind is star to star, which is your normal sort of one arity generic, so like capitalize of S or promise of T, etc. So TypeScript natively supports these two, but we want more. So we would like to support, for example, a type that takes in a type generic itself and a value which represents an array, and we want to loop over that array applying this type operation to each element. So the kind associated with this would be this sort of complicated expression, which we need to do clever things to support in the TypeScript system. So what are we actually trying to do? So what we want to do is we want to write code like this. So we want to say, we want to use this operator or any sort of application operator and say, all right, we want to apply the operation capitalize to map so that we get map capitalize, which, converts capitalize into something that can be mapped over an array. And then we want to apply that to an array to get a result. So we're extracting out the logic intrinsic to looping over an array and applying a transformation to each element. This is surprisingly possible in TypeScript. So here's the minimum definition needed to create this rich set of higher kind of types. Basically, what's going on here is that we are exploiting the fact that on interfaces, the types of functions can be a function of attributes on the object. So basically what we're doing is we are filling in the parameter represented by the X element on line 2, and then extracting out the return type of F. And as we saw before, if I applied, like, for example, the identity function to 1, we would just get 1. Here's an example of the identity sort of higher kind of type. What we say, identity extends kind, and then we just return type of x for the underlying sort of transformation we are representing. So always the transformation is on the right-hand side. This is a slightly more complicated example. We don't need to understand or walk through all of this, but essentially on line 11 here, we are applying append to this bar string, which creates a function that appends the string bar to any string that it's given, and then we're passing in foo, so we get foo bar. So what you'll notice is that all arguments are curried in this sort of like new semantics. We can also do map, as I mentioned before. Again, we don't need to understand the entire logic here, but notably, what we're doing is we are taking this append function that we made earlier, we are sort of converting it to something that can be mapped over an array, and then we are running it over an array, so we get foobar and basbar. All right, so that was a lot of code listings. The question would be, how do we actually use this in real programming? So to do this, generally speaking, we want to use a process that I call kind reification, but basically we are bringing down a higher kind of type, and we are giving it a callable interface. So on line 2, we're saying the callable function is going to be a generic function that is an input of the kind associated with this type. When we're inferring what that literal constant is going to be, and then we're basically recursively executing that across all of the like arguments that this higher kind of type is returning. I'm not including the full implementation here, but it's not much more complicated than this. And essentially what this allows us to do is to create functions which behave like higher kind of types. So using this, we can create this reified map view, including the implementation. So we have a map here, very simple sort of curried map logic, and then we say as reify map, and then we have append, which is just as reify append, and then we can create this result expression where we are sort of mapping over an array with this append statement so that we get hello exclamation mark world exclamation mark. So we've created these composable functional utilities that are sort of that have intelligent type inference associated with them. So up until now, we've used point-free semantics to write our code, whereby we're not explicitly mentioning any arguments to our functions. But more often, folks use Fluent API design, for example, in Lodash with their chaining semantics. So we can actually represent that using HKTs. I'm not including the full implementation, but what we want in the end is, and what we can get, is a chaining interface that actually computes the type level result as you are executing these operations and chaining these operations together. So what we infer in the end is A and B and C. That's my lightning talk. Thank you so much for listening. Please go out and improve the TypeScript ecosystem by writing libraries that use higher kind of types.
Hello, I'm Lucas. I'm software engineer here at Klarna in Sweden. I'm originally from Brazil and have been coding for the past 11 years and sharing what I learned. So if you like this talk and have any feedback, please reach out to me in my socials. Just put the name of the network in lsantos.dev and you get there, or just lsantos.dev will also do the trick. But cutting to the chase, I will be presenting the best tips and tricks that I learned with TypeScript in these past years with you, and all of this in 10 minutes or less. So let's go. First thing, over the past few years, I lost how many times I have copied and pasted the same tsconfig over and over again until I discovered that I could just use tsconfig bases. It's an official repository that has several tsconfig bases for you to extend naturally, and tsconfig supports that through the extends property. So as you can see, we can use the extends and pass the name of the repo following the configuration that we want to extend. And if you don't like any of those configs, you can just override it by writing it again in the bottom. But this is not only for the tsconfig basis extension. So you can actually extend if you have local files, if you want to extend, like in a monorepo configuration where you need to extend the base file. So what you can do is you just need to put that path in that file in its magic. So you never have to copy a tsconfig again. And for the second tip, I wanted to something that took me some time to understand how powerful it actually was. I'm talking about branded types. Normally, you don't see a lot of those in TS Code. That's because they have a very specific use case, and those cases are massively helpful, like when you have different types of strings, but still strings, like a UID. You can brand your type to mark it as an ID, even though it's a string, but it's a string of a certain type, making it impossible for to pass a name to an ID by mistake, for example, or even to pass the wrong type of ID to some function. However, branded types can only be converted through explicit typecasting, which is bad, so we can make a function to explicitly convert one type into another. But there is a better way to do this. And I present you the third survival tip, the type guards and assertion functions. So when you use branded types, they're usually followed by one of those two, because guards and assertion allows us to narrow down the type without having to explicitly cast it. It takes, like this example, I can explicitly cast anything to an ID and it's going to work, basically. The trick here is basically to add a new function that will guard that type, and this function is typed by saying that a type is of another type as a return annotation. This way, we can do an if check and actually check the ID is an ID with the regex. But this is not just adding noise, this if there, I don't like it. This is where we have assertion functions. They're declared by saying that the return annotation that the function asserts a parameter of a given type. So the main difference between one and the other is that the assertion functions don't return anything, they throw, while the guards return booleans. So this way, branded types can be more useful, and you can also create guards that are lightweight. Well, for the next tip, enums, the big elephant in the room. While some don't like enums, I am particularly very fond of them, and I think they have many uses, but you need to know them. So that is the tip, know the enums. So let's start with the basic number enum, right? Enums are one of the few structures in TypeScript that produces JS code when outputted in transpile mode. It looks hacky, but it makes sure that you will always be able to match either a number or its type. The problem is that you can use both, and it kind of defeats the purpose of enumerating things, right? So what we can do is that we can use string enums, which are easier to read, but we cannot directly assign the value it contains to the variable that has its type. So you need to convert, for example, a user input into an enum value if you need to assign both. In my opinion, it's worth it because you standardize the code. However, enum types can also be a very good substitute for this. And the final one is a const enum. It does not produce any output because it will replace its calls with its values in the transpile.js. It's like magic. So in this example, all the enum values will be replaced with their enums in the final code. It won't produce any output, but also doesn't standardize the things. So there is still magic numbers popping up from nowhere. Also, const enums don't exist in runtime, so you cannot access their keys or values the same way you can do with others. So they're expanded into their underlying values, and that's it. There's no coming back from them. For the next survival tip, a new one, something that's pretty brand new. In TS 5.2, there's a new keyword, which is also coming to JS soon, that allows you to explicitly control resource disposal and memory cycle. It's the using keyword. It all starts with the symbol dispose or the async dispose that you put in an object class or anything that accepts a method like that. This method will do the work of disposing the resource. And then you just need to declare a variable with async using or just using, depending on your object, it's a sync object or not. And this is a very good life-saving tip because you can abstract a lot of the complexity from object lifecycle away from the usage of that object. For one of our final tips, I want to bring you the world of unknown and how it can actually save a lot of lives. In Klarna, we have a lot of places where we deal with legacy systems, especially those that were ported to TypeScript, and all the places where people didn't know what to type, there isn't any there, and that's very bad. Bad because we're literally disabling TypeScript for those types, and we are not inferring anything. There is no types. Well, we all know how bad any is in general, but there is a solution. And this solution is unknown. We start implementing unknown, and the catch is that everything can be assigned to unknown, but unknown cannot be assigned to anything. So this way we protect the data where it's actually used. And a good example of this would be the typing of a JSON parse function to return unknown instead of any. So you can see that in the old object, we can even use keys that are not there. And this would definitely break in runtime. Besides, unknown is a very good way to migrate from JavaScript to TypeScript, because as soon as you create one, you already know the whole path that resource has taken and who is using it due to the error it's going to create. And lastly, I wanted to introduce the case conversion utility type using uppercase, capitalize, or lowercase. The context for this is that in Klarna, we have a lot of other services using snake case and some other services that use camel case. Because of that, we needed to convert API calls and returns to the specific casing. And this led to the creation of these duplicated interfaces, where one was the snake case and the other one was the camel case. So you don't need to do this. Obviously, there is like an overcomplicated way of making it generic, like I did here. But in this example, what I'm creating is a type that takes a string, split it from snake case using a recursive type, and make it to camel case. And then we can use a mapping type to map all the keys from an object to camel case. And now we don't need to duplicate our interfaces anymore. And that was it, basically. 10 tips in 10 minutes. So thanks a lot for being here and for listening to this. And if you do have any questions, please join me in my socials and in the websites down here. So see you soon.
Hey guys, my name is Akash Joshi. I'm a software engineer at SigTech, and today I'm going to talk about unleashing object proxies, building type-safe wrappers for anything. So object proxies, they are an amazing tool which are severely underexplored, but are quite widely used in all of the libraries that we use in our day-to-day. So I'm going to explain how they work, what they are, and how you can use them as well. So what are object proxies? Object proxies are basically middleware for your objects. So think of them as a wrapper around your object with which you can control what input comes into the object and what you return from the object whenever a user tries to access a method or a property. So what are some of the use cases that we see with object proxies in the real life? So one of the first use cases that one can think of is controlling data access. So doing input validation or implementing an access control layer on any sort of object which can contain privileged properties. So for example, on a bank, if you want to create an object which contains a user's data, then based on whether a user has, one of your developers have access to that property or not, you can actually do input validation on it. So if the user or the developer has access to that property, then you return it. Otherwise, you can return an error or whatever you want to do instead. Similarly, you can add logging to your objects via object proxies. So if a user tries to repeatedly access an unauthorized data, or you just want to have a log of all of the activities that your developers are doing on any privileged object, then you can add logging to it via object proxies, and any accesses are logged to one of your access logs. But most importantly, what we use object proxies for is response handling. So this can involve returning something else based on what the user provides, or lazy loading certain objects. So for example, just continuing with the user case, let's say we have an object which contains a user's banking details, like their address history, their transaction history, anything, but you don't want to fetch all of it at runtime. So whenever someone tries to access their address history, then we make a network call to the address API, get all of that data, and then return it via the output. So on the developer side, it just looks like you've made a property call, like a dot call to an object. So that would be user.address. But in the backend, it will actually make an API call. And you can also implement caching and other things on top of it to actually make your object calls faster. In the wild, object proxies are used by Prisma. So have you ever thought about how Prisma knows what all of your tables are and how it is able to access all of them at runtime, even though it actually isn't present in their code base? What they do is they generate the types for all of your tables, and then they apply them to an object proxy. So whenever you are accessing your property by using the dot methods, so like prisma.analytics, prisma.user, prisma.posts, what it actually does is it makes a network call via object proxies to the actual database, and then fetches those results and then returns them to your client. So of course, it isn't all hard coded into the Prisma's code base, but they generate it at runtime via TypeScript, and then object proxies take care of the rest. Similarly, for TRPC, TRPC works on a similar concept where they allow you to make object calls, make method calls from your front end to your back end quite transparently. They use object proxies as well. They expose a router object on the back end and expose its types, and then use those types on the front end. So the actual proxying happens on the front end, where any call to one of their queries is actually transpiled by the object proxy into a network call, and then the network call executes on the back end to actually return you the result on the front end. So what we are going to do now is we are going to implement a very simple version of the TRPC library, or just try to implement a little bit of RPCing to the backend ourselves using object proxies. And I'm going to also explain how object proxies work. So this just involves a little bit of code. Firstly, let's look at what our server looks like. So this is a very simple Fastify server. If you go to Fastify's documentation page, this is similar to what you will see on the main page. In fact, this is what I've copied from there. The only route that I've added here is /RPC. It accepts a procedure name and a set of parameters for that procedure. And it then parses this data to string, and then it applies those parameters on those procedure, and then returns the response to the front end. Where are we getting the actual procedure from? So let's say we have an API object which the developer provides to the server, and this API object contains all of the APIs that the developer actually wants to expose to the client. In this case, we are exposing hello, which just returns world, and then another method called sum, which returns the summation of two numbers. And see how we have actually defined the types correctly here. This is because we are going to use the properties of TypeScript to actually pass that type to the client as well. On the client side, now what we are going to do is that we are going to define a very simple object proxy. Have a look at the main method here, where I will define a few lines of code which try to access some properties of the object proxy and try to get the results of it. So the first one is that we are trying to destruct a property called hello on object that doesn't exist yet. Next, we are checking for two properties, whether they exist on the object. And lastly, we are trying to make method calls on the object proxy, and then console logging the result of it. So let's quickly define our object proxy here. The syntax for defining object proxies is to use new proxy to define them. The first parameter it takes is the target object that you want to build it upon. So the standard way would be to use a wrapper over an existing object. In this case, we are just going to use the properties of the wrapper, so we don't use any existing object. So I pass in an empty object. Next, we actually look at all of the properties that a proxy accepts. So they are primarily get, has, and apply. These are the properties that you will be mostly looking at while building object proxies. The get property is the dot method. So when you are destructing hello, or you are doing client proxy dot sum or client proxy dot anything else, then the get method is called, and you can return whatever you want from it. Has method is sort of like has own property, which actually checks for whether a property exists in an object proxy or not. And in this case, we are just returning true. So these two methods which check whether these two parameters exist in the object property should actually return true, even though they don't really exist there. And then lastly, we have apply. I don't think we have enough time to go into the depths of it, but it is a trap for any method calls that you make on your object proxy. In this case, get should be enough. We'll go into the depths of it as we actually define it. So let me, so we have right now we have a type error here which says property hello does not exist on type empty object. That is because it's actually returning a type of empty object, as that is the default object that we passed here. But since we are going to create traps on this object proxy, we have to now fake what it actually looks like. So let's try to console log on get here. And the first parameter that it takes is the target object. In this case, our target is a empty object, so we just get underscore. We don't really need to use that. What we are actually looking for is the property being called here. And then we will console log on property. And when we run this code here, this executes main, which executes all of the lines here. We will see the actual output. So the error that we are getting here is hello is not a function, which is expected because it is calling the hello method here. We are going to define the code for that. But what we are more interested in is the first 3 lines here. We are getting property hello when we are trying to console log. When we are trying to access the client proxy property here, and then we are getting true and true for the in property. We are getting true there because we have just defined true here. If we change this to false and then we save it, this should run again. So that should then print false. That just prints whatever we want it to. And then this is actually printing the actual property that we are trying to access, which is hello in this case. And yeah, let's try to solve this error next. Hello is not a function. So this is because we are trying to make a function method call on the properties being returned here. So to resolve this quickly, this should just console log args instead. And if we, yeah, now it returns correctly and it just prints the args being passed here, the property, and similar for sum, it's printing what method we were calling, which is sum, and then the parameters being passed in here, which is 3 and 123. Now we are going to quickly try to make an API call to our backend and return the data based on this. What our backend looks like is it accepts a procedure name parameter and a params parameter, and based on the procedure name and params, it makes the API call. So for hello and params being an empty array, it returns world. For procedure name being sum and the parameters as 1 and 2, it returns 3, and hypothetically for other params, it should return the right result as well. So let's quickly do that. In this case, what we do is we just make a fetch call here. So fetch to the backend, http local host 3000. We need to pass in the parameters correctly as well. So I'll just make a note of that, add async in here. So our procedure name, yeah, we need URL search params. So search params is equal to new URL search params, and then add in a procedure name, which should be the property, and then I believe the args here, params, sorry. So pass in the params as json.stringify args. I think this needs to be a 2-string, and yeah, that resolves that. And then we just add this in here into the API call, and then while returning the data, we need to do response.json, of course. That should return our result. So now when we are running the method again, it should return the result, but I believe I am not logging here. So let me have a quick look at what went wrong. So yeah, as we can see here now, when we are trying to access these properties via the method calls, this is actually calling the API on the backend. So on the server side, what is happening is that it's accepting the procedure name and params that we are passing in via our URL search params here, and then it's parsing them and then returning the actual response via procedure.apply. Now in this case, that's pretty much it in terms of our object proxy, but we are actually missing the actual part still, which is actually defining the correct type. So I can actually import the type of API from the backend and then try to apply it to our client proxy here. So, so let's try to do that. If I do as type of API here, then it should hypothetically apply the correct type to my client proxy here. And then if I try to do something like client proxy dot, then it should also return the correct types here. But what we are missing is that it doesn't return a promise. In our case, the client proxy actually returns a promise whenever you're making a method call, because it is actually making a fetch request. So we define a simple type here called promisify, which extends a record, and then based on the keys for that record, it just applies a promise to its return, to the return types of all of the existing methods. Now, in this way, if we wrap our method in this generic that we have just defined, then what we get instead when we are trying to do client proxy dot is that all of the results actually return a promise instead. And so we get the correct type on this. And so we don't confuse our users anymore. So that is it for our object proxy. And what are the takeaways? The takeaways here for building your own object proxies are embrace, experiment, and explore. Firstly, embrace object proxies. Try to find out where you can find object proxies in the real world. You might be surprised to find that most ORMs might be using object proxies, and then a lot of RPC libraries use them as well. Experiment with object proxies. Try to create your own RPC libraries, share them on the internet, and just try to have fun with them. And then finally, explore. Try to push the edges of object proxies. TRPC or Rocket RPC, my library, wouldn't have been created if the people behind them wouldn't have tried to explore the edges of object proxies and what you can do with them. Same for Prisma and a lot of other libraries out there. So yeah, thank you. Thanks for this talk. Thanks for being a good audience, and happy coding. You can find me at my website, thewriting.dev, or on Twitter at thewritingdev.
Thank you so much. That was such informative talks by our amazing speakers here. Do not forget to address your questions to Michael, Lucas, and Akash on spatial.chat and Discord.
Wow, what a day, full of many learnings and amazing speakers, great talks. We would like to thank all of our speakers for sharing their experiences and knowledges with us. And also, thank you to our lovely audience for being with us, for watching and participating in our discussions and speakers QA rooms. Once again, thank you to our sponsors for your great support. We wouldn't be able to do this conference without them.
Again, we highly value your feedback. It helps us keep making the event better and better every single year. We have a form available to you at typescriptcongress.com/feedback. And when the talks are over, we're going to have a remote party with Draw Battle. Let's have fun together on spatial.chat. The after party is going to start after the closing ceremony in the interface track. Thank you all for being with us today. See you all at the after party. Bye.
Thank you all. See you.
So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions. So, you've put in the hard work of developing this new feature, and you've tested for errors exhaustively. But a user immediately reports an issue, and you don't know what's causing it. You wonder how many others are affected. What's the root cause? How long will fixing it take? There go more hours spent searching through logs. Now, if only you could see how each bug happened instantly. That way you could spend more time on your next project. Meet Rollbar, the continuous code improvement platform that helps developers discover errors in real time for faster resolutions.